Hi everyone, welcome to AME Academy. Our session will start promptly at 9 a.m. Welcome to the AME Academy. We will begin our session shortly. Please keep in mind if you have any questions throughout the webinar or session, use the Q&A button located at the screen below.
Let's see.
No. Oh, I think Heather wasn't indexed. Okay.
Let's try.
What did you switch to? Yeah.
I don't know. Why are you trying to?
Because you're
Oh, it's
Recognize
Welcome to the AME Academy summer session. We will begin shortly. Please remain seated and get ready for our summer AME Academy. Hi everyone. 2 more minutes until we start the AME Academy summer session. We want to welcome you and hope you enjoy this fantastic seminar with great speakers.
I'm disabled to share my screen. Can you see my screen? Good morning, good afternoon, and good evening to all of our virtual audience. Welcome to summer session of AME Academy from Boston, Massachusetts. We are going to start a very interesting and insightful workshop, and we will hear from experts from industry, academia, and students. It takes a tremendous amount of work organization, and communication to make an event at this scale possible. I want to thank the great team from AME and Dimension for all of the efforts and congratulate them for putting together a fantastic lineup of speakers whom we are going to hear from. I'm Ben Davaji from Northeastern ECE and the Smart Center. It's a pleasure to welcome you to AME Academy 2022. The Smart Center at Northeastern is sponsoring the AME Academy event. Special thanks to leadership, Professor Matteo Rinaldi and Dr. Benjamin John. We plan to have a hybrid event model for this event where we could serve both virtual and in-person audiences at our Isaac complex at Northeastern. Due to technical challenges, we switched to the virtual-only presentation for this event. I want to thank the team from Northeastern and the AME who worked tirelessly for in-person event preparation, and I hope we will have the next event in person. At the Smart Center, we are focused on integration of advanced materials, structures, and devices into nanosystems. We are exploring new fields and paradigm shifts in technology enabled by nanosystem integration, and AME, or additive manufacturing of electronics, has a potential to support and enable every single research trust. We are going to hear about the AME capabilities during the rest of the workshop. I want to highlight one of our strengths at Smart Center, where we are integrating nanosystems, piezoelectric nanosystems, which is driven from the wealth of experience on our campus and the state-of-art infrastructure to support development and characterization of the piezoelectric nanosystems at prototyping and production relevant scales. For more information about the Smart Centers and capabilities, please visit the center website. I can envision AME-enabled smart packages and interfaces will enable testing these systems at much shorter timescale and much higher flexibility in design. With that, I can't wait more for talks to start. I hope a healthy rest of the summer for everyone, and I will set the stage for AME Chair, Dr. Nolman. The stage is yours.
Okay, good morning, everybody. My name is Jaime Nolman, and I'm the AME Academy director. And first, before we start, a couple of logistics here. We would like people to use the chat room responsibly for any communications or questions as well. Sorry for the questions. Use the Q&A button to post any of your questions, and we will then rebroadcast them at the end of the speakers. The allocated time, the last 5 minutes, will be for a Q&A session. Question will be addressed, as we said, at the end of each speaker session, and during the closing remarks, additional questions. One important thing, that no financial questions are accepted. In the past, some people have been asking financial questions for the coordinators of the AME Academy. This is a purely technical session, and all financial questions will be ignored. So just heads up. So with this, I would like to thank the co-coordinators, James, Electron Inc., Nano Dimensions, PulseForge, and Enscript on this, and any other basically AME or printed electronics or the related industries, companies that supply equipment, materials, and so on. They are more than welcome to join as co-coordinators for the future sessions. Just please feel free to send me an email, and I'll be glad to coordinate with you guys to add you to the website as well as the future presentations. In any case, today we will see during the presentations the use of many of these suppliers or activities already and resolved by the end users. Also, I would like to thank TechLink. It's a platform based in Europe that is rebroadcasting this session to their members. And so we have a broader coverage besides what we are covering directly with our registrants, which is over more than 300 registered for virtual presence, covering not only North America and Europe, but also many countries in Asia. So I appreciate for the people who are staying very late or very early in the morning and joining us today. So with this, basically a brief recap of the program. After my introduction, we'll have Gene Weiner, who is very famous in the industry, who's going to give us an overview of altogether additive and semi-additive technologies for the fabrication of electronic devices, circuits, and so on. Then we'll look at the Professor Rash from FIU, who is going to talk about the impact of AME on packaging technologies, the direction that this thing can take, as well as then we'll see a presentation from Michael Kedem from ELTA in Israel, who's going to talk about the recent experience on SIP, followed up by the Mr. Yahya Ben Sayed from FIU, who will present embedding components and AME devices as part of sensors for biotechnology. Following then, Joe Beck from Altium is going to show us how to basically we can use an ECAD system to create the electrical connections in conformal surfaces coming from any mechanical CAD type of system. And following that, we have Professor Ying Wang from Florida, from the University of Southern Florida, who is going to talk about microwave and millimeter wave applications with AME type of technology. We'll have a break of about 45 minutes, and then in the afternoon, Melanie Gutierrez from Florida International University is also present about bioapplications for neural recording systems. Then Dr. Yurio Piro, also the PhD student in UMass, is going to teach us how to optimize and develop inks for millimeter wave applications. And then Dr. Daniel Hines will share with us testing methodologies for devices, especially with focus on AME 3D printed electronics. Then Professor Alex Cortus from Purdue will share with us his work on robotics, as applied soft materials for robotics. Then Michael Grady from Georgia Tech will be the last presenter covering applications also in the RF millimeter wave. So with this, just to continue a little bit and look at the drivers for AME, we lack the overall heterogeneous integration roadmap, which is basically looking at the 15-year type of horizon, where starting from the basic printed electronics antennas and the RF antennas, some near field antennas, going all the way to 3D molding, and then starting embedding components and packaging all the way to basically what we'll see today, which is the fully integrated type of systems. This roadmap is a working process and evolving with year over year. And one of the visionary things there is to create a structure that is a fully integrated, monolithical integrated type of device, which the substrate interconnects, capacitors, and system in package and everything in just one simple thing. While this is an ideal structure, I think the realization of this thing could be coming in the next future years as the overall technology continues maturing and the materials as well as the capabilities of the manufacturing equipment. So with this, if you want to see where AME fits within the industry, we have in one side the printed circuit boards, and then in the other, the integrated circuits. AME basically serves as a bridge in between these two areas. And as we will see from the presentation today, this is exactly what's happening as we see the limitations on the printed circuit board and then enhancing the capabilities of the integrated circuits as we start seeing examples of bare dies being integrated into packages, not the traditional SIP that the companies like Intel and TSMC and Qualcomm are doing, but more of the expanded ecosystem of integrated circuits and bare dies. That is a huge opportunity, and we will see an example on how that thing is being applied outside of those specific high, most advanced semiconductor devices. So if we look into the AME additive manufacturing electronics, we have the traditional surface conductive deposition, of a single or dual-sided conductive layer on predefined shapes, traditionally known as the printed electronics, but also the multi-layer dielectric and conductive deposition with simultaneous formation on dielectric and conductive layers, multi-shapes structures, as we can see here from the X-ray showing all the way in the right, a traditional type of electronic circuit, 7 layers with the vias and the traces, but also structures where basically the whole device is manufactured, except in this particular case without the electronics. The electronics are pick and place later on. But you can have here a classic or a typical type of 3D where all the interconnects, the sensing electrodes are in place, as well as the RF antenna is fabricated, and then even contacts where to put a battery. In this particular case, is a biomedical type of device with a IoT, so it can be inserted into the body and transmit the signals of what is being monitored. So with this in place, let's understand the baseline difference between the traditional PCB, which is an analog process with lamination, and everybody's familiar with the multi-steps and the long cycle times it involves, to what is basically the multi-material additive manufacturing electronics, where basically it's a build-up traditionally from or most of the cases from the ground up, from no material into a full structure that could be equivalent to what you see in the PCB, but it's a solid single piece of dielectric with the levels of metal. And then being a digital process, and there is no lamination, no patterning, and you can decide to fill the vias or leave them as a plated through hole, but you don't need to do plating here. It's all filled already. And then more important is that because it's all digital, you can create vias on any shape, or actually eliminate the vias, as we will see some examples later on, and basically take advantage of reduced connection distance, increase IC density, improve RF signals, and more important also, or equally important, let's say, is that you can have any thickness of the conductive layer levels at any level, basically, because it's all digital and continuous manufacturing process. And this basically allows the flexibility of mixing and power lines as well as the signal lines on the same level, which is not possible with the PCB technology. So an example is here on the no vias is basically a 3D trace that goes from a level to level as a continuation and an angle. And the benefit of this, not only the fact that reduces the distance between the points to point contact, also basically increases the packing density, because now you don't need to have the rings that are required by the PCB manufacturing technology. So you can basically put the lines the traces closer to each other, increasing the packing density and reducing the net size of your chip. And we'll see some examples later on in some of the presentations. So with this, basically, what are the technologies that are used typically for AME fabrication? We have inkjet dispensers such as aerosol and leaf laser-induced forward transfer. Then each of them has its uniqueness and benefits and shortcomings, but the industry is moving to overcome equally all across the board. But basically, all together, one thing is common, that you start from a digital design in ECAD or the mechanical CAD, and combination of both, using the standards to basically create a digital file on pixels, and then you go into the dispensing unit, let's say in this case, either a aerosol or inkjet, and you create a printed layer based on those designs. You typically need to do a curing, drying, and sintering, depends if it's a dielectric or a conductive material, and then basically you go build up to the thickness that you need or the structure that you need. But as we said, basically, if you do multi-materials, you have a second nozzle or a second source of material that you can create even sequentially or in parallel simultaneous deposition, and then create the structures that you will be seeing during the presentation today. So in the case of the leaf technology, basically it uses typically a glass plate or a transparent carrier. It could be a flexible material, and then has the material of interest that has been pre-deposited there. And then the laser comes and melts that in that spot where the laser hits, and removes the material from the carrier, and then the material is deposited in the substrate. Typically, it's about 100 micron limitation, but some technologies are improving that to maybe 75 microns. And more important, also some of the solutions are using a laser trimming to reduce the trace width. So, but one of the things that is important is for the technology to evolve and be widely accepted in the industry as an overall solution are the requirements that they need to meet in order to go to down to 10 microns or even less, as to keep pace with the evolution of the semiconductor industry and the packaging there. And therefore, what technologies can do that? I think that we have seen some examples already in the industry with aerosol. And the question is, can it be done? And if we look at the inkjet, the traditional common statement in the industry is that below 50 microns, inkjet cannot do it. Then the lift, what I mentioned before, it might be able to do below 75 microns with the use of a laser trimming on the sides of the traces. Then the question is inkjet, for example, poised to evolve as optical lithography has done it for the semiconductor industry, which if we remember maybe 20, 25 years ago, people were saying below half a micron, you need to use electron beam lithography. But we know today how well still optical lithography is being used because basically the technology has evolved in the wavelength that is used there. So likewise, I think we're going to be seeing inkjet also evolving, especially with the electrodynamic printing, which basically takes inkjet into the next generation, where we see here lines and spaces of 2 microns examples, 25, and control a broad range of width traces on this technology. An example of that also is based on basically creating a MEMS type of multi-head system or multi-nozzle systems with where you apply certain batches and this is material that TechBlink enable us for presentation. So I think that as with the optical lithography in the semiconductor industry, inkjet will evolve as this technology matures and becomes commercially available into the capabilities of reaching the 1 micron range and continue the evolution of using AME all the way to the most advanced SiP technologies altogether. So the applications that that are covered, and we'll see many of these examples today, are packaging, electronics from 2D to 3D on conformal surfaces, biomedical, sensors, robotics, RF, millimeter wave, etc. And just briefly, you can see here a motor where on the right-hand side, which is basically the stator being formed with the coils there, and then the rotor with a couple of magnets placed in place, any shape, as well as traditional 2D electronics, biomedical applications from body sensing elements to eventually some controls and data management from the body itself and sampling these things through the sensors. But for example, one of the key issues is the biomedical compatibility. And this is the work that was recently done and courtesy of Professor Pliva from the Technical University of Liberec, where basically they develop using the multi-material technology from AME, nano-dimension in this particular case, a test for nanofibrous scaffolds where they put the cells and apply bias, and basically using the standards for testing, they confirm the biocompatibility of these materials for no interaction with the cells itself, which is what they needed, so they can apply the voltages and test the cells for what the studies that they were doing. So this is encouraging. Of course, this is short of going through an FDA approval and all those things, but this is at least an indication that the materials can be developed also to provide a solution in here, and we'll hear some more activities in that area in the presentations later on. See some other circuits and examples. We have embedded and side contacts and multiple contacts, or abilities to create a full integrated and shorten the distance, vertical integration of ICs, any shape, as mentioned before, capacitors. We'll hear some more data today, bandpass filters, part of the whole system, or for example, the antenna communication, the board that has been in the International Space Station was there for 11 months. Actually was returned already to NASA for a second tour of duty there. It was after 11 months, when it came back, was inspected and was intact. So it was sent back, an opportunity. Other millimeter wave from multi-level patch antennas to bandpass filters to basically phase arrays with quite unique structures that facilitate the beam shape creation on any shapes as desired by the application, as well as Fresnel lenses with multi-focus built into a single one, as shown here for 75 gigahertz and 120 gigahertz. Going forward, basically, the industry is starting to look into eliminating the via structures, the traditional way of interconnects, by creating shielded cables, twisted pairs, as shown in this particular picture, which is a triple twisted, doing point-to-point direct wiring with basically wires as opposed to traces and vias, which is the traditional way. And I think we're looking forward to the evolution of that technology that way. So in general, basically going from the 2.5D with integration and packaging, eventually we're going to see a 3D type of structures where basically have the controllers, the logic, memory, then the RF and the antennas all in a single structure and have a fully functional device. I think we'll see some of those things already today in different aspects of the implementations. And I will just leave you before introducing the next speaker, thinking about what this structure is. Is it an electronic device, or is it a chemical manufacturing? Maybe it's an ink manufacturing plant. We'll leave that for later on in the presentations today. So with this, it's my pleasure to introduce Gene Weiner, President of Weiner International Associates, who is going to talk to us about the impact of AME technology and other technical advances for manufacturing of electronic devices. And questions for what I just said will be only at the end of the day today during the wrap-up session. Thank you. Gene?
Good morning, everyone. Welcome to an exciting adventure, the start of the growth and expansion of 3D additive manufacturing for electronic packaging. Life used to be pretty simple when I was a young man. First, we had single-sided on phenolic triplet speed and two-sided islands, G10, plated through hose, flexible multi-layer HDI. Now the digital twin and three-dimension bidirectional database formats. There are new concepts of hybrid materials and packages to meet the demands for higher frequencies and power and speed. Those of us engaged in advanced packaging are now seeking new solutions for further miniaturization through ultra HDI circuits and 3D structures with components formed as an integral part of the build process. When I was a young man, Motorola took a great adventure and started building in layered multi-layers for the cell phone capacitors on a mezzanine layer. It was quite a complex process and pretty difficult to build. Today, with the advent of 3D additive manufacturing, you can make it as part of the build process going up. So what we have to do is we have to stop harvesting the remains of the past. We have to invest in the future. Think out of the box for fabrication and assembly and design, new materials, new semi-additive manufacturing, 3D fabrication and assembly processes where assembly can be part of the fabrication. And then we have to look at multi-level additive manufactured electronic parts. To this end today, we're going to preview several innovations that have already begun to contribute to future fabrication and packaging. The IEEE Packaging Society has identified additively manufactured electronics as an essential technology for its next heterogeneous integration roadmap. 3D electronics enables greater integration of components. It's time to consider electronic packages as structures instead of just PCB assemblies and layers. New standards are needed to meet new processes equipment. For example, ANSI's new spec on the future equipment sintering temperature uniformity measurement for photonic sintering systems is important for two reasons. One, it is used for low temperature, low power soldering of even SAC alloys, SAC alloys, where substrates are temperature sensitive. And the second, with additive manufacturing and the use of silver and other inks, we have to sinter the material to make them conductive and remove the carrier. The AME Academy, working with companies such as Nano Dimension, PulseForge, and others, has already begun working on standards for this adventure. Now, with algorithmic engineering and AI, artificial intelligence, coupled with 3D additive manufacturing for design and manufacture of electronic packages. Will this succeed? What advances are being made to further advance SAP processes to meet the needs of HDI and ultra HDI designs? Let's look at some of the activities today. What changes already on the horizon? What's new in advanced packages and structures? Let's look at a few new approaches in semi-additive manufacturing first. Now, this came to us from methods for PCB-like interposer structures from Joe Dixon of Loose Printed Circuit, who has developed a number of semi-additive HDI builds and encapsulations for a build-up for a new procedure to work for interposer-like structures, for organic interposers. And the list, and this is available, and I'm not going to read it all to you, when you look at this and when you review it, the current PCB process, standard modified semi-additive process, and the new carrier additive process, which is the development of loose printed circuits and others. Information that will be widely available upon request. Now, what they do is they show the conventional HDI buildup as in thin foils with a subtractive process, as our friend Denny Fritz, chairman of the IPC's Hall of Fame Council, likes to say, the semi-additive process is really a semi-subtractive process. And here we're comparing the pros and the cons of HDI buildup with a carrier embedded additive process with conventional buildup. The big favorable thing for the new buildup for the carrier is you can have a thicker interposer capability with a larger panel size. You get better impedance matching of signals to the dielectrics, some of the core type structures. You have high resolution because there's no etching of line space. So, as you saw earlier in Hein Millman's presentation, can now go below 60 microns, which is even with copper traces. We can use traditional prepregs and glass for this, and can be processed with traditional equipment. Now, thinner dielectrics are available in the future. Here's a cross-section of a carrier additive panel HDI process, very high density substrate of a panel interposer, and it shows the process stages and planarization and frame dimension top view. Now, again, we're comparing embedded additive HDI with subtractive HDI, the aspect ratios that are capable of better. The original glass ratios are lowest with the new embedded carrier, and the dimple effect is virtually reduced to very little due to lower volume copper needed to fill vias. Additional interconnect technology for these carriers are the VECS, PCB and interposer connections from a 0.4 millimeter pitch and above, and a UVECS for interposer connection below the 0.4 millimeter. And here's the methods for producing the PCB-like interposer structures. You can look at these later, but it's been proven and it's well accepted how they're developed. And then it shows the different interposers with and without glass. And from there, we're going to move on to conventional semi-additive processing. Now, semi-additive processing was really initiated in Japan, moved from there into Taiwan, and then into China in volume, where most of the high-density interconnect boards are produced. Then there was a new development by a company in California called Veritech, with the manufacture or capability of liquid metal ink as a substrate for a true semi-additive process. Very thin, few nanometers that can be used with palladium, gold, and a variety of other metals, and it has broad applications. It's already been tested by a number of companies, and as you will see, is already in production. Now, this is the system. You have a substrate, you coat it with the liquid ink, you put an electroless copper down, and by the way, Aditech in Germany has developed a new special electroless copper designed for semi-additive processing. Then you image it, expose it, develop it, electroplate copper, and once again, Aditech, McDermott, and others have developed special new coppers for buildup for this type of circuitry. It's strip your photoresist flash, etch the base electrous copper, which was put onto the substrate. Now, a very thin copper base is fundamental for fine patterns to avoid undercut. And the ASEP process, the Veritech semi-additive process, provides a 0.2 micron base of copper for the plating, where the standard modified semi-additive etched down is 5 microns, as are the super thin copper foils available from most of the Japanese suppliers. And what's the end result? Dramatic size and weight reduction, improved reliability, radio frequency performance, signal integrity, lower cost, and there are some biocompatibility capabilities. Now, Crane Laboratories under the U.S. Department of Navy has evaluated the process, and this is showing the improvement they've been able to get in resolution down to 12.5 micron line in space, and these parts were produced at Crane Laboratory. There's a circuit density improvement, which spaces trace space and minimum feature size. It is reduced from 75 down to 19 microns on a BGA grid. Now, micro BGAs are coming more and more into use, and we're seeing more and more need for smaller grids, ability to solder to them and match them up. The backup one here is another example. Copper traces on this one. This is manufactured in Santa Clara with 11 micron lines and spaces, 13 microns, 17 micron spacing. The company claims that submicron traces could be produced, but I don't know if I'd want to try it in production today. One of the advantages of semi-additive processing is you get great signal integrity because of the modern photoresist, the dry film photoresist now can give you straight sidewalls on the plate up and narrow spacing for improved conductive and capacitive coupling. And this allows for very thin dielectrics. Here's an example of 20 micron space of 50 micron pitch with a square cross section with a 0.2 micron base copper conductive layer. And here's a shot produced in Greater Chicago by American Standard Circuits using this technique. This is done in their prototype shot. They're now doing it in production. Now, one of the military companies in Canada, we also an operation in California, is Furon Technology, FTG Corporation. And they're also working with the ASAP process, and they're producing 1 line in space after plating with copper thicknesses up to, as shown there. This was produced in their factory in the Midwest. 1 line in space after plating copper thicknesses up to 20 microns in tenths of a mil. And here's a board produced that way. And here's another one produced. This is a 6-layer build-up design. Again, this is 2 line in space on that. And reliability coupon designs, which are matched for the conventional standards that were developed for wider spaces and developed by the IPC standards. Thermal stress testing, and also for CAT, for testing, CAT testing. Then Calumet Electronics in Northern Michigan, way up in the north. I think they're the northernmost printed circuit shop in the world, if not the United States. They are producing organic substrates for flip chips. They're doing various additive manufacturings. They're doing complex HDI PCBs, and they're also working with the Veritech system to produce such parts as you see in this photo. Now, advanced additive manufacturing and IC substrates at Calumet takes many forms, everything from the semi-additive to working with IC substrates and flip chips, and they're right now doing 10 micron plater lines in spaces with the ASAP process. Now, in Switzerland, headquartered in Switzerland, is a company called Secor. They're active in many areas of packaging. They do thin film work, they do lattice copper, they do various semi-additive processes where it's developing systems for 25 micron lines and spaces. They ran a webinar just a few weeks ago, which I watched, the development of 10 micron technology in cooperation with the thin film technology, where they sputtered an adhesion promoter, which turned out to be titanium, followed by imaging copper plating, and then etching away exposed copper. They also use aerosol jet 3D printing, as you may have seen in the first introductory presentation. Aerosol jet is one of the techniques used for additive manufacturing. They're using aerosol jet, and they've just ordered another machine to be installed in one of their Asian facilities for aerosol jet printing. This is my famous die. You can't lose when you toss that. This is a molded part where the conductors were applied by aerosol jet in 3 dimensions. Now, I mentioned Additive and a new generation of electroless copper semi-additive buildup. This is it. It's called Printer Dance. It was just introduced this past month in July, late June. It has excellent drawing power, it covers critical areas, and it has advanced micro roughness of dry film adhesion so that you don't get undercut etching. You can get a straight foot on the cross section of your buildup layer. It's designed specifically for semi-additive production. It's great throwing power, and it has a good loading factor. Sometimes when you load electroscopics too heavily, it loses its balance, stabilizes, break down, and the bath falls apart. One of the challenges by the shrinking size of components we're all familiar with, and most of us use the SanDisk for something or other, 3D additive manufacturing may be a solution to the next generation of parts such as the SanDisk SSD. Now, one of the problems in making very fine pitch patterns for ball grid arrays is applying solder or solder paste uniformly to different designs with narrow spacing and on a part, and without reformulating the formulas for deposition thicknesses, types, or whatever, and their different applications. One of the additive methods that was mentioned is a laser deposit where you can control the flexibility and apply drops to tight pads at a very high speed. These slides were provided to us by another Israeli company from the Tel Aviv area called IoTech, and they've developed a technology for applying solder paste with resolutions down to 60 microns for multiple component designs, including large and small components. They can actually print the solder paste on components, and they can put down 5 million drops an hour. They stay. Here's an example of the solder paste deposition. They can deal with multiple component size and design on the same passes. It's small pads, large pads. They have a consistent height to width ratio, and activity in the field of 3D manufacturing is gaining momentum with the increase of cooperative alliances emerges that bring many new technologies to the already matured segments of advanced manufacturing to the table of additive manufacturing. Now, what do we say by matured segments? Well, GE, a number of years ago, developed an additive manufacturing process for 17 jet engine parts, got them approved by the FAA, and they're now in use. There's a company, a relatively new company called Hyperganic, using artificial intelligence and computer algorithms to design 3D rocket engines and other parts heretofore that could not be done. I'm going to show a photo that shows the space rocket engine spike designed and printed to their technology, their Hyperganic core, and the detailed combustion changes it produced can only be created by AI software, and they were designed to ensure that the rocket spike doesn't overheat. Take a look, that's built by 3D production, additive production, layer by layer. It's rocket nozzle. An amazing piece. Another example of dealing with great details in the industry, when we're talking about miniature parts and microprocessing and close spacing, there's a company called Admatech and Formatech that created metal and ceramic additive manufacturing portfolio with multi-grade industry 3D printing systems with an array of parts for medical, jewelry, industrial, and investment casting, and hopefully combining them with the technology for the companies such as Nano Dimension, we could bring more materials to the game. When we looked at the rocket system before and other manufacturing techniques by additive printing, you're generally dealing with a single component, a metal, a ceramic, or a plastic, but not, sometimes with a fiber filler, but not multi-materials at the same time for the same part. This is one of the innovations of that we're seeing now, is they're bringing together the different materials into single systems. Now, information of this is widely spread, and Nanotech, who's one of the hosts of this meeting, has now partnered with James to build the first online community for additively manufacturing electronics and other parts. And they're providing a stable software system where you can find other people with like desires and needs and inventions, and make it functional for the whole industry while setting the standard in electronic device production. So they are now a partner of Nano and AME, and you can gain access to the largest collection of processes and designs and know-how in one place through James, and leverage it and use it and develop some synergies with novel insights and fresh perspectives from the different advances already made by others. Now, their portfolio will talk about the ability to 3D print the drone structure in a single print, such as shown here, a radio frequency synthesizer, and an NFC coin, which I think might be a curious thing to have. Now, AME development in the future. This is an emerging, additively manufactured electronics is an emerging technology. Can only be taken to the next technical readiness level if we're able to combine different processes, different materials, and different design methods. We can already are doing fabricated capacitors and coils, as we saw earlier. We have commercial capacitors, we have AME capacitors, and this shows a better performance on that. Weight and size reduction. Electric motor control board transferred from a printed circuit board to an additively manufactured electronic device, and then further reduced in size as we progress from there. And we can also, in the AME additively manufactured system, have raised and recessed walls, open spaces. You don't have to mill out an open space. It's designed in. You don't have to raise a wall or laminate or plate something on there. You can just build it as part of it, as part of the system design. There's another shot there. Now here's a PLL board that was designed by Hensel and redesigned for AME, and it got a new condensed secure solution that was available in the traditional society. You can see the stacked solution. Now, I talked about embedded resistors. One of the newer things I look forward to with some of the precision capabilities of the micro printing of components is embedded resistors. We talked about embedded capacitors, but no one has spoken about embedded resistors. They've been buying, people have been buying Omega ply and etching it down, which has a resistive layer there and etching the pattern in. I believe that we can make precision resistors by additively manufactured electronics going forward. So we have a precision component resistor and film capacitor. I also envision a photoetch components that think of the Fabrica 2.0 microprinter by Nano Dimension with a resolution down to less than 2 microns and 1 micron tolerances. This is something new that people should be looking at for some of the finer designs. Now, the following companies contributed materials to this presentation, and each of them has a place in the industry. Additive is a major printing supplier. Veritech is very innovative for a new semi-additive thing. Calumet Electronics is trying many new things, one of North America's leaders. Secor, a global operation which is trying new things from China to Switzerland. Foreign Technology Group, Canada. Hyperganic, which is ranging from Germany, from Munich to Singapore with their operations. They're now getting involved with the semiconductor industry with new designs and things there. James, which is providing a new platform for interconnect and getting together with other people. Nano Dimension, of course, and Wu's Printed Circuits. Now, Wu's Printed Circuits is an unusual company. They started as a small printed circuit company in the south of Taiwan, using materials and things imported from the West, and then they started developing their own techniques, moved into a major plant in China, expanded there, then started hiring a number of American engineers who have moved up in the organization. The current officers are educated at Berkeley, California, and they're running quite an operation. Now, there are a number of questions. I don't know how we want to handle these. Are they coming
You're
up?
done?
Pardon?
You're done?
I'm done, unless there are questions.
Okay.
on that. Okay. Good.
Thank you, Jean. Any questions from the audience in the online? Just one question that I see here. Which, from all the areas that you cover, which one do you think is the most prominent evolving in the market from the applications, the verticals?
Most prominent?
Yeah.
The most prominent ones are in Taiwan and China.
No, but it's from the applications, the verticals, not the companies. I mean, between the RF, between the
Covered prominent or future?
future.
Future, I see a combination of hybrid applications using different additive manufacturing techniques coupled with some of the conventional things. For example, you may take a modified multi-layer board and to it add capacitance layers, antennas, and then put another insulating coating on it and putting down some other components. And I see a hybrid future for many applications. I see niche markets for total additive. And I see, they say when printed circuits came out, wire was going to vanish. How many miles of wire are still used today? I see the same thing. The space for all, each has to find its niche. And we have to go through adolescence now and additively manufactured electronics.
Okay. Thank you, Jane. If we don't have any more questions, and thank you for your smiling display here. This is great insights into the industry altogether. And although we are 10 minutes ahead of time, I know that the next speaker has probably more slides that we can cover in a couple of hours, but so I will give him the extra 10 minutes now. So with this, I would like to introduce Professor Paulo Gurta from Florida International University, who was formerly with Georgia Tech with the packaging group there. And he's going to talk to us about the impact of AME on packaging.
Good morning. Can you hear me?
Yes, we can. Perfect.
Thank you. I'd like to share my screen if it's okay. So my talk is on AME impact on packaging. And what Chaim mentioned, I'm from Florida International University, and I'm really excited to be here. And thank you all for having us here to present our focus in how AME can impact future packaging technologies, particularly focusing on variety of product segments. And my slides also have contributions from other people like Yahya, who is on the agenda, Melanie, who is on the agenda later, John Volakis, and Satish Venkatkrishnan. So basically, I like to highlight this pervasive role of AME in packaging. So we have it in computing applications, in power modules, 5G millimeter wave packaging, analog and sensor integration with embedding actives and passives and the wireless communication. So the big part of today's agenda is dedicated to the 5G millimeter wave packaging. So while I have a few slides on that, I will focus on also the first two items where there is slightly less focus today. And I'll briefly also talk about the wireless sensor technologies, even though we have two complete presentations later on from the team at FIU. So I created this snapshot of heterogeneous integration customized to different product segments. So if you can think of them as computing, communication, and sensor integration for maybe health monitoring, IoT, and other things, each of it has its own product architecture based on the system metrics or the system performance targets. For example, computing is all about high bandwidth between logic and memory with very, very fine line interconnects between the active devices, logic memory devices. And while doing this, you need to deliver power to maintain this voltage at the transistors within these particular noise margins. So it's about, again, very high density interconnects, almost approaching microns, and but then delivering power with all these other power delivery, analog and storage components. In communication, it's about all these impedance matched interfaces between active devices, new multi-layer designs to improve the bandwidth and the gain of these antenna arrays to achieve this communication between different subsystems, keeping in mind that at the millimeter wave, you have all these path losses that you need to address with high directivity. So here again, it's all about the transceiver integration with antenna on the surface using the so-called antenna in package. Sensor integration is about embedding actives and passives in a flex substrate and then integrating them with the sensor interfaces coupled with the external environment. So if you look at these three product segments and you look at the latest technological innovations that will play a role, you can see where AME can have a big impact in achieving these conductors, 3D multi-layered architectures with advanced conductors for low signal loss, maybe even creating new multi-layered conductors, advanced dielectrics, and these high impedance surfaces or frequency selective surfaces, thin film power sources, power components, particularly batteries, supercapacitors, decoupling capacitors, new seamless interconnections between different subsystems, between for example, the antenna and the feeding package or the feed board, and how to achieve these very fine pad-to-pad interconnections, perhaps with new bonding architectures, encapsulants, barriers, hermetic coatings, and advanced conductor materials, thermal management materials between different active devices and the external heat rejection system, how to achieve this low thermal impedance, and also embedding these sensors and the electrodes. So you can see basically, if you look at all these building blocks, AME can play a role in enabling almost all of them. So I call it the pervasive role of AME in future packaging. The packaging technologies will still benefit from all this very fine line panel manufacturing techniques using semi-additive patterning, like what was mentioned previously in the earlier talk, and lithographically patterned techniques. They scale down to submicron, and they scale down to very precise impedance matched architectures with even less than 10 microns for RF, submicron for digital. And so those are going to prevail, but then there are many building blocks where additive manufacturing can provide scalable solutions. So this hybrid technologies is where I think the world will tend to, with typical panel manufacturing or even wafer fan out packaging taking care of the very high density interconnects, and additive manufacturing providing certain components and in certain cases, additive manufacturing can replace the whole system altogether because of its very unique manufacturing and design enhancement. But if you look at the traditional wafer fan out or panel embedding, panel fan out manufacturing, it's all about 3D heterogeneous integration with embedding actives and passives. So the idea is to reduce the interconnect length from say millimeters to less than maybe 100 microns to less than even 10 microns eventually with embedded devices. And so the idea is to migrate this 2D side-by-side modules with 3D modules and to enhance the component density and performance while at the same time reducing the interconnect length. So this embedding of active devices has been happening and that will drive a lot of future heterogeneous integration, either embedding in the panel using panel fan out embedding or embedding with wafer fan out. Either way, I think active embedding has to go with packaging advances because ultimately the active devices have to couple with the system interconnects and the passive components to get the true system benefits. So without bringing active devices into the package, you cannot really realize future systems. And then the next thing is about passive integration. Even the passive components embedding started a little bit before mainstream active embedding. Active embedding took over and still passive embedding, particularly for power components, is still lagging. But with the latest high density passives, even passive embedding is coming in for power integration. In the RF integration, obviously, passive component embedding has been mainstream for all these matching networks and filters and even all the power dividing networks and so on. So passive embedding will go with active embedding to realize the future heterogeneous integration. And so along with that, once you bring all this, you need to realize the thermal structures, double side cooling, for example, and or single side cooling, depending on your product and its system metrics. And while this is happening with panel embedding and 2D substrate migrating to 3D substrates, this will also happen with discrete modules that are typically in analog world. People still worry about lead frame integration of actives and passives because of its very scalable infrastructure with low cost manufacturing. So in this case, you still take a lead frame and you mount the devices, and now can you then replace all these wire bonds with embedding and printed or fan out embedding of devices, integrating actives and passives within this lead frame package so that your customer can now mount this module without worrying about additional bill of materials, and you can address the whole system functionality within this package, taking both the, for example, the GAN, the wide band gap switch, the controller, the CMOS controllers, for example, certain passive components, and so that you can integrate this whole module. And so why hasn't this happened already? Because and that the reason is because it brings in a lot of thermomechanical issues, supply chain readiness for all these thin film components, and the market pull, so that you can realize this highly embedded integrated 3D active passive integration with low thermal resistance, reduced parasitic inductances between the components, and you can integrate the whole functions like gate drivers, isolation, sensors. And so as you migrate these topologies to advanced power module integration, you will realize that this kind of active passive integration becomes more important, particularly with this multi-level and multi-phase conversion, where you need a lot more passives, a lot more active passive integration. and bringing in wide band gap with traditional CMOS. So now with that background, let's see how can AME play a role in different product segments, like what I said. So let's start with high bandwidth computing. And in the computing, the logic memory bandwidth is realized with high density interconnects that is typically done with wafer fan out packaging, or recently with glass fan out. There is a lot of drive towards glass fan out packaging. And of course, the mainstream silicon interposers, high density silicon interposers. So we're not worrying about the interconnect bandwidth or the high interconnect densities. Those are going to be lithographically defined for submicron to almost a micron kind of spaces. But where I think there is still a big opportunity is in power delivery. How do you deliver power from the board to the package, bringing in high density storage components like inductors and capacitors to deliver seamless, clean power to the active devices. So traditionally, this power conversion used to be at different stages using board level voltage regulator modules, and then doing power conversion in the package, and then a lot of decoupling caps in the package and on chip. But with the future, the packaging power conversion is migrating into the package. So you'll have a lot more power converters within the package close to the chip, with the components distributed between the package and the chip. And the components, I mean the active and passive components like inductors and capacitors, and also the switches and controllers. So basically, the voltage regulation now will migrate more and more closer to the chip, but there is no real estate there. So you need to integrate very high density inductors and capacitors in the package to realize this power conversion, whatever topology you choose, whether it is a switching regulator for high current or switch capacitor networks or the hybrid topologies. You will need a lot of passive components to convert this say a 12 volt or a 48 volt line coming into the package to less than 1 volt, like almost 0.6 to 0.8 volt in the chip. So you will realize this voltage conversion with this passive integration. And so while the signal bandwidth is achieved with panel fan out and wafer fan out and silicon interposers and so on, which I'm only showing the typical laminate embedding, more like panel fan out. The more mainstream today for mobile computing is wafer fan out, whereas for high performance servers and GPUs, it's all about silicon interposers, high density silicon interposers. But either way, you will need a lot of embedding of these passive components for power, embedding inductors, capacitors, and so on. And those component technologies will benefit from additive manufacturing, because you need to realize high surface area electrodes with very, very conformal dielectrics. So these high surface area electrodes require new architectures. Similarly, inductors will need new magnetic composites that need to be integrated with the package in very, very thin form factors. Like you need to have now inductors within 25 micron thickness, capacitors again within 25 micron. So that requires new nano electrode architectures with conformal dielectrics. And these nano electrode architectures can be realized with additive manufacturing. So you can create this high surface area electrodes, then followed by other kind of approaches to realize the dielectrics and the counter electrodes, so that you can have this power delivery. And one thing we are doing is basically to have this cold sprayed aluminum capacitors on copper to realize this high density passives. So aluminum is a very great material for making high density capacitors, because it forms a very natural oxide that is of the best quality in insulation strength and decent permittivity. But aluminum integration into the package is not easy. People use aluminum foils, and they're only used for board level. But if you actually do aluminum cold sprayed additively manufactured capacitors, there is very strong opportunity to realize additively manufactured passive components, not only for computing, but also for high power modules in automotive and other high power applications. So either way, I think additive manufacturing has a role in aluminum capacitors, maybe even migrating to tantalum caps for higher permittivity. So we started realizing these aluminum cold spread capacitors on copper and achieved very good densities now that can be realized in very thin form factors and integrated both into package high density lead frame packages like what I showed for power modules, eventually maybe in high density computing and definitely in high power packaging that I will cover in the subsequent section. But if you go towards magnetic integration, again, a lot of components, a lot of power converter topologies depend on switching regulators where you need magnetics. And magnetic materials are realized with more metastable architectures like nano-amorphous or nanostructured alloys that are typically not easy to realize with traditional fabrication techniques. If you look at sputtering techniques, they are too expensive to realize enough magnetic material for high power handling. Plated magnetics has its limitations. It will run into eddy current losses. But if you actually cold spray, again, we have a big program in cold sprayed additive manufacturing. So I'm trying to use that opportunity. If you cold spray nanomagnetic or amorphous magnetic films, you can realize extremely high performance magnetic materials. They can go to higher frequencies. You can scale the thicknesses to tens of microns, not just 2 microns and 4 microns like sputtered films. You can realize inductors with additive manufacturing. You don't need to realize cold spray. You can even use typical composite additive manufacturing like using inkjet printing and so on. And you can realize magnetic core along with the conductors, inkjet printed conductor silver core to realize power components. So you can achieve high density inductors with high saturation current to overcome the limitations of sputter deposition and plating. So basically the opportunity is, can you get rid of the low performance plated magnetic films or magnetic flakes or sputtered magnetic films by additively manufacturing new metastable architectures. And these cannot be typically manufactured with more, stable processes, thermodynamically stable processes, like, where you are limited to certain material architectures. You need to create a metastable architecture. For example, you have to realize a iron cobalt alloy with a very thin passivation that is at a nanoscale, maybe in a matrix of a nickel zinc ferrite. To get this ideal material combination using traditional processing, thermal processing, you will not realize because the thermodynamically the system goes to some other architecture. It won't come to the architecture that you want to realize for your best properties. So some kind of cold spray technologies has a good opportunity. Even without cold sprayed, if you just print this nano composites, ferrite inductors with 3D printing, you have good opportunities when you seamlessly integrate with copper or aluminum bus bars to make these 3D power modules. So 3D integration of passive components is my first part of my where AME has an impact on packaging. If you go to power module packaging, again, this is a very different product segment. It's about delivering power for automotive power modules, high power modules, even delivering power for other, product segments, particularly maybe in data centers and other where you need maybe kilowatts of power to maybe even hundreds of watts. So in that case, again, there are opportunities to realize these high density architectures with additive manufacturing. Traditionally, the technology's evolution is shown here. You will have this PCB with high density embedding magnetics, like what I talked about before, plated magnetics, on-chip integration of certain thin film magnetics, and then 3D packaging of these wide bandgap devices with these passive components. Now, along with thermal management, you want to realize this goal of almost getting to 1000 watt per inch cube kind of numbers. But as systems go towards higher frequencies, you need more lower electrical parasitics and higher power densities are always required with more integration and single package integration of all the active and passive devices. So the idea is, where can additive manufacturing play a role? So I use this slide from ORNL where additive manufacturing can play a role in miniaturizing passive components, like just what I talked before, the DC link capacitors, the integration of system components with bus bars, integrating sensors, and more importantly, integrating the thermal management structures while you also bring in other functions. So can you realize additive manufacturing with thermal management and passive components with the power delivery bus bars and create very compact 3D power modules? And that is my second part of my presentation, where we want to realize highly integrated 3D power packages with benefiting from additive manufacturing wherever it makes sense. We don't have to force additive manufacturing into architectures where it cannot compete with traditional lithographic patterning and lithographic fan out interconnections or high density, high bandwidth connections. Those guys will prevail. But where additive manufacturing will play a role is something that needs to be understood and captured, so that the hybrid system technologies provide the best solutions. One way is, for example, you have all these bus bars, and they are typical aluminum bus bars, and integrating components on this seamlessly has been a problem. But recently, for example, Amphenol realized cold sprayed copper on aluminum bus bars, and now you can mount your devices directly on the copper, and you can realize 3D power packages. Just one example. And so traditional power modules are basically, you use this direct bonded copper, aluminum nitride, for example, alumina with direct bonded copper. You have your IGBT or now wide bandgap devices, wire bonded. And then you have the ALSIC base plate, and then the cooling system. The whole thing is molded in a silicone gel and with the connection bus bars. Now, how do you get rid of all these packaging architectures? And how do you get rid of these packaging architectures? The current prevailing technology that's going to stay forever, and at least for a long time, is basically fan out embedding of gallium nitride in a laminate, where you then form these interconnections, direct copper interconnections between the embedded gallium nitride chip. Now you can have a double side cooling if you want. You can realize very high density heat transfer thermal management with heat transfer coefficients exceeding 50,000 watt per meter square Kelvin. But now, what about the passive components? What about the thermal management structures? And what about the other logic devices, controllers and drivers to get the lowest parasitics? So then these are mounted on the top with these 3D architectures. Passive components now can be integrated directly with these copper planes. And so you need to realize very high density thin film capacitors and inductors. You need magnetics, basically transformers, and then seamlessly integrate the thermal management structures with this. And that's where, again, additive manufacturing has a role. For example, how to achieve high density thermal cooling in a thermal management system. And then opportunities to have the die attach on the backside with nano copper or nano silver. Then this, instead of using galvanic, plated copper, can we realize this with printed copper, because nano copper paste is getting to be more prevalent, similar to nano silver. So how do you realize this fan out interconnects with very low parasitics, high current handling, and the lowest resistances to the gate drivers. How to realize them with sintered copper interconnections between the devices, and also provide this very high performance encapsulations. So basically this 3D power packaging will again benefit from additive manufacturing, bringing in all these technologies for encapsulation, power, thermal management, capacitors. And one thing again I come back to is these capacitors that are really bulky and big, and they are a very integral part of any power management. And how to realize them with this, whatever I showed before, the cold sprayed aluminum capacitors, and so that you can get extremely high densities of power densities with these caps. And now how to realize thermal management, again, that's again a big area. So you can have now this die attach, and then to a copper cold plate with this vapor phase cooling systems to get to very high heat transfer coefficients. So eliminate the thermal interface impedance by directly printing this cold plate with a very hierarchical porosity, so that you can minimize the localized hotspots and create appropriate 3D architectures, so that you can get the best thermal gradient management, and at the same time benefit from this localized vapor pathways. So if you look at it, typically the cold plate is quite far away from the die, the DBC, the copper plate. And now if you can integrate them with additive manufacturing to realize this high density thermal management, then you can basically benefit from this 3D power packaging. So what is the benefit of integrating wide bandgap devices with passives and so on if your thermal management system eventually creates a very big bulky system? So the idea is to even realize this very integrated 3D power management. So you can see the benefit of it in the this high density 3D packages, particularly in automotive world. How to integrate this thermal management with the rest of the 3D power packages. So that is my second part of the impact of additive manufacturing in advanced power packaging. Now let's go to the next part, the 5G millimeter wave packaging. Today we have very exciting presentations, so I will barely highlight some of the key aspects. So millimeter wave packaging and additive manufacturing role. So if you look at the key elements, you need advanced designs, active and passive beam steering and beam forming, ultra wideband antennas, reconfigurable intelligent surfaces, high-K superstrates to form these lenses and isolation and so on. And then that brings in new materials, dielectrics, low loss dielectrics, multiferroics, new terahertz detectors and sources. Now we're bringing in new liquid dielectrics, liquid conductors to bring in these new functions. Obviously, everything goes with chiplet integration. If active devices are not seamlessly connected with the passives and the interconnects, then you only realize very limited performance with your packaging. So packaging has to go hand in hand with chiplet integration, embedding actives, using new device assembly techniques. For example, massive parallel device assembly techniques that are typically used in display technologies today. New pad-to-pad bonding with interconnection heights of less than 30 microns. And the whole thing coming together with 3D heterogeneous integration of analog, RF, even digital in the same package, photonics and sensors, and high density, low loss transmission lines, 3D seamless interconnects. So basically that all brings in this 3D millimeter wave packaging. So there are again different ways to realize. You can build the whole package with additive manufacturing, like the way Nano Dimension has been pioneering, and also companies like Unscript. So, or you can benefit from some kind of a hybrid manufacturing where you take flex substrates and you start printing certain conductors and dielectrics using inkjet printing and a combination of other additive manufacturing techniques like aerosol jet printing. But eventually you need to bring active devices with either RAM connections or inside a cavity with that planar connections, like the way we like to do in FIU, and then mount these superstrates and other functional layers on the top to increase the gain and bandwidth. So this is again a very rich design space where additive manufacturing is getting a lot of traction, a lot of great examples from Nano Dimension and its partners that I think Chaim already showed, that I will also briefly highlight. So the mainstream technologies will always benefit from high density interconnects and precision impedance matched architectures. For example, if you look at the typical millimeter wave packaging, it will be mostly multi-layered laminates with embedding or backside assembled transceiver chips with, again, heatsink, thermal management, and multi-layered stacked patch antennas typically to achieve the bandwidth and gain. And then for more user equipment, like for example, laminates again with stacked patch, backside transceiver assembly, and you can realize this organic laminates like the way Qualcomm has been using for its latest 5G smartphones from Apple and Samsung. So this will have again the multi-layered laminate because it's a very ripe, mature technology to realize multi-layered precision copper architectures. And so it will go on. And the idea is, where is the role of AME to take some advantage, and particularly for certain product segments where you have new design opportunities that really are only realizable with AME. Additive manufacturing is where the opportunity lies. But other than, but if you look at non-laminate based, the wafer fan-out packaging is again the more prevalent way to realize this, because now you can take the devices, reconstitute them in a epoxy molding compound, create the fan-out interconnections, then form the antenna and all the power dividing networks on the top of the embedded wafer fan-out packaging, using all the wafer foundries. So TSMC, you would think that a semiconductor device company would never invest thousands of packaging engineers and build factories in packaging. Actually did that in the last few years, where you now make the devices are reconstituted into a package with molded compound. And then once you do that, it's a reconstituted wafer. You can now use typical semiconductor back-end of the line processors, and you can achieve the best geometries with very vertical interconnects, stacked architectures with very precision impedance to get your antenna in package in the wafer fan-out package. So the benefits are thickness reduction, low signal loss from chip to antenna. But then again, wafer fan-out is always, in some sense limited with unbalanced stack-up. So there are some constraints, and the molding compound is the reconstituted dielectric that is embedding all the devices. So the molding compound has its limitations. So, but still, I think the molding compound, if you ask them, they will say that, yeah, the molding compounds today they have pushing their suppliers from Japan, they can realize even 0.004, 003 loss tangent, 005. So they say that, yeah, we can get as good as the best of the best laminate materials. So, if the market pull is there and the infrastructure and the design opportunity is there, people will always push the material suppliers to, get to the required product line. You would not think that molding compounds will have loss tangents of 0.005 few years back, but now they have 0.005 and less. So anyway, with that, now you can realize this antenna in package, a lot of applications from Infineon for automotive radar, and also other OSATs to realize this fan-out packaging. Now, if you look at 3D printing, again, where can it play a role? Obviously, it's in certain design innovations that typically cannot be realized with wafer fan-out or multi-layer laminates, or where you want to integrate multiple components with 3D architectures that cannot be realized in this planar wafer fan-out and organic laminate technologies. There are a lot of opportunities. If you look at the IEEE heterogeneous integration roadmap written by Hewlett-Packard HP folk, basically you can have this FDM in the multi-jet deposition techniques. Now they are also seamlessly integrated with active devices, obviously limited by its design rules because of this these additive manufacturing techniques. But you can realize very new 3D product architectures, and the leaders of obviously we know Nano Dimension realizing this several 3D product 3D architectures for high bandwidth antennas with this stacked interconnections, phase array dual beam metasurface antennas like what Haim just showed, and also benefiting from this a combination of flex and additive manufacturing to get the benefit from the dielectric base, the flex, and on the top of it you inkjet print the conductors now with very innovative ways of creating encapsulation, smart encapsulation, and embedding devices with this printed interconnects so that you eliminate the wire bond, and realizing this multi-layer architectures with even printed polymers. So basically, these technologies will have its role in particularly realizing rapid prototyping and accelerated design cycles to come up with new product innovations with shorter design evaluation cycles and faster prototyping, eventually realizing the products. And so one avenue in this area is basically how to eliminate the some of these package parasitics, BGA. In a typical 3D package integration, you have this antenna array and then you have a high density feed board, for example, if you don't have the luxury of integrating the feed lines directly in the package. And then you have this BGA that is creating losses that are becoming a bottleneck for millimeter wave and terahertz interconnects. So one avenue for additive manufacturing is seamlessly integrating this ultra-wideband antenna with the feed lines using this multi-layered architecture. So we have this BGA assembly eliminated with the 3D printed multi-layered architecture, so we can eliminate some bottlenecks. And also, once you have this additive manufacturing, you can bring in variety of new materials that are not easily amenable for typical multi-layered packages. For example, if you want to achieve reconfigurability with all these intelligent surfaces, you need to bring in a new class of materials. And that is not realized with typical wafer fan-out packaging or multi-layered laminate substrates. So in that case, obviously, you have to bring in new materials, particularly multiferroic materials or smart materials. And like what I mentioned, for example, certain reconfigurability is achieved with resistive inks to achieve higher bandwidth and gain, and also liquid metals to achieve reconfigurability. So there are all these innovative innovation opportunities to realize reconfigurable intelligent surfaces. And for example, using new nanocomposites to tune permittivity with electro rheology concepts. Can you move particles around in a liquid so that you can achieve tuning in a very miniaturized way, not the way people realize FSS today with very bulky structures or reconfiguring with very bulky structures, but in a very miniaturized, compact way. Can you realize with new nanocomposites, multiferroics, liquid metal in very thin form factors? And that's where I think additive manufacturing can seamlessly bring in these new materials, because there is no limit to bringing new materials. And I think we have some talk later in the afternoon from University of Massachusetts on bringing new materials. So, and also one opportunity is again with this super straights and also the resistive R cards between the antenna and the ground plane. So if you want to introduce R cards with high resistive materials, again, there is an opportunity to bring in with the additive manufacturing techniques to kill the the surface waves and prevent and achieve coherence between the reflected wave, and so we can achieve higher gain. So this resistive FSS, for example, or the smart FSS for reconfigurability and so on, brings in a lot of new opportunities for additive manufacturing. And we have a few examples, I believe, that we'll also hear today during the rest of the session. And as you go towards terahertz 6G, you will also bring in a lot more new materials, for example, plasmonic materials and reconfigurable terahertz antenna arrays and so on. So even here, I think you can bring in new material opportunities. What goes against AME is the scale. These are all now going towards less than 10 microns. But the opportunity is to bring in a lot of variety of materials. So I will try to come to the last part, which is analog and sensor packaging. And in this case, again, typically all these are done with printed circuit board architectures, where you have pre-packaged devices, analog devices, sensors, and mounted on the circuit board. And what we like to do is actually take these devices and integrate additive manufacturing with the device itself. So can you now, for example, take this device like a fan-out packaging concept, take these active devices, reconstitute them once you dice them, and then do additive manufacturing to do double-side integration of other actives and passives with additive manufacturing, so that now your chip becomes your substrate. And so your active device is the platform on which you add on your additive manufacturing to bring in 3D integration of other components. So this is, I think, the ultimate 3D integration with active devices, migrating away from the lead frame packages, for example, like the one that TI and analog devices may use. So once I start integrating my interconnects directly on the chip, on the diced chip, with double-side connections with additive manufacturing, I can bring in my passive components, certain active components on the top again, print antenna arrays. Now I can realize the real 3D chip scale modules, so or chiplet scale modules. And that's one approach that we are taking, again, working with Nano Dimension. So for example, in this, basically, we want to realize a very highly integrated photonic module for biophotonic application, where we want to bring in the controller, driver, everything into a very thin compact module. So this one, this dashed rectangle, which has basically the drivers for the LEDs, the controllers, the some of the resistors that go into the controller, the passive components, the driver chip, maybe even the transceiver, can be realized with this very compact 3D package. For example, we can additively manufacture, basically we can embed the active device, form the 3D printed architecture, then mount certain other active devices on the top, maybe the microcontroller chip. All the passives are embedded here, and certain drivers are embedded inside. And we started doing this project for the last 6 months with Nano Dimension, and this is still going on. And once you do this, now you can take this compact module integrate with the flex photonic LED detector array. Obviously, you can't bring in everything into the additively manufactured 3D module because certain things have to be spread on the skin to realize the photonic sensor detector array, but certain things can be compacted into a very 3D package. So that hybrid package flex integration is what we are realizing. And the other way is obviously to take these devices, embed them in the flex, form these additively manufactured interconnections, going away from the traditional PCB architecture. So this one is where we are realizing other kind of wireless sensor packages, where we take devices, embed them inside the, for example, cavity, form printed interconnections, and have this integrated 3D active passive devices. So you can integrate active devices and then in a flex substrate with very elastomeric printed connections, silver elastomer connections. And now you can realize them in a very 3D printed architecture. So these are again some details, but the idea is that once you realize the embedded devices on a flex with additive elastomer interconnections with silver, you can bend them and wrap them around, not only with just the interconnects, but also the active devices embedded in the device, in the package. So we are working with, again, Nano Dimension on embedding these devices for wireless neural recording. So there's a detailed presentation, I think right after this, on active embedding by Yahya. So he will talk about it and how to realize wireless neural recording. And again, another detailed presentation later in the afternoon with 3D antenna in active antenna in package for wireless implant neural recording in medical implants. So those are the applications that can realize this. Similarly, we can also realize flex integration with active devices. For example, we can realize a flex sensor. Now on the edge of it, we realize this 3D printed module, like what I was showing in the previous slides. Here I am only showing the sensor. So some part of the system will be flex, will be spread out. You cannot, obviously that has to be done through other techniques, but the signal processing chain, the wireless transceiver, those can be compactly integrated in 3D package. And now basically, how do you realize this interconnects between the 3D module and the flex sensor array is basically the challenge with perhaps rematable connectors and other opportunities, so that you can remate the 3D module and you can dispose some part of the system, reuse the other part of the system. So wireless seismocardiogram is the other application. Wireless biophotonic sensor is the application that I was talking about, where this is only a flex integration, very primitive, original, but now we are trying to take all these devices, make a very compact 3D module, and perhaps with rematable connections, rematable connectors, so that the power sources and the expensive transceiver microcontroller can be reclaimed, whereas certain parts of the system can be disposed. So the rematable connectors between the flex, disposable flex, and the 3D printed module, that rematable connectors is again another important application for wireless biophotonic sensors. And certain devices definitely need 3D packaging. There is no, other alternative. For example, we want to realize a 3D prosthetic for certain subjects with born without the limbs. So basically, if there are these congenital anomalies of the upper limb, then you need this prosthetic that should be very compact and with a lot of degrees of freedom in maneuvering, with very low power, but so that the battery can last for several days before you can charge at least. So in that case, obviously, if you look at what we built in our FIU senior design programs, you need this Arduino controllers, you need the MyoWare to sense the EMG signal and control it. You need a servo motor to move these flanges, the 3D printed, and a voltage regulator, a very large battery, and bring in a lot of packaging penalty that we pay. If you can actually 3D package all of it into a very compact module, then that is the best solution. And obviously that's 3D additive manufacturing is the only way you can realize that, and there is no other alternative. So in these applications, then there is obviously AME is the only way to realize. So my summary is that AME will shape future packaging by integrating new materials and 3D architectures for high energy density and efficiency. For example, high density passives, thermal management, reliability, where additive manufacturing will create new architectures that traditional wafer fan-out packaging, panel fan-out, multi-layered laminates cannot realize. New materials in smart millimeter wave packages. I want to bring in smart meta surfaces, reconfigurable materials, multiferroic, liquid metal, liquid dielectrics, and so obviously 3D printed materials will bring in all these new material architectures, encapsulations, and so on, so that I can create these smart functions with voltage, current, thermal actuation, and 3D active passive integration to create seamless interfaces in very highly in the real 3D form factors, not planar anymore, but 3D curved architectures to bring in analog RF digital photonic sensor in the same package. So I think this AME tool innovations, the materials that go with the tools will shape up all these future application, future packaging in all product segments. And I'm very, thank you very much for giving this opportunity to discuss the impact of AME, and we'll be happy to answer any questions. And also the next presentations will also cover some details.
Okay, Raj, thank you for your presentation. This was great, wide overview, and I know there are many questions, but given the time, I will bring two questions from the audience. One, basically, what manufacturing technologies will produce this type of structures, the complex dielectrics and conductive structures which are with place actives and passives simultaneously? If you can elaborate a bit more, but short, relatively short. And also, we'd like to thank you for staying this late. It's almost midnight for you. And you are in India right now, I know. And then from here, the next presenter is in Israel. So we could go around the world as we continue the speakers today. But could you please answer this question first?
Yeah, the nanocomposites are one way to realize this. So inkjet printing, if you can broaden the material scope for inkjet printing, that's a great opportunity to bring in nanoparticles with new polarization phenomenon, new multiferroic phenomenon. So colloidal suspensions, inkjet printing is one great way to bring in these materials. Similarly, the liquid metal also, it I think benefit from certain fuse deposition techniques and combined with the traditional flex cavity embedded active devices. So I think inkjet printing will have a role when you bring in the new composite colloidal formulations to it.
Okay, thank you. Now, when you talk about the chip being the substrate, so the chips will have to have the output contacts in both sides of the chip assembly, correct?
Yes, you need to have edge connections from the top to the bottom, and that's a great way for additive manufacturing. So you need to first encapsulate the chip edges so that the chip is passivated. So the gap fill and passivation is a very big problem in cavity embedding. And if you have the gap fill with planarization, with a epoxy planarization, then you need to go back with the laser and open it. And the laser, that creates a lot of constraints. If you can additively create this passivation around the bonding pads and the edges, gap fill and the edge passivation, that's again a very big opportunity for additive manufacturing. And then once you do that, now the bonding pads are automatically exposed, and now you can realize the metallic interconnections both from the top to the bottom. So gap fill, edge passivation, they give a lot of new enabling opportunities, and AME is the only way to realize that in the most efficient way.
Okay, Raj, I would like to thank you. And with this, we are going to let you go now to probably sleep, or you are welcome to stay. But we're going to now continue moving towards the west. From India, we're traveling now to Israel. I would like to introduce Michael Kedem, who is going to talk to us now about a system in a package. And with this, Michael, please join us.
Hello, everyone.
Michael, please share your presentation.
Hello, everyone. Can you see the presentation?
Yes, thank you.
Oh, thank you. Hi, my name is Michael. I'm from IAI. Second. My name is Michael and I'm from IAI, and I speak for the QuickSip project in the realm of semiconductors packaging. It's a joint venture between IAI and Nano Dimension. We are part of IAI acceleration project, which basically means 12 weeks to finalize the project from in an accelerator. Let's start. The QuickSip. The quick is obvious. What is the SIP stands for? System in Package. It is a group of active or passive semiconductors that were packed together for a certain mission. At this project, we packed a dozen of semiconductors, embedded and integrated them. What is a SIP? Imagine an all-star team where you gather from a group of available players, a team who can work together and win. Each player with its unique capabilities. SIP is as such a group of semiconductors, silicon, GaN, or gas, tightly coupled to perform a defined function, packed together. Why? For better performance, miniaturization, and cost. Where can we find it? Almost everywhere around us, dozens in a car, hundreds in an airplane or satellite, and even on the watch on your wrist, there is at least one. Look at the sizes. They go quite small. As for the simple ones, you can probably buy them off the shelf. For the more elaborated ones, they're highly coupled, or for the harsh environment, it takes 3 to 4 rounds to finalize one. Each round, for us, each round takes 3 to 4 months of delay due to time slot, stacking up, and setup. We'll get back to it. You've all seen the headlines in the newspaper in the last 2 years since the COVID emerged into our lives. They all talked about delays in supply chain and shortage of material because of shortage of materials due to increase in demand, which is true. And here comes the big but. In the semiconductor manufacturing and packaging, the real problem is the centralization and the shortage of manufacturers and high-end assembly houses for SIP. Look what it creates. Where the cellular and the automotive always are at the head of the line, they don't get any delays. Right behind them are the consumer goods, the aviation, and finally, at the end of the line, all the rest. Small quantities and sophisticated chips. 3 to 4 rounds of R&D, more than 1 year of delay for waiting for time slots. What do we propose? To take our fate in our hands, let's print it. Nano Dimension, a company placed 30 kilometers from Tel Aviv, developed a 3D printer that prints 2 components, a dielectric and electrical conductive, for PCB rapid prototyping. Using their technology to embed, integrate, and pack semiconductors together, as shown on the left side, is our proposal. The smaller 2 on the right side depict the conductive and the electric printing. The printer is at the center. What do we get? Speed, 2 months instead of a year. Size, depends on the technology, 10 to 30 times smaller. Performance, the main reason, due to the shorter electrical length and the fact that we can place the semiconductors where they need to be instead of where the technology can support. Here we can see a simplified view of the MVP, a functional exploded view. depicting the dielectric, the conductive, and the chipset itself. It's a 1/2 inch by 1/2 inch, thickness of 40 mils, 1 millimeter. The testing process and the results. A typical block diagram of a development process, it remains the same. We just added a dragonfly machine to the process. And now it allows us to do quick, hours to days rounds to gain total independence during the system development and the prototyping. Aiming for IAI in-house customers, time to market, more efficient design and performance. You can see here the depiction of the stages during the creation. We are at TRL 1-2. After 12 weeks, we started by analyzing and targeting technological and performance risks, during which new risks, as always, emerged, mitigated each with several solutions, and started synthesis and the integration of solutions towards the MVP. And depiction of the process, 3D model with the color codes, each color defining other function. Next slide, the conductive printing. You can see the DC, the shielding, the grounding, and the transmission line, the out transmission line. Printing assembly process of the MVP. Again, we developed several, but implemented only one. I'm showing here only the one that we implemented. There are other ways also. This is the process that we succeeded doing, and we got the results that we wished for. One of the more promising ones is the flip chip assembly. This is the way that we called it. Doesn't really mean that it is a flip chip. The chip doesn't have to be flipped. We just called it the flip chip. This one is a very promising one, and we didn't explore it yet. The main advantage of it is you get flatness on both sides for both of performance and solderability. Definition of the product, you can see that the product had simplified the model, what you see here, simplified the picture. The 4 watts HPA and the modulator, the two main blocks. We started by checking the resistance of embedded resistors. Continued by the measuring, simulating and measuring 50 ohms. You can see here 3 types of measurements on johnstick, on wafer, and soldered. You can see the consistency of them. Simulation vs measurement. We comparing 10 measurements. You can see a very small variance between on the transmission lines. Basically, our team, collaboration of 2 companies, between 2 companies, Elta and Nano Dimension. On our group, system, packaging, electronic and chemical engineers. On Nano Dimension and several application engineers, and headed by Nano CEO and co-founder, Amit. That's it. Questions, please.
Okay, thank you, Michael. And a couple of questions that I have here from the audience that while you were talking. And one of them basically is, how do you solder the components? Basically, regular soldering, solder reflow. Could you elaborate on the process for those?
Soldering, or you're talking about the soldering or the die attach?
Well,
the process.
Maybe you want to elaborate on both the die attach as well as the soldering of into the pads of the dies.
We started by just printing the electric and the conductive, creating cavities with or and without the cavities. And just a second. And right after it, we used the conductive glue. We just applied a conductive glue and did the die attach process, which was quite quick and easy. We didn't use any pick and place machines, and now I understand some machines were integrated into this Dragonfly 4. I haven't seen it yet, but now I understand they have, we used manual positioning under microscope. We just stuck into the machine a microscope and placed the dies on the conductive glue manually. And later on, after finalizing the part itself, we tried to solder it on a PCB. By the way, the PCB also, we printed it on the Dragonfly 4. We tried to solder it, and we had some problems since the faces, the surface of the conductive on the outside weren't so flat until the engineers that now they mentioned, the process engineers found a solution how to get it flat. Part of the other way that we went of the flip chip version was to avoid to get a better flatness on both sides if you want to connect it from one side or from the other side for soldering. And we used the manual soldering. We didn't use automatic reflow process. We didn't have much time to try and do it, but it worked. It took some time, but it worked at the end.
Okay, the other question that has come up here is if you have done any thermal reliability testing of the chips that, or the SiP that you produce.
No, we didn't go through thermal cycling. We did some short thermal cycling, but not really. I mean, we did about 5 cycles and cycle it from 0 to 80 degrees. We didn't go below 0 and we didn't go above 80 degrees. And the number of cycles, I don't know how much statistic you can deduce from it. And it's still something, but it's a problem. The material is a gap. The material's CTE is a real gap. There's an internal CTE between the conductive and the dielectric material, and of course there's a CTE of the carrier itself, if it is an interposer, a ceramic interposer, or a PCB. The easiest way would be of using it, soldering to a current with a PCB that was printed in the same machine. This way it might ease the tension and smaller the CTE mismatch.
Okay, then the last question that has come up just as you were talking is related to the slide you have with the roadmap of the TRLs. So if you are, you indicated there that you are now at TRL 2 to 4, you plan to go to the higher TRL. Could you describe what do you need to achieve that the higher TRL? Not only 3 and 4, but beyond 4 to more of a TRL 7. That's what the question is.
We need basically we need more time. We need some time, and that's about it. TRL 3-4 is to go for a final product. It's a very far one, and we just need time to optimize the process itself. And again, we didn't cover all the options that we had. We developed here about 5 processes. Each one differs from the other one. Each one has its own advantages and disadvantages, and they all need to be rated. And in order to go through these 5 processes that cover all of the, regardless of the material gaps, we need time. That's about it.
Okay, Michael, thank you for this presentation. I don't see any more questions right now. So
thank you, guys.
With this, have a good night there, and we're going here to a presentation. The next speaker. Let me just briefly share my screen here to introduce him. So we'd like to introduce Mr. Yahya Ben Sayed, who is a PhD candidate at the FIU, who is going to talk to us about embedded actives and fabricated passives in with AME for wireless sensors in biomedical, actually it's in biomedical devices. So with this, Yahya, the stage is yours.
Hello, everyone. My name is SK Yahya bin Saeed, a graduate student in Florida International University. Today, I'm going to talk about embedded actives and fabricated passives in AME for wireless sensors. So we have two systems. One is invasive neural recording. The other one is non-invasive seismocardiogram recording. So I'll cover them both today. So I'll start with invasive neural recording. So just like ancient Greek people imagined the possibility of soaring flights, our minds are now dreaming about merging machines and brain in a way so that we could solve the human mortality problems. One of the most critical applications of brain-computer interface is that to use it as a diagnostic tool for epilepsy. So what is epilepsy? Epilepsy is a chronic disorder, which is most notably known for causing seizures. And seizures are abnormal neural activity in the brain. Among the partial epilepsy, most common is temporal lobe epilepsy, which doesn't have any effective medical treatment. So location of this seizure is needed to find out. So in order to locate this area, we need to record interrectal epileptiform discharges. So existing neural recording systems have some issues. They have wire electrodes, so which causes which hinders free movement and causes trauma. They are bulky in size and large, and they have battery in the systems, and this battery needs replacement. Also, high density circuits tends to hit the tissue, and if you hit tissue, it's not good for human body. So we propose a miniature neuropotential recording system with advanced packaging. So we have battery-less implanted sensor, and we have interrogator. So in our battery-less implanted sensor, we have antenna, transistor, capacitor, and Schottky diode. From the interrogator side, we send a 2.4 gigahertz signal, and at the implanted side, this signal gets converted and mixed up with the neural signal transmitted back to the interrogator. So, and the uniqueness of our system, that system is it's an RF backscattering based battery-less system, and battery-less high impedance matching, tolerance to DC offset voltage, and signals acquisition as low as 20 microvolt peak to peak. And we miniaturize the implant with embedded active and passive components. So before jumping into more circuit explanation and all that, I would like to briefly discuss the electrode impedance mechanism. Subcranial electrode has been well studied. So the double layer capacitance, actually the cause of the electrode impedance being dependent on the frequency. As many studies shows that impedance magnitude reduces while increasing frequency. At the smallest frequency where neuropotentials may be identified, for example, at 0.5 hertz, the electrode impedance can be as high as 33 kilo ohm. And the electrochemical reaction at the electro interface generates DC offset voltage. So now, this wireless and batteryless implant match to high impedance electrodes. So our circuit is operated in two modes, DC and RF. So in DC mode, a 2.4 gigahertz signal is transmitted from the interrogator to activate the implant. So when the implant receives the signal, the diode acts as a rectifier to generate DC current to self-bias the BJT. After the biasing, the neuro signal, low frequency, low amplitude neuro signal can pass through the base and get up converted by the diode. The BJT emitter is connected immediately after the Schottky diode, and the collector is grounded. So due to this operation in saturation forward active region, signal can travel from emitter to base, and DC voltage may be ignored. So these unique characteristics suggest tolerance to DC offset voltage. And our BJT acts as a buffer to transform high impedance to low impedance as well. So in the RF mode, in the RF mode, the diode acts as a mixer. So it uses a 2.4 gigahertz signal to up-convert the neural signal and generate 4.8 gigahertz plus minus F neuro, and sends it back to the interrogator. So let's have a good short discussion on the neural recording system, especially on interrogator. So our interrogator is composed of several components such as signal generator, circulator, filtering and amplifying block, multiplying chain, and mixer, as well as displays such as spectrum analyzer and oscilloscope. So a signal generator generates 2.4 gigahertz signal, and the splitter splits into two parts. So the one part goes to the circulator, and the circulator directs it to the interrogator antenna, and this antenna sends signal to the implant. So other end of the splitter goes to the multiplying chain block, and at the mixer side, this whole signal gets down converted, and we see the F neuro signal demodulated at the oscilloscope. So now we have to calculate the noise figure of our system, because that's how the noise floor is calculated. So the noise figure of our interrogator is 4 dB. So it means that the noise floor of our interrogator is minus 133 dBm. So we have two variations of implanted sensor here. One is with AME capacitor, other one is discrete asymptotic capacitor. So of course, the AME capacitor, with AME capacitor, we save time and labor of soldering as well. And of course, the AME capacitor has low parasitic loss compared to commercial discrete capacitor due to absence of soldering and packaging. So the overall size of our fabricated implant sensor is 8.5 by 8.2 by 0.7 millimeter cube. And the substrate is UV rated acrylic polymer, the dielectric constant 2.71, loss tangent 0.011. And to encapsulate the device, we used a standard PDMS. So the neural system performance. So we used for in vitro experiment, we placed our implant under the skin, pig skin. The thickness of the skin is 2 millimeter. The interrogator is 1 millimeter above the pig skin. So in frequency domain analysis, we observed that the backscattered power is improved by 0.8 dB with AME capacitor. And this improvement is attributed to the lower parasitic because of, as I said before, no soldering and packaging of commercial because AME capacitor doesn't have the parasitics of commercial capacitor because of the packaging and soldering. So let's go to the minimum detectable signal. While we vary the impedance, we see that the minimum detectable signal at 35 kilo ohm is 20 microvolt. If you go beyond 35 kilo ohm, we see that we cannot acquire 20 microvolt peak-to-peak anymore. So we keep the power, our incoming RF power fixed here, which is 6 dBm. And you can see the difference in AME cap and discrete cap samples. So at 20 microvolt, peak-to-peak is detectable with discrete cap sample by increasing RF power. So we have to increase RF power from 6 to 7.3 dBm to detect 20 microvolt peak-to-peak with SMT capacitor sample. Now we have to validate the functionality of our neural recording system. So we use three different types of signal. One is square wave, sine wave, and the ramp. All of them has 1 kilohertz frequency, and the amplitude is 1 millivolt peak-to-peak. We recovered them successfully, so it validates the functionality of our device. However, if we go to lower voltage, low amplitude voltage, we see that the signal shapes get deteriorated, and that's why we need the digital filtering. So now I'm going to talk about the non-invasive seismocardiogram recording. So we know that heart is one of the most important organ in our body, and coronary artery disease causes heart failure. And this coronary artery disease can weaken the heart muscle, and this may lead to heart failure. So, despite the advance of medical treatment, the hospitalization hasn't been reduced. So overall cost, the overall cost of medical treatment hasn't been reduced down to a level where underserved people can get treatment. So there are many clinical techniques available to measure heart activity. There is no doubt they provide life-saving intel. However, they require expert technicians and clinical settings. So let's talk about briefly on SCG signal. So SCG is a micro vibration of the heart that propagates through the chest wall. And it ranges from 10 to 40 hertz, and amplitude varies from 1 to 3 millivolt peak-to-peak for a healthy adult. So with this seismocardiogram signal, we can identify the anatomy of the heart. So one of our collaborators have a hypothesis that if you can record heart sound and measure the delay, you can predict heart failure. So there are few commercial SCG monitoring devices available in the market. Either they are battery dependent, or have active components or complex circuitry, or they're expensive or need surgery. So we're proposing a miniature non-invasive, fully passive seismocardiogram system. The first uniqueness of our device or system is highly compliant thin film piezo sensor. So highly compliant means that the young model, the stiffness of our sensor would be in the range of 100 kilopascal to 20 megapascal, which is skin compliant. Then wireless passive module. We have antenna, we have anti-parallel diode, and we have bypass capacitor. There is no battery in it. There is no energy harvesting unit in here. When you combine one and two both, we get fully passive wireless SCG sensor, and the rest of the part is the interrogator. So now the question is, where should the sensor go? It's very debatable. Debatable that there is only one place you can get the SCG recording best. So we actually chose the most common place to design our sensor. So the most common place is sternum, which is very close to the heart, and and the width changes based on the positions. So the structure of PVDF electrodes needed optimization in terms of stretchability and sensitivity. So for any given serpentine design, the area density, which is the ratio of electrode field mesh area to complete square area, and it dictates the quality of the signal captured. And the serpentine design has several parameters and depends on rotational angle, outer circle radius, and curve width as well. So we keep the theta at 15 degree and circle radius of 1.25 millimeter due to machine limitation, and varies the curve width. So while we vary the curve width, we achieve 50% area density. We couldn't go more because of the machine limitation. So it's time to show how we fabricate this thin film piezo sensor. So we have a blanket pre-pulled PVDF, and we print the silver on both sides and cure it at 60 degrees Celsius overnight. Then placing the PVDF thin film on a weak adhesive transfer tape and use the cutting machine to pattern it, and then transfer it in a strong adhesive substrate. And with the uniaxial test, we see that the stiffness of the piezo sensor is 10 megapixels. So we achieve the skin compatibility. So compared to other design, our design is skin sensitive to planar forces, skin compliant, and easy of manufacture. So we have fabricated with nano dimensions Dragonfly system. We have fabricated the wireless module, and then we attach it to the thin film sensor. So the overall size is 26 by 17 by 0.750 millimeter cube. So now we validate the system with a mechanical pulse generator. So this mechanical pulse generator generates a mechanical vibration of 40 hertz. And that 40 hertz causes strain on the sensor, and the sensor induces the electrical voltage. And the electrical voltage goes into our wireless module, while the 2.4 gigahertz signal coming from the interrogator side is basically the same system as I described before in the neural recording system. So it's a backscatter system. Our wireless module converts the signal, mixes with induced signal, and send it back to the interrogator. So in a bandstop experiment, we showed the demodulated signal and the functionality of this fully passive wireless STS sensor. So it's time to wrap up my presentation. So far we have demonstrated the battery-less highly sensitive miniature neural recording system with embedded passive and active, and conformal stretchable miniature fully passive wireless Seismocardiogram recording. We need additional work for further reduction in size and component matching, and we will explore printing the pattern on the PVDF in AME fabricator directly followed by the AME electronics. Thank you all, and a special thanks to AME Fabrication and Nano Dimension, especially to Dr. Haim Nalmana and Dr. Ryan Barr. Thank you, everyone.
Thank you, Yahya. At this stage, we are right on time. We are going to go to the next speaker because also it's a long presentation. And any questions we'll try to answer them later on. Okay. So with this, I would like to turn the stage to introduce our next speaker. Let me just share the screen here a second. Mr. Yao Beck, Director of Enterprise Tech Marketing at Altium, who is going to talk to us about how to design from the ECAD electronic devices design into conformal shapes design on 3D mechanical packages such as SolidWorks and others. Joao, the stage is yours.
Thank you, Haim. Let me just start sharing it.
So if you can put it on
Yep.
presentation mode, please. Okay, great. Thank you.
Can you see it? Yeah, cool. So, hello, everyone. It's a pleasure to be here with you today. I'd like to first thank Nanodynamics for the invitation. I'm going to be talking about structural electronics and fast prototyping, most specifically the routing of electronic components over 3D body substrates. What we will see is an ECAD technology that is being developed to make 3D routing easier than the current methods and capable of outputting mechanical files that can be then 3D printed and manufactured. I am João Beck. I'm the Director of Enterprise Tech Marketing at Altium. So let's get started. So let's start with the challenges of designing structural electronics directly into the MCAD tool. So the first point is disconnected and distorted projected traces sketches. You probably have tried to do that before when you have conformities or irregular bodies with round corners. And from the MCAD, you have to create projected sketches. So these projected sketches are a big problem when it comes to ECAD because they distort the length of the traces, and also it's really hard for you to connect traces from different faces. You have to create multiple sketches and at the end try to connect the trace from one plane to the trace from the other plane. So the second topic is they are logically disconnected by nature from the MCAD. Since they are just mechanical designs, you can actually export the net list from the ECAD schematics, but you have to check connections one by one. You have to place your components looking at a netlist file and then trying to sort out what's the best placement for the components, which makes really hard. The biggest challenge is to make sure you are going to be able to route all the components due to the possible crossing traces. So I'm sure that if you're doing like a 10 components design, that's going to be fine. But if you're doing 100 components or over 100, you have to make sure that their traces are not going to cross each other. And if you try to do that, or try to accomplish that, you find that making changes to mechanical trace or sketches, it's going to be very, very much time consuming for you. So there are also no automated checks to find out if, any component is disconnected, if you did not make any mistakes connecting pads that belong to one net and then connecting a different pad that belongs to another net. This is all visual. It is all these checks would be visual from the MCAD side. You also can have short circuits because you need to make sure that the traces match each other, are connected or not, or the nets. You can have misconnections as well, because there's no way for you to check if there's a component that it hasn't been connected to a specific net. And again, very hard to optimize component placement. The other topic is you don't have an ECAD component library. And I know it's fine for mechanical designers to create mechanical bodies, but it's not the same when it comes to from MCAD world to ECAD world. It's not like you're shaping a 3D body. You have, hundreds of millions of different components. And you probably don't want to keep track of or create a library with, a huge amount of components. Because at the end, you probably are going to use, you can possibly use, over 100 components in one single design, and you don't want to spend all your time creating these components or even finding step files for all these components one by one. And the last topic is, again, this is what we call, and we used to do in the past, the freehand PCB designing, because there's no logical connection. It's pretty much you drawing, like in the past, drawing traces manually from point A to point B. Now, let's go over and just see how what I'm talking about in the real life. And I'm using here SolidWorks, but it could be any mechanical tool, any mechanical package. I want to use this one just as an example of how usually designers design a sketch over the 3D body to have the traces laid out in the body. So pretty much what you have to do, this is a very, very simple sketch. And I wanted to create one single sketch just so you can see that this is not possible. It's not possible to have only a single sketch if you have a regular 3D body shape. So what we have here, I tried to create a I tried to create a plane over the 3D body so I can project the traces over it. And what you see here is that I have the length of this line here, or of this trace here that I created on the plane, on the top plane. But then when you have the projected trace over the 3D body, you see it's much, much longer than what actually is. It's also with one sketch, this is you're going to end up having the trace with all this, cornering and round edges that you might not want that for some reason. And again, it's really hard for you to have a straight line here going from here to here without having this curve, even if you create multiple sketches, especially for the round edges here. Now, the most important thing here is that with this sketch that I created, I should have a component placed here. But the distance between these pads, it won't match with the actual component, because the projected sketch actually distorted the traces or the length of it. And now they're much wider than what they should be from the sketch. And remember I mentioned about the different sketches and being difficult to connect them. So if I had another plane on the side here, and I needed to connect the trace from the top to the side, it's really, really hard for you to have a trace or a sketch that connects from multiple faces. Okay, it's time consuming, it's not impossible. That's what I'm trying to say. Let me go back to the presentation here. So what we're trying to develop is a solution that will really help you save time when designing ECAD and then having it manufacture or pass prototype in a 3D printer. So let's go over the topics we have for the solution. So we have then, since it's coming from an ECAD, we're going to have all the netlist displayed connections right when you're laying out the components in the 3D. So you can, right from that moment, see where each component should be connected to. And then having this information, optimizing the placement makes much, much easier. You can know beforehand where's the closest position that you can have a component from each other, and when you're going to have the least trace laid out on the 3D body, you're going to make sure that you can actually place or route all the components on the top of the 3D body. So you have all these advantages. Then you also have the clearance and connection check rules. Again, it's with the ECAD logical connection, you actually end up having the ability to check for this misconnected components. You're going to have the clearance rule, making sure that different nets don't get connected, that you keep distances, or you can set up specific distances between traces as well, or different net traces. You can also run other type of design rules, such as different width, trace width. So all these design rule checks can be done from the ECAD side, and it cannot be done today from the MCAD. Then you also have the advantage of having hundreds of thousands of components available that you don't actually need to create. Not only they come with the 3D body, but they come with all the technical information, data sheet, and all the values that they should have. We also have the direct 3D routing over the substrate. So again, remember I mentioned about having to have multiple sketches into different planes in the MCAD side. And from the ECAD side, you don't have to lay out any sketch. You just go and start routing straight away right over the substrate. Let's see how this is gonna actually works out from the solution we have here. So let me go over the actual flow. Okay, so I'm gonna bring up a mechanical body here from SolidWorks. Let me just open up this one. Okay, and I'm gonna get back to the reason why I laid out a sketch on the top here. Okay, let's pretend this is not here right now. This sketch is not here, just a 3D body. And so how this process starts, you have the 3D body, right? So what we're gonna do, you can export this 3D body from any mechanical package. You're gonna save as here, in this case, I can save as an IGs, a Parasolid, or a stat file. In this case, I'm gonna save as an IGs, just so I can show you something else, another capability you can get from it, and the advantages of exporting it as an IGs file. Let me go over here. I always take a while to find the IGs file here. Here. Okay, so let me save it on my desktop. And once that is done, I'm gonna get into the software. Okay, so what we have here at Altium Designer, we have the normal or usual project structure. And again, because it's an ECAD software, we have, of course, the schematics and all the logical part over here. We do have, of course, the 2D mode for designing PCBs. This is the standard normal 2D mode, right? Where you can actually route over normally over a PCB. But we are introducing this thing called PCB doc or PCB 3D. Okay, so if I go ahead and add a PCB 3D file, the first thing it's going to ask me is, what's the 3D body you want to route on top or create your traces over it, either step, IGs, or Parasolid. And it's going to point you should point it to where the file is. So this is where my file is. And here it is. So this is the 3D routing environment. And what I'm gonna do here, because I'm on the ECAD tool, I'm gonna bring in all the components I have from my schematics into this 3D routing or 3D layout file by simply going and importing it. Sorry, just need to save it. And then importing it. Okay, so all the components will come with all the connections, and we don't need the room for it. And then I'm going to execute it. And now I have all the components floating there where I can just start placing them on the top of the substrate. It's a really, really quick and easy process here. I can then also rotate components if I want, easily position them differently, however you want, just laying out some of them. And what I want to show you is the connections. You see the connections there? You see how I can now see exactly what pad should, or which pad should be connected to what pad. Which pad has the same net in this case, of course. And from there, I can easily start routing them. I can have a view without the actual 3D bodies for now, just to the sake of routing. And then I can go route and start routing them. So without the need of any sketches or different multiple sketches, I can even go through different faces. So if I go over here, you'll see I can go around round edges. I can go and change the plane that I'm automatically change the plane that you're routing. And you can easily start routing the whole circuitry right from the software here. Now, to help you out with, having a grid or having everything, the traces well placed, and also having the 45 degrees over the routing, you can easily switch on grid. Now, the grid comes with the proper, orbit, the X, Y, and Z from the mechanical 3D body. So I'm just gonna switch to the right one. And then here, you can set up your grid distance or step. So I'm gonna set 1 millimeter by 1 millimeter. So now you see how easy this is becoming. I can also, the components and the traces can follow the grid. So if I want to start routing there from that point and then suddenly get a 45 degrees, I can easily do it. Okay. Now, remember I mentioned about the sketch over the 3D body in SolidWorks. So let me get back to that. When you use step models, it's going to work exactly how you see here. When you use IGES files, there is a small advantage, that is you can bring in projected sketches into your ECAD. So if there is a path that you want to make sure it's used on ECAD for either placing the components or aligning the components or even routing them in a specific way, you can bring that into your routing here just by bringing in the sketches. Okay, this is a really powerful tool, and it just saves so much time from you creating all those sketches and disconnected, of course, components. Let me get into the complete design here, and I'll show you something. So on this complete one, I want to show you something I can also bring in. Remember I talked about design rules? So I have here, I assigned a specific color for a specific net, or it could be a net class as well, right? So I'm calling this power, I'm giving it a special color, and I can also assign a design rule for it. So let's go over here into design rules real quick. And now the normal width I have, it's set to 10 mils. Let's create a quick rule here for the width, 10 mils is standard. Let's create one for 30 mils, just so we can see it clearly. And let's call it power. And let's assign it to, let me see if the next it's here, power. Okay, now let me make sure I bring in the components. I think this one has it, has that net. There you go. You see that the connection line has a different color. And I routed before with a 10 mil trace width. Now, if I try to route this one, sorry, it's not that one. Sorry, something is wrong here, but it would automatically use the trace width assigned to it, which is 30 mils. This is under development, but it's what it would happen. You can assign different color for specific nets. You can assign different rules for specific applications here too, for your design, just like a PCB design. Now, when it comes to components, let's get to that problem. Instead of creating the components, I can access this online library. Let's say I need a USB connector. So I can search for a USB connector. This is looking over an online library with over 300,000 components. And I can filter that by manufacturer. I can do whatever specific search I want to. This is all coming from Octopart, as I said. And then let's say I want to place this component here. It's an USB C, if I'm not mistaken. And then if I want to bring that into the PCB, right? Not the PCB, to the design, the 3D layout, I can simply import that. This is an example. And here it is. Without the need of creating the component from scratch, without the need of spending any time working on this component, I can simply bring it in, use the online library, search for the components, and then start laying out them. Okay, so that's pretty much how the solution we envision to have. Besides that, let's talk. Look, I created a trace here on the side, and I'll show you what the outcome is going to be. Let me go back to the presentation, and let's see what else I have to show you here. So, okay, this is well and good. We can route over the substrate. We first import from the ECAD package the shape that we want to be routing on. But then what's the output, right? So this is, with this tool, we can optimize routing for better component placement. As I mentioned before, we can prevent mechanical and electrical problems. We can save time, make use of the component models. We can speed up the routing by laying traces directly over the 3D surfaces. And then let's get to the output formats finally. So we can output these files into step file, IGES again, or Parasolid. And then from there, from your ECAD package, you can easily convert into an STL format, slice it, and then 3D printed it. Let's see how that would work and how easy that process would be. So you pretty much would go from here, from your design, your finished design, you would export it, 3D layout. So let me save it on the desktop. I'm going to save it. Wait a moment. Done. From the MCAD tool, let's see how that, what's the outcome is going to be. Let me just open it up. Now, with the 3D body, we can actually have the traces extruded out of the substrate or into the substrate. You can set up the extruded height as well. I have here, I think, 50 mils, if I'm not mistaken. And then if you want to have a look or have them separately exported, you can do that too. So let's see here what we have. So if I want to take out the, just hide the 3D body. Oh, sorry. Here it is. Here are the traces, right? Here are the traces. I don't know if you actually can see it, but my computer just flicked with the video card, but with the zoom.
We can see it. Keep going.
Oh, you can see it. Cool. So this is pretty much the output that you can actually later on slice it and then manufacture in 3D. Let me go back to the presentation again, just to finish it up. There you go. So here's the flow that we talked about. You have the substrate design in MCAD exported as a step file or an IGES file, then imported into Altium Designer, which will make it a actual logically connected design. Then you lay out the components, route them, export them as a step IGES or parasolid file with the traces extruded out of the body or into the body, however you want. And that will be ready for your slicing and printing. There's only one more thing that I want to show you quickly, is that what if you want to talk about, when I talk about a normal PCB and having cavities for components to be embedded into layers. You can do that today with the normal Altium Designer as well, if that's what you want. And then we have a tool called our co-designer, make MCAD co-designer, that can export it into SolidWorks as a solid part as well. Not only SolidWorks, but also Creo from PTC and other tools as well. So what you have here is just a simple design where we have this laid out. Sorry, it's just flickering here. Laid out PCB with the components and routing. You can see that there is an embedded component there in the mid layer, and the traces and the vias are solid vias. They can be exported into your mechanical package as solid vias that then again can be 3D printed with conductive ink, and you would have components, vias, and traces right within your 3D body. Okay. Going back to the presentation, do you guys have any questions for me?
Yes, I'm waiting for Chaim to join 1 minute. We do have some questions coming.
Yeah, there are some questions, and some of them you may have answered that in part, but let me ask that so maybe for completeness.
Uh-huh.
And it's related to making the traces inside the 3D body, and then what constraints you have in doing that. You show it's another solid, but then you need to, when you slice it, how this slice is taking place, and then how you consider the fabrication of that composite material.
Okay, so with the routing on the surface, at the moment, we can only route and place components on the surface, on the substrate of the 3D body. We cannot have embedded components on the 3D layout itself, the solution that I showed first. What you can actually do, you can actually route over a surface and then have multiple 3D bodies, and then at the end just assemble or have them assemble on the top of each other, which will make and interconnect the traces, which will make a multi-layer. But it's would be a manual process. It wouldn't be a feature that we carry today. For the normal design, PCB design with multiple layers, embedded components, with the solid vias, you would have the cores that you can set up the height, and then you can, with this tool called ECAD Co-Designer, you can export that design into the mechanical tool. You will come in as native your mechanical package tool format, and you will be able to see inside the 3D body all the vias and the solid vias, the traces, the components, everything will be exported into the native ECAD package you have. Okay.
Okay. I think that that was basically the question that we had from the audience. Very nice work. Thank you for the demonstration. This is enlightening and probably would facilitate a lot of work that people have been waiting to be able to do on the integration of an ECAD into a mechanical CAD. Do you have any idea if you guys plan to create the ability to basically do more of a freedom to design the traces inside the 3D body and be able to then fabricate it without the manual assembly?
From what I heard, the developers, the product manager told me that it is in the roadmap, but he didn't want to share with me a date, a release date for it. Okay, so, but it is in the roadmap, so you probably see it in the near future.
Okay, that sounds great. So, Now, thank you for your great presentation. And even though we are 5 minutes ahead of time, I'm sure that the next presenter will like to enjoy those extra 5 minutes. So with this, it's my pleasure to introduce Professor Ying Wang from the University of Southern Florida, who is going to basically talk to us about, let me just share my screen briefly here. Talk to us about additive manufacturing of antennas, phase antenna arrays, wireless sensors, and millimeter wave front-end transceivers. So, Professor Wang, the stage is yours. Thank you.
Going and go to the PowerPoint. Can you guys see my screen?
Yes.
Okay. Thanks for the introduction. It's my pleasure to present our work. This is work done by some of my current and former doctoral students and other collaborators in our research center. We have a lot of focus on putting together wireless technology. In some of the sub area, we're focused on additive manufacturing for package or making antennas and integrating active passive phase array, making a lot of interesting millimeter wave targeted circuits. This is a motivation slides and that I tend to use in many of my workshops. The things I can highlight, I can take this away. Things like if you're looking at the lower side of slides, you should see back in the 2005 when people actually have a gathering, we actually can go for the purpose of gathering more simple. But once the iPhone started, if you look at this chart in the 2007, smartphone over dominantly changing how many sensors we each carry. And obviously, once you go to even nowadays, or even since 2013, at least some of us is carrying our gadget, taking video and picture just to show our friends far away that we're actually there, instead of enjoying what is going on there to a lesser extent. But as we go to the future, there's three technology, in my view, that's going to drive the need of bigger quantity or bigger integration level and higher frequencies. There are 5G, Internet of Things, and 1 trillion sensor economy. If I quickly move over to this part, and based on Ericsson's prediction, the mobile data rate traffic is going to increase 300 times in the next 10 years. And this is a fairly recent report, and the IoT market projected also going to expand 12 times. Interesting thing, I did a calculation between the two. You're looking at each of the IoT or phone gadgets going to have to be able to take care of 25 times higher data rate, which means a lot of more integration, more devices, more antenna, more electronics. So if you can move to the next page. Sorry. Okay, so this is my very early work. Somehow I was not hiding this. Let me try to hide that. Okay, perfect. Take that away. Okay. This is one of my earliest NSI-funded project where we're the first inventor of the technology for focusing doubling transponders, that is battery release, basically can be powered by your interrogation signal. And in order to do such a sensor node, of course, we want to design very efficient 3D antenna so you can receive the 2.4 gigahertz interrogation signal. The sensor have to carry a fully integrated impedance matched diode doubler so that you can double the frequency at a pretty low interrogation power, which I will show on the next page, and radiate 4.8 double frequency back to the interrogator to minimize any potential interference. And then the fact this thing's 3D, we can also put sensor in there and putting the whole thing into a ping pong board as a package to hermetically embed that in the stand in some cases. So if I move forward, okay. So one of the important thing, obviously, is to design the antenna in a 3D shape. This case, we have the 4.8 dipole antenna still looks like a dipole, but 2.4, you have to meander that into the 3D space to balance between the radiation pattern, which should be more isotropic in this case, because you never know where sensor is embedded in the concrete wall or the sand or the ground. And then you want to also, in between the two, making your diode doubler in order to make sure your diode electronics is good doing this job of frequency doubling at an incident power of negative 25 dBm, which is 1 microwatts of power received at 2.4 gigahertz antenna. We take out fundamental 2.4, 4.8, 7.2, and 9.6 gigahertz harmonics and present them different type of impedance match or mismatch to make sure maximum power transition to the 4.8 gigahertz, then radiate that back. To do so, we are able to achieve interrogation range from this battery release sensor up to about 43, 45 meters distance, which happened to be the diagonal distance of one of our student lab building attic on the top of our building. Okay, so then we take this sensor node into the antenna chamber, and we design the transmitter setup, the receiver setup to interrogate the sensor node, which is battery free. In order to demonstrate the real purpose, which we target for several infrastructure monitoring, we introduce a vibration sensor, which is piezoelectric cantilever, which generate a waveform. This waveform modulate the conversion efficiency to make it up and down. So we have amplitude modulation coming back from the sensor node. We demonstrate such a sensor with pretty isotropic radiation pattern to the interrogation signal, so that people interrogate such sensor doesn't have to know exactly where it is. You can still interrogate, establishing a link budget to communicate and getting the waveform back to your source. So the main technology I will spend time talk about is not sensors, mostly based on laser enhanced direct additive manufacturing. And we're having one of the N-scrape printer in our lab, which does incorporate basically the fused deposition modeling, printing of thermoplastic composite. Many cases we're in-house preparing those materials, some of the material having comparable or better than Rogers or microwave laminate kind of dielectric loss tangent. And we also using most of the time silver powder ink to particle ink to print the interconnect layers. As you can see, there's some interconnect layer demonstrated here. And most importantly, we try to build a very repeatable foundry process-like library of models so that eventually we can send our process and share that with other users far away. They can send their design, they can simulate, predict the performance. We can implement additive manufacturing, pick and place, fused deposition modeling for dielectric, and the micro dispensing for metallic layer, followed by laser processing for trimming or some kind of photonic curing for sintering to make such a structure. Importantly, we're using a picosecond laser that can downsize the minimal feature size, the gap, and the feature size to about 3 to 5 micron, mostly not needed in many of the design we are implementing. Sorry. Okay, so this is moving on to our initial approach to additive manufacture antennas, showing to the left and right. Sorry, two type of antennas we built. To the left, antennas built from the top side down. So we started printing the support layer, followed by alternating metallic layer, which is in the red color, and we also changed the infill ratio of the dielectric. So we're able to make play with infill ratio to enhance antenna bandwidth, which I will talk a little bit more about in the later slides. Showing to the right, we're printing this case from the bottom side up. We are making a cavity embedding this case phase shifter into the package. And we're also able to build not a solid wall, a pillar or weir hole formed cavity that behaving as a solid cavity wall connecting to the ground plane here to make sure we can engineer the antenna to have optimal front to back ratio, basically not too much back radiation as a result of that. Okay, so, I have to use my mouse to change. That's okay. So basically, this is the details for the second antenna that I showed on the previous page. In this case, one of the important features is this layer. We're using a 50% infill ratio ABS, which can help us reduce the dielectric constant of that layer to right around 1.5, 1.6. This helps you to increase the radiation efficiency, antenna bandwidth for the patch antenna that we're feeding by a slot. And also, in order to make sure we have a good front to back ratio, we also incorporated this weir hole array with engineered distance so that they behave as a solid wall cavity connecting to the ground plane. It will help us to ensure the optimal radiation efficiency and pattern, so we have an optimal front to back ratio as a result of that. In order to incorporate the phase shifter, at the time, we were manually inserting the phase shifter in the QFN package into the cavity preform. In order to help us removing the package, we even leave some kind of feature on the side in case we have to re-engineer such a substrate. But we can directly print micro dispense the interconnect over the paths for both control line DC feed and also RF input and output. And we are also, you can see the relative position of the feeding line in between the cavity, so it can go through the cavity to feed inside the cavity, then connecting to the slot antenna in that way. As you can see, the minimal feature size in this case is only 300 micron, which is well within our reach for direct print. And this is a package. The next thing about this package is that as a unit cell, we can testing the antenna radiation pattern, and eventually we can incorporate in a tile style a bigger phase array into antenna array that way. So this showing the tested antenna performance. This case, we're achieving 24% of radiation bandwidth. The gain was 7.2 dBi, and then we also realized 80% efficiency. Most importantly, because of the incorporation of the cavity that is embedding in here, you're able to achieve 20%, 20 dB of front to back ratio. And all of this is a little harder to do with the uniform material construction traditional multi-layer PCB technology. We also found out in this process, not to our surprise, even the best microwave gallium arsenide phase shifter have its own losses that were impacting the unit cell performance, which you will see in a later slides, in a later figure. So basically, the impedance match was overall pretty good for all the 3-bit operation state 0 to 355 degree. And we also show a pretty flat phase shift across the target bandwidth, in this case 9 to 11 gigahertz for all the bit that we turn on. However, you can see some variation in the gain, mostly because of the losses of the phase shifter in different bit. The maximal loss can be as high as 6 dB. Most places is in between 3 to 5 dB range, which is not ignorable and it's not flat across the frequency, which is the reason why we eventually moving into active beamforming from the passive beamforming concept. But as you can see, the radiation pattern exhibit a good front to back ratio greater than 20 dB, which is again one of the important performance aspect we anticipate to achieve by this particular design. Once we build a unit cell, our goal is to further expand this and building it into a larger array. The array our target to build in the project was 8x8 array, actually over a doubly curved surface. In order to validate unit cell with all the control signal and all the beat variation and the radiation pattern, we further improve the design by implementing a 2x2 subarray. This case, instead of using all the 28 lines for feeding and balancing, we can drop the line to about 8 by introducing a shift register, a digital control circuits onto the same layer, embedded alongside of the cavity of the phase shifter. Then we take the signal through a signal wire over to the top layer so that we can interact with other signal processing and radiation features. This is what I'm originally talking about. The project originally was targeting to replace the belly part of the Scan Eagle, which is made by In Situ, one of the spin-off company from Boeing. The belly part is a mechanical part, but if you can replace it by roughly the same design, you can have phase array functional at the belly of this UAV. You can communicate uplink and downlink, doing all of that. But as a result of that, the detailed data we could not share for the phase shifter performance. But I can show you the simulation was done very carefully for this design. The printing was done by our collaborator for that project, Sapir and Discrete, using one of their 5X system. As you can tell, printing such antenna multi-layer, you need to have those 2 degree of rotation to help you getting the precise finish of that design. And also, as you can see, in order to get such a radiation pattern for 8x8 array and feeding each of the antenna element universe individually, it takes a long time, a lot of computation resource to achieve this. Overall, this antenna design achieved 22 dBi of both side gain. You have 86% efficiency without considering additional distribution network, feeding network losses. It achieved very good 50-ohm match and bandwidth control and all of that. And then we have a press release article together published with Nscript talking about the success of getting a phase array on a curved surface. This was a US Air Force funded project that we finished a couple years ago. Moving along, as I mentioned, in the previous phase array concept, I realized we can do better with something that can compensate the variation of the gain due to the change of the phase. Obviously, such a technology already exists, which is how you can use automatic gain control and other active electronics to do such a compensation. This is why we move into considering incorporating beamforming IC, and beamforming IC become available into the commercial market only about a year and a half or maybe 2 years ago by several different providers. Mostly they are CMOS-based electronics, and they are mostly operating still in a mid and low power range up to about 2 watts, but still there's a requirement of thermal management and cooling feature to be co-designed with interconnect and routing, as well as the microwave features for those package, which brings a new interesting challenge for us for heterogeneously package those electronics efficiently using additive direct print technology. Most of the beamforming IC can drive each one of them 4 channels, which means they can drive a 2x2 antenna array. If you want to scale up, you can do the tailing to scale up into a bigger system, which is exactly what we plan to do here. The potential benefit of laser-enhanced direct print additive manufacturing for doing this is obviously incorporate multi-material that you need for dielectric and interconnect metals. And also, as you can engineer their property by infill ratio or using a composite we developed in-house to increase the dielectric permittivity. But also, you can use the pick and place to precisely position those electronics. In this case, you may have more than a few for each of the building block unit cell. And also, we can integrate 3D antenna, 3D heat management feature into your package to make it more efficient. One of the previous presenters talked about something more like a porous structure, something more like a microchannel. We're incorporating some of the things like that in our project as well. So, however, in order to do the beamforming IC, they typically come in with many paths, many terminals and ports that need to be either grounded or connected to the supply or some kind of RF signal. For RF, you have 4 RF output, you have 1 RF common to control those. So those have to be hopefully automatically interconnect to in your printing technology. And also, you have also a concern that you have to deal with mid and high power, so you have to do some kind of thermal management necessarily. And there's no guideline or fabrication, processes developed, particularly for such a complicated electronics with potentially up to 100 interconnect just to routing to one single IC. Not to say you have to build multi-layer for digital RF and other separation purpose to make it even more complicated. So we have explored initially analog device ADR beamforming IC at X-band by one of my graduated master student thesis work. Then later on, we're exploring an Ocuwave 26 gigahertz circuits beamforming IC currently. So this is the early work by the master thesis students. And basically, as you can see, this is the cavity left for the beamforming IC. In this particular design, we also incorporated 4 additional RF switches at the X-band frequency range. The beamforming IC can work between 8 to 16 gigahertz, but our target operation frequency due to the design target is from 9 to 12, 9 to 11 gigahertz. In this design, we're actually still using the widely investigated dielectric, in this case ABS, and CBO28, a silver ink based silver particle based ink for microdispensing to make those dielectric layer and metallic layers. We're still doing very basic heat curing using the traditional technique with very minimal intervention by laser. I don't think we even have to use laser processing for this case. As you can see, we tested the beam steering for such a antenna array, and we achieved the anticipated gain of 15 to 16 dB for the antenna array gain, and the total package loss can be up to about 6 dBm. I can explain that in one of the future improved design cases, somewhere between 3 to 6 dB if you also consider the losses interconnect with the connector, as its frequency is typically anticipated for this type of package. Obviously, one of the downsides for such a design was also all the digital control line and electronics was connected in a very not very robust and very improved design method. That's one thing we're also trying to improve upon in the current study for the high frequency beamforming IC package. But at the time, we already explored co-design and simulation using HFSS ANSYS to jointly consider EM radiation. In this case, we're investigating such a phase array without putting any heat sink that could potentially adjusting the radiation pattern again. We're adding a heat sink to the back, we're adding heat sink to the front. Due to this is the master thesis project, we didn't have time to explore a lot of other more advanced thermal management features, but we did investigate the intervention between the heat management feature and your EM property for your system. As you can see, this is simulated, this is measured. We obviously have ability in lab to use infrared camera along with thermocouple and other thermal sensors needed to measure the temperature distribution of the package. As you can see, this is the shape of the heat sink. I believe this is on top of the package. And then you can see the maximal temperature during the test that we ever reach is about, I think 77 or 72 degrees C. As you can see, before and after package, we compare the gain of such a beamforming IC at I think one of their mode. I'm not remember this is transmit or receive mode, but as you can see, if you're doing the package design right, you can maintain pretty much the same reflection coefficient impedance match across the board band as anticipated. In earlier work, even than this, we're able to incorporate a printed via hole array as a thermal dissipation feature. In this case, you don't have to use a commercial heat sink. You can just distribute it, those features as a heat sink tailored based on the density of your heat distribution with your package. This is ANSYS simulation, but it also measure the temperature as a function of the power driven that PA. As you can see, they're matching pretty well. So we're doing more this kind of design nowadays in order to get to a better handle, better trade-off between thermal aspect and EM properties of your package. So Anoki Wave is a new system we recently adopted for beamforming IC. We started with a QFN package. I don't think this is our limit. We can still using any package or potentially unpackaged circuits if we ever need to. But this package comes with 48 leads. I think most of the leads need to be interconnected. I will give you an example. You'll see it on the next page. And this one operates in the RX and transmit mode. And one of the things that we actually spend a lot of time to figure out is the SPI interface require you to send coding to control the operation of your beam steering IC, and also to operate in different mode, transmit, receive, and changing the phases, amplitude of each of the channel. So we built a separate board for those control electronics signal coding sequence to be generated. This is the fabrication process, briefly starting from printing a dielectric base, mostly for making your package robust. Then we put in the ground plane, a cavity to embed your beamforming IC. Most of the RF and digital control interconnect were routing on the top. With the header pins on the side, mostly feeding those SPI signal and the control signals. The 4 RF on the side, one are common on the opposite terminal. As you can see, that's a layout. We tested the beamforming IC, and first we evaluate the temperature property of such a package with the insertion or addition of the heatsink embedded on the back. This is 4 RF terminal output, and this is our common. You can receive or you can transmit to this common terminal. And then this particular package in the transmit mode can consume and dissipate up to about 1 watt of power that you need to thermally manage in your thermal management features. And the size of the heatsink we incorporate is also reported here that we directly added into the package. You can pick and place, or you can manually position that into your system. The beamforming IC have an interesting feature that can, in the real time, reporting the temperature on the chip back to the SPI coding. You can use that as a way to help you continuously monitor the operation state of your package as well. We're currently still working with more advanced thermal management feature to make sure we can most efficiently using the space, the 3D space, 3D volume to dissipate the heat, or not have to use commercial heat sink design, which may not be well tailored for the distribution of heat over the IC in our case. So this is test performance. I want to quickly mention, I think we're one of the earliest groups that ever successfully additive manufacture, package, and tested a beamforming IC. And obviously, this device is anticipated to have a single pass gain of 18 dB. The coherent gain, if you're operating in a phase array fashion, is a single pass gain plus 12 dB. So you can achieve about 30 dB of gain. For most of the mid and short range communication, this is sufficient to achieve the typical link budget you anticipated. This one have 5 bits of phase control, 5 bits of amplitude control. We obviously tested the 32 state of the attenuation of the amplification. We also tested the phase shift bits. They're actually pretty decent across the broadband frequency, in this case from 24 to 28 gigahertz. Anticipated operation range is slightly more narrow than that. We also tested how this device behave under different phase bit in terms of the gain of that setting, and it was pretty constant, better than the phase shifter design I was referring to in early packaging attempt. Okay, so switching gear, I still have 2 little topic to cover, so I want to start accelerating a little bit. I guess I changed all the movie back to the figure. This is why they're a little bit they're not moving anymore. That's okay. So in this case, we're starting to move gear to talk about heterogeneous integration of electronics. In this case, we have sometimes in-house designed MMIC that is naked chip without a package. We want to introduce printed plastic as a hosting package, similar to an early on project by Doppler heterogeneous integration, where they used high resistivity silicon to incorporate different technology IC into a common carrying substrate. In this case, our carrying substrate can be printed ABS, printed PEEK, printed thermoplastic. And then we're putting a housing on top. As you can see, the housing does a very sufficient job of hermetically protect the IC from moisture and from liquid as well. Then we're feeding all the lines to it as needed. This was a movie to show how the housing was printed in the real time. You can form a dome shape without have to do additional process. You basically, making a net on the top, and then you can make the net mesh more denser. Then it will become a hermetic dome shape package on the top. So this is particular design that actually tape out by a student in my class, and I teach them to at the time using Quovo, one of the 0.5 micron gallium arsenide MMIC design kits to design their circuits, and they all have to finish this design as a final project. The best design get a chance to be tape out. This is one of the 2 best design that got a chance to be tape out. The design we're working with is called traveling wave amplifier. So basically have a very broad band, anticipate to operate between 2 and 20 gigahertz. Obviously, you can see the simulated and measured performance are matching very well. This is also one of my incentive. If we can pushing towards in additive manufacturing society, some standardization of the process, some library of major feature rear hole interconnect and probe pass feature design, make them scalable into a foundry design kits like library models. Then we can let other people using our design kits and design their package, and we can then finish the package, hopefully getting similar kind of comparable performance measure and simulated for them. This is the, for example, noise figure for the low noise amplifier. As you can see, they also match very well. Okay, so once we're able to test in the circuit by direct probing it, we want to put it into different type of package. One of the traditional package is a QFN package with wire bonds. We mount this thing onto that package. There's a pin on the back that can interconnect to a board, and then we wire bonds. We put in that. As you can anticipate, by wire bonding, introduced inductance in series. The path introduced capacitance is basically low pass filter. By packaging into such a housing, your bandwidth performance is entirely distorted, cutting down by this low pass filter behavior. But if you direct print interconnect to using the additive manufacturing, we're able to more largely maintain the 2 to 22 gigahertz bandwidth of the circuits with very minimal losses. In this case, we tested interconnect. They're presenting a loss of 0.1 to 0.2 dB per millimeter, depends on the frequency range of operation. And we achieved broadband impedance match. The return loss is also very good. To push forward to the higher frequency, we want to understand what limit us to go even higher. In this case, we're targeting 170, 110 gigahertz as a frequency limit, so we can package the real millimeter wave electronics and front-end demonstration at those frequencies. If you're looking through all the models for microstrip, coplanar waveguide, grounded coplanar waveguide, the guideline tells you there are several parameters you can tweak. The dielectric constant, for example, the height of the substrate. You cannot change the speed of light, you can change operational frequency. But this critical operational frequency tells you in the desired mode, a quasi-TEM, you don't want other mode to appear at frequency within your operational range. So that's most effectively done, we later on learn, by shrinking the thickness of that package layer, bring the ground plane closer to the surface metal transmission line features. However, that's a cost of also increasing the dielectric losses. More signal will propagate into the dielectric layer. If your dielectric is lossy, then that can adding additional losses to it. So it's mode-free operation trade-off with the losses per unit length. But also, if you can finish very well with very minimal surface roughness, you can also positively impact the losses in that way as well. Getting a better cured conductor layer would also contribute to this, obviously. So here's another slide, quickly show some of the design parameter. The structure you can most reliably work with at very high frequency turn out to be grounded, the CPW showing to the right. You can work with coplanar waveguide, but you have to carefully design the geometries, the gap, the line width, and other features. It shows you the guideline that we figured out and published in one of the recent transactional microwave paper. As you can see on the next page, by following those rules, you can really achieve a grounded CPW that can have a good return loss below about 15 dB up to 250 gigahertz. We measured up to 110, and we actually have measurement up to 170 gigahertz. So this circuit performed very well, interconnect, and we also compare different interconnect features, even with a gold standard calibration substrate, which have aluminum substrate with gold layer on top. We are actually achieving comparable loss per unit length across the range of 0 to 110 gigahertz. Good return loss as well. But overall, I will show a number of loss on the subsequent part. Around 0.01 to 0.02 dB per millimeter is the loss you can anticipate if you do everything right. To break apart upon that barrier, there's a few things that you can do. One of the things is to getting almost perfect metallic conductivity, getting very perfect surface finish, and some of other things I talked about on the previous page. This is the process we show how to embed the in-house designed MMIC, that is low noise amplifier that we tape out this case with OMMIC. The circuit work between 75 to 95 gigahertz as a broadband low noise amplifier. And we started by printing the housing substrate, making the laser cavity so it can be precisely matching with the MMIC chip size. Eventually, we develop a technology, you don't have to do this anymore. You can refill the cavity surrounding to make sure you get a pretty good groundation for your interconnect to run over. Most of the system nowadays have precise alignment down to about 10 nanometers, so pick and place can drop it in there without a problem. We later also explore one of my students how to print capacitors so you can avoid using bypass capacitor on the site. You can get rid of them instead of direct print those capacitor as balance line or feed line, which serve the role of knocking out noise from the supply source. So supply noise suppression can be done with printed capacitor nowadays as well. This is the package performance. As you can see, with without packaging, direct probing shows the right curve. As you can see, the loss between the two with without package, which introduced all the probe transition interconnect here and the transmission line here. It's about 3 to 5 dB at 100 up to 110 gigahertz. And also we maintain the broadband impedance match for this low noise amplifier as well. And we got a loss of interconnect of 0.03 dB, and which is referring to that wire bond replacement directly interact with the path on the chip. And then we have transition losses that is fairly low, and we have good model for those as well. So later on, once we're able to do that, we start to explore how likely we can use the same technology to demonstrate a real operation system. This case is RF front-end transmitter, RF front-end receiver printed on the same housing and with a dipole antenna, simulated link budget, and all the fitting and everything's in there. This is still under publication preparation, so I couldn't talk too much into the detail. But we take care of all the reference calibration, so we're able to report to you with without package. The dirt S21 is the losses of the package, which is very, very minimal, down to about 1 to 2 dB. We also able to match the reflection coefficient for all the pores by carefully model design and having a model built for the packaging element in order to ensure that. So compared to other packaging society report at a similar frequency range, 110 gigahertz, we're right on par with them in terms of loss per unit length for metallic interconnect. Some of them are using traditional multi-layer PCB, some of them using aerosol jetting, some of them using other printing technology. And the losses vary from 0.2 to 0.77 dB per millimeter, which is okay for a short interconnect. But if you want to go further in frequency, you want to further reduce the losses, you want to travel in a longer distance with your ribbon-like interconnect, for example, from chip to chip, then you want this loss to be another order magnitude of 5 times lower. And there's a solution for that. That's the next topic. So let me check on the time. So I'll quickly run through the last topic. This is more additive traditional 3D manufacturing, but we basically propose to make dielectric waveguide, which in many cases rely on total reflection, the electromagnetic wave bouncing at the interface between the high K core and the low K cladding layer of this dual layer dielectric waveguide, which behave like optical fiber to allow electromagnetic wave to propagate. But obviously, the theoretical background behind it is more complicated than that. You have to look at in the Z, Y and X direction, all the operational mode. You have to do the mode matching, E-field matching in order to drive it by even a metallic waveguide. You may have to do taper structure into the metallic waveguide to make sure you have a good transition of the signal launching into the dielectric waveguide. We started by numerical model and electromagnetic simulation, the on-site frequency for different mode of the dielectric waveguide. We want to operate in between the first and second mode. In this region, you have a single mode operation, so you have the minimal losses as a result of that. Obviously, you can do more. You can use the multi-line method. You can use matrix conversion. You can use de-embedding method to actually calculating the propagation constant of that transmission line. And then you can learn what is the loss per unit length for such a structure. You can get rid of the radiation loss. This red curve mostly showing you the radiation loss, as you can see at the frequency below this frequency before the cutoff frequency. You have a lot of signal getting out of this dielectric waveguide radiated, not coupled and fitted by the metal waveguide feed. And then you have other losses. For example, you have dielectric loss, which is dominating the rest part of the frequency. Adding the two together, you have the total loss. But basically, we get to a range of 0.02 dB millimeter of attenuation, which is about, again, an order magnitude lower compared to all previous report with metallic interconnect. So you can make your line 10 times longer, you'll still have less than a dB02 losses as a result of that. So these were movies I replaced to reduce the file size. But anyway, otherwise you will see some laser machining. At the time when we started, we're using a dielectric core from microlaminate to be the core of the dielectric waveguide, so we can start exploring. We're additive manufacturing the cladding. We actually play with infill ratio to reduce the dielectric constant of that if needed, and we can enclose it to make your dielectric waveguide. In this case, you're still feeding them by metallic waveguide feed. Eventually, we also replace that by other in-house design transition features. Looking at this particular structure with without cladding, our invention is to adding a cladding layer into the traditional dielectric waveguide, which tends to be a single core. There are several benefits. One of the benefits is we can tweak the on-site cutoff frequency to make signal band even wider by about 2 dB more compared to the traditional design. If you're putting your hand closer to your dielectric waveguide with cladding, it will be less sensitive to the surrounding. You can put a regular silicon wafer. This one will see a distorted signal. This one will be immune to that for the large part. But in order to fit it into metal waveguide, you have to match impedance by matching this distribution of E field. And from your metallic waveguide, you have to match geometry. You may have to taper in order to make sure you have the best transition. We did all of that. And as you can see, traditional waveguide without cladding, if you bend it, you're basically changing the operational band of your system. But if you're putting a cladding on top, you can have a pretty sharp bend. Your operation of the signal bandwidth was largely returned, and your in-band attenuation is also not distorted. We also make one of the early design tested in the D-band up to 170 gigahertz. Obviously, we didn't capture in our model some of the losses. That's why the simulated loss was lower. So potentially, this largely come from either the transition in the radiation because imperfect alignment at such a small feature size, or the dielectric losses that we didn't anticipate from the dielectric material. In this case, we're using a high K dielectric core. So I already said this, so just skip that. So in order to make such a design into a radiation pattern, we can also make antenna, no problem. In this case, the left-hand side is a taper section you feed into a metal waveguide. You can have more than enough parameter to engineer to optimal radiation characteristic. In this case, we also design one with printed 4.5 dielectric core and a low K cladding surrounding it. We're comparing performance with without cladding. As you can see, without cladding, you're getting lower antenna gain. And with cladding, you're getting improved antenna gain by 3 to 8.5 dB, which is significant. More importantly, you can also engineer your half power beamwidth by reducing it by 22 degree from 40 to 18, almost reduced by half. So you have more pencil beam-like radiation pattern if you're putting on this cladding. Removable, by the way, then you can compare the performance with without that. Interestingly enough, we can also introduce metallic features into such a print in order to give you an interesting design performance. In this case, this period metallic print introduce a band reject filter within your operational band. So if there's interference next to your antenna radiation band, you can get rid of that, potentially up to about 20 to 28 dB, as we found out. So you can design the feature by changing the critical feature size. This is the length of the metal strip. And then you obviously can tweak and shifting that rejection band center frequency. You can also improve the peak gain of the antenna slightly as a result of that. Similar effect, if you're putting down those periodic features, you can also tighten your half power beam width a little bit, less severe compared to sliding on low K cladding, but that make an impact also on your center gain of your antenna. And then since we can do so within radiation feature, we can also introduce the same feature into a dielectric waveguide. In this case, you're introducing band rejection filter. Again, knock off the signal you do not like to see. You can engineer the line and gap to shift this rejection band. You can get up to 28 dB of rejection as a result of this simple design here. Most importantly, we later on started investigating. People may be concerned about the being able to operate the dielectric waveguide interconnect with we're still not with IC because you're still using metal waveguide, which is bulky, expensive, and all of that. So that's why we started developing microstrip like transition features. Then you can transition into a connector or transition into IC on this end from your dielectric waveguide. Let's say I have a dielectric waveguide that's 10 centimeter long. At the end of it, I built this transition connector. As you can see, by connecting back-to-back such a radiation structure, we're able to test it and verify the transition loss is about 0.5, 0.6 dB. Metal waveguide can achieve close to 0.1 or 0 dB of transition. So this is still not as optimal, but it's getting there. So we use that feature to feed the antenna. As you can see, antenna works, and with without cladding, you get about 4 dB of difference in the radiation gain. You got slightly different half power bandwidth improved because of the cladding, the double layer design. And we measure the antenna gain, the reflection coefficient for such antenna fitted by this feeding structure. And this end, you can fit it into MMIC as a driver, or your beamforming IC if you need to do that. Now this work is possible without the hard work of my students and without hard work of the student in our research center. One of the proud points I always want to mention is that in the recent years, our students been getting very prestigious awards. One of them is Micro Syrian Technology Fellowship, which they give out globally about 12 awardees every year. We've been getting that continuously for 6 years between 2010 and 2018. They have one student carry that to another university, and then pandemic, we didn't have a lot of students apply anymore. So we need to get back on track for that. That's it for today's presentation. I also want to show you this interesting picture. This is the N-Scrape printer. One little surprise we found out is that after everything's ordered, prepared, our service elevator was able to handle the weight, just not able to handle the size. So we have to break our neighbor's window to push it to our lab. Okay, that's it.
Okay, Professor Wang, thank you for this enlightening presentation and extensive and quite illustrative of the work that you have been doing and so on. I have a couple of questions that have come up during your presentation, and let me address them. First, when you look at all these properties, how you compare basically the thickness of these layers to what is used in traditional PCB industry? People say in the PCB industry for the microwave, basically you use a thicker copper, and basically with that you attenuate some of the issues related to roughness or imperfections in the conductive material.
Okay.
The skin depth issues, basically. If you can address that, we'll appreciate that.
Okay. I think we are one of the earliest groups that study the high frequency up to 110 gigahertz or 170 in some cases. The skin depth at that time is already not comparable to the thickness of your typical copper cladding layer or typical printed layer. I have to say most of our printed metal layer per layer thickness is around about 20 to 25 micron. Same is true for our dielectric layers, but we have a way to use micromilling to thin them down. We can use laser to thin them down. For most cases, to get to high frequency, one of the key features you need to make sure you have mold-free operation is actually the thickness of your dielectric substrate in between your metallic feature microstrip and ground plane. So, and also in many cases, how well you can incorporate it, those weir holes, and how well you have a model for those become very, very critical. So we automate all the weir hole printing and trimming precisely the lines needed by laser. All of those seems to make a bigger impact in terms of impedance matching losses compared to the actual conductivity. In many cases, we found out we actually getting in many features better RF conductivity at our frequencies comparing to DC conductivity extrapolated. Obviously, we have to carefully get rid of the transition loss at the port, either probe or connector to say so, but that's what we found out. And also, in many cases, the ink we deal with till today, because we're still referring to works mostly presented as 3 years old, 2 years old. Back then, I don't think we sufficiently cure those metallic ink to the extent they're actually centered. They're mostly just dried powders. Even in that case, I would say the roughness of the substrate, roughness of the metallic layer make the drastic impact comparing to the thickness of the layer or their actual conductivity. That's our experience.
Okay, I really appreciate it. I think with that explanation, you even covered the other question that was how the silver sintering affects the performance compared to copper. So I really appreciate it. And right now, let me just double check to make sure there are no other questions. In one of your slides, you indicate the laser sculpture recess as or well in a 3D printed substrate antenna, the board. The question is the well in near net condition printed into the substrate or cut out of the uniformity in the uniformity printed that the substrate creates?
Okay, we have different way of doing this. Our early student tried direct print, basically printing the thermoplastic housing or enclosure by leaving a cavity in the middle of it. Then we found out the precise accuracy. If you want to directly snap your IC with a less than sometimes 5 micron gap on the edge, it's going to be pretty difficult to directly print a leaving a cavity there. And the flat back is important for making a ground interconnection as well. Then we realized you can do micro milling, you can do laser machining, you can at least do those decoration after pre-left cavity. And then nowadays, we found out that you don't have to engineer them to precisely on the edge of your IC. You can refill them by another layer of material. We have several material candidates that we work with that actually work extremely well, potentially better. You can also make them as enclosure, almost like a ramp on the side of your IC, make it easier for you to interconnect.
Okay, this is great. So Professor Wang, I really appreciate it. This was the last question that came through. Great presentation. And I would like to thank all the morning speakers that presented some great papers and so on. And we're going to take a break now, 45 minutes, and continue in 45 minutes with the afternoon session. For some will be the late evening and some others may be early morning. Okay, so thank you for so far, and we'll reconvene in 45 minutes. Thank you. I am on mute. Okay, good. Hello, everybody. Welcome to continue the AME Academy now with the second part of it in the session. Thank you. So we'll have several additional presentations now. And we're going to start first with the presentation by Melanie Gutierrez from Florida International University on integrated wireless neural recording system with additive manufacturing. And Melanie, the stage is yours.
Thank you, Chaim, for this. So thank you, Chaim, for the introduction. Let me start sharing my screen. You able to see it? Perfect. So, yes. That's great. So I will say again, my name is Melanie Gutierrez. I'm a PhD student and also a graduate research assistant at Florida International University. And today I will be discussing the more recent results that we have obtained with our technology in this presentation titled Integrated Wireless Neural Recording System with Additive Manufacturing. So neural implants have the potential to early diagnose neurological disease. Let's say that we have the potential to improve the well-being of patients with Alzheimer's, epilepsy, and other neurological disease as Parkinson's. So in this sense, the current available implantable systems are divided into wired and wireless. The wired systems are highly invasive and they require external connections. This hinders the possibility of having a normal lifestyle and also the comfort of the patient. The recordings are limited to clinical setting. This also can endanger the patient since there is more possibility of hazardous particles as well as more infections. So on the other hand, the wireless system requires power source that can generate heat. So this can also risk the neural tissue. There are other wireless systems that has also a very low sensitivity antenna and chip separation. That's why our group, in collaboration with Ohio State University and Arizona State University, has developed a lower power wireless system that is minimally invasive and can record neural signals. So our system is known as Wireless Neurosensing System, WINS, and principally address all of these concerns that the available recording neural system have. This collaborative work has led to a minimally invasive, fully implantable, wireless, and also batteryless system that can record any kind of neural signal. So first, we have proposed this system with two principal components. So an interrogator and a subcutaneous implant. The implant will be located below the skin, while the interrogator will be located just above the skull. So this system, this unique technology has realized the operation principle in the radio frequencies communications. So in this sense, we utilize a carrier signal that is generated in the interrogator. We send it to the implant where it will be mixed with the neuronal signals. This modulated signal is transmitted back to the interrogator where it's going to be demodulated, processed, and visualized. So we can, after it, diagnose which kind of disease can the patients have. So in this sense, let me explain a little bit more how the implant works. So we have a passive impedance matching network that is composed by a BG2 transistor. This BG2 transistor acts as an impedance buffer. This is extremely important since the available electrodes that we have commercially have orders into 220 kilo ohms. So in this sense, with this impedance buffer, we can match the impedance of the implant to these high electrodes. So after that, we utilize a modulation circuit, which is composed by a Schottky diode. This Schottky diode has two purposes. First, we rectify the signal to sell via the BGT, and second, we mix the carrier signal with the sense neuronal signals to generate the modulated signal that will be transmitted back to the interrogator for further demodulation. So with a clear understanding of how our system works, so I would like to go to a summary of how we have proposed and get to the point that we are today. So we can further compare our system, like the one that we are proposing, with the ones that we have worked before. So in 2017, we proposed our system with a miniaturized footprint of 8.7 times 10 millimeters square. This system were using a TMM dielectric, which has around 12.2 permittivity. So this was great, so we could use a miniaturized system. However, this system does not use a multi-channel. In specifically talking about multi-channel in recordings, neural signals, we normally use more than one channel. So we can sense the signal and then process it together in the sense that we can average and have more than one channel. In this case, in Shen, in 2018, he proposed a multi-channel. He utilized optical communications, utilizing LEDs, photovoltaic cells, to further choose between the different signals of the multiplexer that it was implanted in the system, and this way having up to 8 channels. So 8 channels is still a little bit low, but we can scale. This system is scalable, and we can go even to 32 channels or even hundreds of channels. We only have to add more LEDs. So the limitation of these two systems are that there was no impedance matching within the electrodes. So this was only utilized for 50 ohm like kind of electrodes, but this is only usable for in vivo operations within the lab. When we go to humans, we definitely need utilize the electrodes that we have available commercially. So we needed to upgrade to an impedance matching network. That's why in Shen in 2019, he proposed the implant utilizing the transistor as a buffer impedance. At the moment, he designed using Rogers for 2003C. He designed the system to have the electronics and then attached to the antenna. Of course, this system was a little bit big. So the goal for me is to try to lower the footprint, and also to lower the minimum detectable signal until 200, until 20 microvoltage peak to peak, to be able to recover all of the neural signals. So in this is, we propose to use a multi-layer system, so we can have different, so we can have a smaller footprint, in this case of 45 times 29 millimeters. In this sense, we propose it this way because the actual goal that we have at the end is to make a multi-channel. So for right now, we have the proposed system of 45 times 29 millimeters square, and then we can place the LEDs accordingly, so we can have the multi-channel. With this said, let me explain a little bit more how we design the system. So first, we have the different layers in the brain model. We have white matter, gray matter, and we utilize the different permittivities for the scheme model based on a work that was done before, so we can actually chemically modulate and evaluate the system. In this sense, we utilize a biocompatibility by introducing a PDMS in the system, like quadding with it. And then we implemented the antennas based on an EPASH antenna. We utilize an in-house genetic algorithms that it is programmed in MATLAB, and then we can optimize every time that we choose to change the size of the system. We can optimize the transmission coefficient between the implant and the interrogator, and we have done this with MATLAB and HFSS. Then this antenna has a dual band operation that is between 2.4 and 4.8 gigahertz, and it can also get until all of the F neural signals. That means between 10 hertz and 5 kilohertz. So first, we proposed the system using Rogers 403C. And here we can see how the transmission coefficient improved regarding the other models that I explained in the at the beginning of the presentation. So we have here that our system was improved by around 4 dB regarding all of the different systems that we have in the past. So once that we have this transmission coefficient in the HFSS, we go back to ADS, and then in ADS Keysight, we do the electronics and try to make the best dual band matching network. For that, we utilize an open and short circuit stop that regulate and try to make the best performance and lower the system loss. Doing that, it is, of course, we go to the goal that we have, that is go to 20 microvoltage peak to peak. That means that in the system loss must be less than 12 dB. We kind of have very low loss in the propagation loss. So we also made the system that our mismatch loss and the convergence loss was the more simplistic, like the minimum possible. So after optimizing an ADS Keysight, then we can see how the power received at the interrogator is around minus 120 exactly for the co-simulation. When we compare with the simulations are a little bit further away, like let's say like around 8 dB. However, it's still possible for us to recover the signal, since the receptor, the interrogator, and all of the demodulation circuit can actually can actually understand all of the signals below minus 120 dBm. So in this sense, we expected that our signal can go to 20 microvoltage to peak, and we were able to recover. So all this work was done with Rogers again, and we can see how the specific absorption rate is also below the standard. It's around 0.17 grams per kilogram, watts per kilogram, sorry. And then after this, we actually started thinking about how to make the system and fabricate it in the easiest way. And we started doing some simulations using the AME technology and using the dielectric specific for nano dimensions. So we started doing some of these, since the advantage that additive manufacturing has, that we of course has better system loss and all of that when we actually fabricate, and the fabrication will be more accurate in terms of when with the co-simulation. So, and these are the results that we obtained. So here at 2.4 gigahertz, you can see that again, the system has around 4 dB better than the previous one, and also much better than the previous one, also in the 4.8 gigahertz band. Then if we compare the AME dielectric with the Rogers dielectric, we can see that they are very similar. Kind of the same 0.9 dB that we lost in the 2.4 gigahertz band, we also gain it in the 4.8 band. So said this, we continue to do the fabrication with additive manufacturing. For that, we still use all of the system. The system ADS, like all the optimization, and we get that again our signal receive a 4.8 gigahertz plus minus the frequency, the neural frequency we have that is around minus 120 again. So it's kind of what we were expecting. In this sense, we also compute the specific absorption rate, and this one was again below the standard, and this allow us to actually recognize that the system has a very low power transmission. So that's what we really want. And finally, this is how the fabrication looks. We have the two EPASH antennas. One is for the implant, the other one is for the interrogator. And then we just place in here the different diodes and transistor. And we can see how we smart the footprint of our previous device, and also we improve the sensitivity and decrease the system loss. So this is the first fabricated prototype using the multi-material, multi-level Dragonfly, and actually I will show next all of the measurements. So first, let me explain how we proceed to the measurements. We have in the lab a waveform generator that emulates the neural signal that's set between, let's say, 10 hertz and 5 kilohertz. We also utilize a power supply, so we can supply with power our demodulation circuit. And then we also have the spectral analyzer where we are seeing the peaks where the frequency, the neural frequency should be. And then we have the implant and interrogator. We also have the signal generator producing and generating the 2.4 gigahertz signal, the one that is the carrier. So then next, our first test was to test in air, how it will work our system. And then we can see that at 100 microns, we can actually see the very nice peak of the frequency. And then we can also vary over all of the different frequencies between 10 hertz and 5 kilohertz and obtain those nice peaks of signal. Now, let me just say really quickly that this big peak that we have here is the 4.8 gigahertz signal. And then these other to the left and right are the ones that we have actually to demodulate to get the neural signal. So after that, we also wanted to check if our system has the ability to get all of the different kilo ohms of electrodes. So we, I cannot see well here, but yes, exactly. So we go here and we have again demonstrated that our system can even do 50 ohms or 33 kilo ohms. We actually, this test was done using some resistance. In the future, what we want is to actually put the electrodes. So after that, we went to our goal, which is to measure using some kind of tissue, emulated tissue. So here we have utilized ground beef. So we utilize ground beef. As you can see here, the permittivity and the conductivity of the ground beef is very near to the actual skin. So we utilize this ground beef to measure how it would look like in when it's in a human tissue or something. In any animal in general. So, and as you can see, of course, we can see the peaks and we can see the peaks. However, at 20 microns is like a very small peak. When we take it, we have to further process it. There's more filtering stages and amplification stages, but we are able to recover it. Next, I want to talk about the vision of our project, since we really have a lot of different things that we are working on. So our system will start by having all the implementation that we have, like implant, interrogator, and the RF station. So the RF station is very important because it has all the demodulation circuits, so that it has amplification stages that it could actually travel into the data analysis part where we can actually diagnose the patient. So this this kind of system has can revolutionize the neural recording, since it could be working for research, for monitoring, for diagnosis. So the idea is that in the future we want the interrogator to be wearable, to be, let's say, in a hat or in a cap, or even in a patch in the body. So or even wearing any necklace or watch device, so that the interrogator doesn't have to actually be up the scalp. So I want to talk about some limitations that we had on some proposed solutions that we have done using AME technology. So by using PDMS, we have actually seen that this coating with the PDMS generates a non-regulated thickness. So as you can see, it can vary from 0.4 until 0.8. And actually, if we use AME technology, which is being demonstrated from European doctors, that it can be used for biocompatibility. So if we use AME technology, then the dielectric, then we will have a constant cohesion and biocompatible cohesion, and that would be great because we actually simulated like this. And I did some simulations between the using the dielectric and nanodimensions, and also the dielectric for PDMS, and then we get the same transmission coefficients. So other real quickly, other different things that we want to work on is the actual final goal of our for our system is to make a multi-channel, and even until 5 different LEDs. That means having 32 different channels. So what is the problem that we have right now? So the available PV cells are between 23 and even more, 23 per 8 millimeters squared. So we are working on making an appropriate PV cell. The PV cell that was 5 times 6 millimeters squared is now discontinued. So we are working in actually making the PV cell. And once we have this, we will have only to put the LEDs in our system and have the multi-channel operation using optical communications. After these other different problems that we have faced and challenges is that we work in the reactive near field region, and we also will always have the head tissue losses. So we want to elaborate a phantom, not using the limitations of the ground beef. We actually have elaborated already. We just didn't have time to test it before this presentation, but we have elaborated a head tissue that has the properties of the human tissue. And also we want to include an automatic signal recognition using machine learning algorithms. This process has been done already. We just have to integrate it with introducing microcontrollers and everything to the system. Also, other challenges are that our demodulation circuit is very big. So we have addressed this by using some X microwave components, which does a RF station very small and half the size and weight was reduced. And where of course we want to address the miniaturization, we have seen other hypermittivity substrates, and we have been working to see if AME can also work in some higher permittivity substrates. And then finally, the conclusions. So we propose a packaged wireless and batteryless brain implant. So this is matched to the high impedance commercial electrodes. We improve the antennas transmission for 4 dB, and also we utilize a very small, like a 52% smaller footprint between 45 times 29 millimeters square. And then also we have improved the sensitivity by using AME technology to 20 microvoltage peak to peak. Future wall, as I said during the presentation, will focus on miniaturization, including the multi-channel recording, which is also already in progress. And then, of course, we will do in vivo testing in rats. And then, of course, and we will have the FDA approval to make the biocompatible using AME technology. So thank you very much to my co-authors, Professor Volakis, Satish, and Carolina, and also to all the staff in Nanodimensions. This is been great to all the insightful discussions that we have had, and thank you for the fabrication of the samples. Waberman, Ryan, and Hein. So reference, and thank you. Here are some questions.
Okay, thank you, Melanie. This was very enlightening and all that. There is one question that came up. I don't know if you can answer, but the question was if there is any industrial sponsor for this research.
We have an NSF sponsorship for this research. Yeah.
Okay, so it's NSF, another
NSF, no company. Well, yeah.
Okay.
Not that I'm not knowledge.
You're aware.
Yeah.
Okay.
Sorry.
And then what material are the electrodes that you will use to go into the?
So we have seen different materials. So first we tested it with resistors, only resistor. But the materials of the electrodes that we will use, I think we have one with platinum, and I don't remember the other one. I think it's silver, AG /PT, I think, if I don't remember. Exactly, platinum and silver, I think is a layer. Also, very important, we have tested in rats all the previous system that we have. We haven't tested this yet because we are in the process of including the multi-channel, but we have tested in rats, so we are very near to the FDA approval for more testing in humans. Thank you.
My apologies, I had to mute you. Could you please unmute? There was the echo.
You muted me. Okay. So the next speaker is future doctor, soon to be, Yuri Piro from University of Massachusetts at Lowell. And he's going to be talking to us about the materials development for additive manufacturing and printed electronics, RF and millimeter wave applications. Yuri, please.
Okay, thanks for the nice intro, and thank you for having me. As you just heard, I'm going to be talking about materials for developing some of these RF and microwave applications out of additive manufacturing. So my name is Yuri, and I'm coming to you from the University of Massachusetts Lowell, where we have a partnership with Raytheon. That's why you'll see both UMass Lowell and Raytheon on top of all of my slides. So with that, I'll talk about our research institute very briefly, and then I'll go into some of the research that we're working on at the Research Institute. So collectively, our research institute is known as the Printed Electronics Research Collaborative. And that's because we are very much interested in printed electronics, and to show that we have a lot of industry sponsorship. Within this institute, we have, like I said, Raytheon with a large research interest. So we actually have a co-location model with Raytheon within our research institute called the Raytheon UMass Lowell Research Institute. So with this, we can have Raytheon employees show up every day and research side by side with UML staff, and we can put our heads together and tackle some of the issues that we think are very important to printed electronics. And then also take in some input from other industry sponsors too. You see some of those industry sponsors on the slide. What's really nice about this is these partners are people that are involved in all sorts of different aspects of print electronics, from software suppliers to equipment vendors to material companies to people making the actual devices. So getting together all these people, we can really organize our research thrusts into what we think is the most important area to focus research to advance this technology. With that, I'll just quickly talk about some of the technology we use in our lab. You see on the upper left-hand corner of the screen, that's our lab right there at UMass Lowell. We have the 4th floor of that facility. And in that facility, there's a few different lab spaces. We have a very involved printing lab where we have the high resolution aerosol jet printers that you heard about earlier. We have N-script printers. We have different dispensers. The IDS NanoJet aerosol jet printers. We have pad printers, different SLA printers, DLP printers. So outside of just the printing lab, we also have a very sophisticated modeling lab where ANSYS, one of our partners, supplies us with software to run the HFSS modeling, so we can print parts and then see how they behave, comparing them to the modeling software. We have anisotropic chambers, so we can characterize the antennas that we print on the spot. We also have a very involved materials development lab. That's where I work. And then a lab that has the LPKF assembly system also. So in our research group, there's a lot of different projects happening. There's a lot of different people involved. Like I mentioned, we have these advanced printing processes. Just researching those alone is a whole chore, but then applying those into these novel device integrations is something that we're very involved in. We do technology protection. We do authentication work. There's a lot of work being done with textiles in our lab and wearable electronics. But what I'm going to talk about are the novel materials that we're working on, and specifically the dielectric materials. So with that, this brings me to the topic of the research that I'm doing and I'd like to share with you, and that's the issue of dielectric loss in RF and microwave frequency for these additive devices. So to talk about our approach with this research, I thought it would be best to start with a discussion of this polarization phenomenon. So polarization in a DC field is just culmination of all the different polarization modes a material has. And the polarization modes are just ways that the distribution of charge orients against an applied field. So it's pretty simple in the DC world, but when you switch to AC, you have to start to worry about the relaxation frequency of those individual polarization modes. Now for RF radiation, your applied frequencies typically between 1 gigahertz and 20 gigahertz. And that's an issue because for organic materials, you have the relaxation frequency of common organic dipoles relaxing in that range. So those relaxation frequencies can't keep up with the RF signal, and you have that constant rescattering of the field. And that's why you have losses in that range. So our approach to material development for RF devices is to take those dipoles out of the material. But that becomes a major issue when you think about what RF or what printed electronic materials currently use for dielectrics. So photopolymers are the go-to materials, and the very common conventional photopolymers are typically acrylates or methacrylates. Those are initiated with radicals, and they have huge dipoles. And those dipoles are actually very important for the kinetics of the reaction. They stabilize the radical during propagation. And if you were to start to remove those dipoles to make your material less lossy, you would destroy the kinetics of the reaction. You couldn't form those polymers on the spot. Now, cationic photopolymerization is also very common for things like epoxies, but again, you have the electron withdrawing groups that stabilize the cation propagation, and removing those again really hurt your kinetics. So there's a couple ways around that. One of the ways is you use preformed nonpolar materials, and you just dissolve them in some sort of solvent. There's two big issues with that approach. The first issue is you have to drive off the solvent during curing, and that introduces a lot of stress into the film. The other issue is the viscosity. Typically, those are high viscosity materials. And to get the viscosities down to where you can use high resolution printing, you need to use large fractions of solvent. And a lot of those solvents, to get the nonpolar materials to dissolve, have to be things like toluene or xylene, and those are pretty toxic and hard to use in a manufacturing environment. So there's this big need to make nonpolar polymers on the spot that have this low dielectric constant and minimal processing conditions. And that's really what we've been focusing on. Now, there are some solutions happening right now. You'll see in printed electronics, the polyimide is a common material people use that has a low CTE and has a pretty low dissipation factor. But one of the issues with polyimide is the material has to be imidized on the spot. So you have to heat up your material past 180 degrees. And once you start doing that, you have to disqualify some of the flexible materials that are kind of the most exciting parts of integrating printed electronics in the first place. Another common material people use is benzoyl-cyclobutene, but again, that requires processing conditions that are very long and hot and destroy the ability to introduce flexible materials. So coming up with a nonpolar material that you can form on the spot with low processing conditions and low polarity is difficult, and you really can't use these conventional approaches, and that's what we've been researching. So looking into this issue, we looked at a lot of literature, and there's one field of work that really stuck out to us. And in this work, this was out of the University of Illinois, this group was not making electronic materials. They were making they were looking at different manufacturing techniques for side panels for aerospace devices. And they were using this reaction called a frontal ring opening metathesis polymerization. And this is really cool because if you look at the polymer they're forming, it's an incredibly non-polar structure. It is a bicyclic carbon ring, so it takes up a lot of space. So if you think of polarization being your dipoles per unit volume, you have a lot of free space and not a lot of dipoles. There's also a lot of bonding, so it potentially would have a low CTE. And it does. That polymer is polydicyclopentadiene and has a CTE of about 40 ppm per degree Celsius without any filler at all. So if you look at how they're doing it, they use a Grubbs catalyst and they inhibit it with a trialkylphosphite. Now the trialkylphosphite coordinates with the bottom of the Grubbs catalyst and disables it so it cannot do the ring opening metathesis on the dicyclopentadiene until the material is heated. So by mildly heating, they can activate this catalyst and cure the material on the spot. So this is cool because it's a mechanism that is pretty easy to control. Just with mild heating, you can cross-link this polymer, and they did this by just touching this gel, this dicyclopentadiene gel with a soldering iron, and then creating a reaction wave where the reaction enthalpy is enough heat to keep dissociating that trialkylphosphite from the ruthenium and cure the dicyclopentadiene. They were doing this in an open air environment. So we thought this might potentially be a way, if we can change the rheology, to come up with a low loss dielectric ink where we're just mild heating, we can create this very non-polar, low CTE polydicyclopentadiene material on the spot. So this is the approach that we came up with. Again, just going through the attractive parts of this reaction. That second generation Grubbs catalyst is stable in air, so we can use open air environments. It has an excellent tolerance to heat and contamination, so if there's some humidity, it's not going to slow down dramatically. The catalyst can accelerate with heat and decelerate when it's cooled down. Now, if you look at typical photopolymer formulations, you're using 1 to 2 weight% of your initiator, and that can add losses. But with these Grubbs catalysts, you're using incredibly small amounts, you can actually have this reaction work at less than 0.05 weight% of the catalyst. So that's really not going to feed into your loss the way that the initiators typically do. Now, our approach, we stayed away from dicyclopentadiene up front because it reacts incredibly fast with this catalyst. So instead, we used a 5-vinyl-2-norbornene monomer. And this monomer, instead of having 2 fused bicyclic carbon rings, it has 1 with the preferred norbornene alkene in the backbone, but then it has a vinyl pendant alkene group. And what that does is it allows for an alternate reaction pathway with the cross metathesis, and that's a much slower reaction. So by mixing this 5-vinyl-2-norbornene with the Grubbs catalyst, we can slowly grow the monomer to the viscosity that we like, and then we can add the inhibitor and freeze the reaction. And then with that stable mixture, we can print that onto a heated build plate. So in this slide, you see us doing this on our Optimac printer. And then the heat from that build plate can reactivate the catalyst and cure the polymer film. So this is the approach that we're using to come up with our low loss dielectric ink. Now, just to give you a little more details on this reaction, in this step one, like I said, we take this 5-vinyl 2-norbornene and we mix it with the Grubbs catalyst. You can get a crude sample of this material very cheaply from Sigma without purification. There is a reaction, there is a difference in the kinetics between the endo and the exo isomers of the 5-vinyl 2-norbornene, but we kept them together just to see if we could do this without having to purify these, and it works very, very well. At room temperature, we can mix these with the Grubbs catalyst at a very low concentration and slowly grow this polymer. You can see the NMR here. This is over a 12-hour period of time. This gives us a lot of control over the viscosity of the material. And then we found after 4 hours, we have a very minimal viscosity, but we have the polymer growing to a point where we can freeze it and reinitiate it later. Just to give you another image of the kinetics here, 2 different NMRs. One on the left is a room temperature sample, just showing the slow progression of the 5-vinyl 2-norbornene polymer forming. On the right, you can see what happens if you were to then heat that sample. So this is at the 4-hour reaction interval. We quickly gel the material and form that poly 5-vinyl 2-norbornene. So adding the inhibitor, we weren't really sure exactly how much to add. We wanted to have a stable shelf life when we add the inhibitor, but we didn't want to destroy the reactivation. Like I said, we want to be able to reactivate this onto a heated build plate. So we looked at different concentrations of inhibitor and studied the way that the viscosity changed over a 24-hour period, and then how much reaction enthalpy we could recreate when we heat the sample. So on the left here, you can see the viscosity drift over a 24-hour period. So we tried a sample with no inhibitor. Of course, that jumps in viscosity because the reaction keeps running. And then when you have about 1.8 equivalents of triethyl phosphite per Grubbs catalyst, there's less change in viscosity overnight, but there still is a dramatic amount where you really couldn't process this. The viscosity is changing quickly. We found out about between 3 and 4 equivalents of triethyl phosphate per Grubbs catalyst. We had pretty stable viscosity over a 24-hour period, and even more so with 5. But then taking that 2.1 or the 3.5 equivalents sample and heating it in a DSC, you see on the right here, with the area under these curves corresponding to the reaction enthalpy, we show that we can reactivate this catalyst pretty easily around 60 C. So this gave us confidence that we can stabilize the reaction, print it without having the viscosity drift and having to change the processing conditions, and then reactivate the reaction, cure the material on the spot, and create this nonpolar polymer. Now, the next thing we did was we looked at the dielectric loss. And before I show you how we did that, I just wanted to quickly comment on how we measure dielectric loss. There's a lot of different ways that this can be done. There's a lot of research happening in these materials. So of course, people come up with their own techniques, but there's one really standard technique, and that's with this waveguide characterization tool. So what you do is you collect your S11 and your S12 scattering parameters off of a WR or any waveguide, but for us, because we're interested in the X-band, we use WR90. So that waveguide has a cross section of about 10 millimeters by 23 millimeters. We cure a rectangular prism and fit it into that waveguide structure, and then collect the scattering parameters. With the scattering parameters, we apply, there's a couple of different algorithms you can use, but what we use, because it's very commonly used, is called the Nicholson-Ross-Weir algorithm technique, and that gives us the complex permittivity. So for this technique to be as accurate as possible, we need the sample to be roughly about a quarter of the wavelength. So in our materials, the dielectric constant is typically between 2 and 4. So what that means then is our thickness, assuming that dielectric constant, that frequency, needs to be less than 3 millimeters thick. Because once you're past a quarter wavelength, you start to have multiple solutions with that algorithm, and your uncertainty becomes very large. Now, sometimes fabricating samples that thick is difficult, and because of that, there have been other techniques that people use to characterize dielectric constant. One technique that we use in our lab also is this cylindrical capacitor method, where on the Optimac we can aerosol jet print these different capacitor structures, and then subtracting one size from the other, we can calculate the complex permittivity. but this is a less used technique. The waveguide characterization technique is what's used most commonly. And what's great too is you can easily replace the WR90 with something like a WR62 for higher frequency. And we do that later on in this presentation. So the WR90, like I said, gives us a nice measurement at X band between 8 and 12 gigahertz. The WR62 pushes that up to 20 gigahertz. So to test our samples, we took that material that I showed you, heated it, we poured it into an aluminum pan. We just heated it at 60 C for a few hours, and it cross-linked, it reacted. Then we used a razor to cut that WR90 waveguide structure. We put it into the WR90 and we calculated the dielectric constant and loss. And then we did the same thing for NEA-121, which is a very common aerosol jet. Well, it's not designed for aerosol jet, but it's been used in aerosol jet printing in this additive RF research. We found that our material indeed did have a much lower dielectric constant and dielectric loss compared to the NEA-121. So on here you see NEA-121's 0.02. It's between 0.02 and 0.025 for dielectric constant. Our material was 0.005. So that was really exciting for us. But unfortunately, we really weren't getting the print resolution that we wanted. So this reaction can harden after multiple hours at 60 C, like I showed you in the past slide. But if you want to actually use this in a printer, the reaction doesn't happen fast enough. So to have decent print resolution, you need the material to be aerosolized in deposition head and then cure instantly when it hits the substrate. And if it doesn't, then the material is just going to mobilize on the substrate after printing. The way the aerosol jet system works is when you print the material, you're printing it as an exhaust. So there's a lot of sheath gas coming out. And if the material can't hold its shape and cure it when it hits the substrate, it can be blown around by the sheath gas and you can lose print resolution. And you see that happening in this picture here. Now there's a couple of ways you can get around this. You can do the dam and fill approach where you maybe do something like syringe dispense and create a nice dam structure and then fill in the material. But when it comes to conformal printing or doing any real high resolution printing, this really isn't the way that aerosol jet printing is meant to be, especially for dielectrics. So we wanted to find a way to fix this issue. Now, there's a few different ways that you could try to do it. The first way is increase the stage temperature. So what I just showed you, that stage was at 60 C. Now, in theory, you'd think that increasing the stage temperature would increase the reaction rate. So we tried that. These are all capped on samples. You can see our material is that clear stuff you see printed on top. We tried 60 C, 70 C, and 90 C. And in all cases, the print resolution did not increase with that increase in temperature. In fact, it looks like there was even some sort of rheology change that was actually hurting the printability as we increased the build plate temperature. So that was discouraging. And we thought that maybe it's best to take a step back and look at the chemistry and what we can do instead of just changing the engineering controls. So there's two different approaches that we looked at. Now, in the first approach, we thought, all right, so this material, as we're growing it, we have a lot of these alkenes. The ring opening metathesis reaction maintains these alkenes in the backbone. On top of that, we have the vinyl pendant group. So we could probably do a very simple click reaction. In the click reaction, you take a dithiol and you take a photosensitizer. And what happens is the photosensitizer, in this case, it's a very common ITX molecule. This can be excited by very common UVA radiation. In this case, it's our LEDs that are at 365. And when it's excited, it can abstract a proton from the dithiol. And then those dithiols that are scavenging for protons can react with the alkenes. And what happens with that is it cross-links the system and you end up with this photo-cured material. Now, this works. As you can see on the right, we have really great print resolution when we add this click reaction. But really, in theory, it's not that elegant of an approach because we're adding polarity back into the system. Those thiols aren't that polar, but they're more polar than just the alkene is by itself. So we really weren't satisfied with this approach. And we thought, all right, maybe there's another way we can do it without adding more polarity into the system. So if you remember at the beginning of this presentation, I talked about dicyclopentadiene being the monomer that we decided to not use because it's too reactive. So we thought, why don't we take this inhibited complex and add the reactive monomer back into the complex and see if we can increase the reactivity. And sure enough, that worked really, really well. Again, this is not LED cured this time. This is still just the 60C substrate, but we're forming our material on the substrate much faster because we're introducing these higher reactivity monomers that still don't have any polarity associated with them. So just to give you a visual of the reaction kinetics on the left, these are two DSCs. Again, the area under these curves represents the reaction enthalpy. So you can see on the top left, before the dicyclopentadiene addition, we have a reaction enthalpy of about 112 joules per gram. Below that, after we add the dicyclopentadiene, you can see we greatly increase the reaction enthalpy. So with this, we would assume that we were having the reaction happen faster, and this would fix the printing. And sure enough, it did. If you look at the video it's playing right now, you can see us printing onto a 60C plate. The material cures right when it hits the plate. We don't see the sheath gas blowing the material around anymore. So this is giving us much better print resolution than the strictly 5-vinyl 2-norbornene approach we had used before. So we're really happy with this approach, and this is what we're currently researching. We are noticing there is some overspray that we'd like to fix, but that's, we think, not as difficult as an issue. So these are some more pictures to the left here. You can see some pads that we printed on very different surface energy substrates. One of them is copper, high surface energy, the other one's Kapton. Both prints had pretty good print resolution. And then we decided to really test this and characterize it up at the KU band. So we used the WR62 method for this. And our dielectric loss is even lower than it was with the 5-vinyl 2-norbornene, probably because we have a very high monomer conversion compared to the 5-vinyl 2-norbornene. You can see now we're at 0.0017 at 17 gigahertz. So we're really happy with this approach. So with that, that's all I have to share. That's a little quick, but just in summary, hopefully I was able to share some methodologies and educate you on some of the current research work that we're doing on low loss dielectric inks for high resolution printing. Future work, there's a lot of future work to be had. We, like I said, want to fix that overspray issue, characterize some of the thermomechanical performance. These polydicyclopentadiene materials are supposed to have excellent thermomechanical performance. So collecting more data around that and sharing it, something that we want to do as soon as possible. And then because we can form this material so quickly on the substrate, it would be great to start to look at some conformal dielectric printing techniques and some really interesting packaging approaches that are no longer 2D, but 3D. And then lastly, adding a UV-induced cure mechanism. There's some different things you can do to disrupt that phosphite ruthenium bond with things like photoacids. We'd like to get the data on that and share it. So with that, I'll take any questions.
Okay, Yuri, thank you very much for this enlightening presentation. We switch from pure electronics now to materials, and I think it was pretty good as well. And there are several questions actually. The first one that came actually, when is this going to be available commercially?
That's a really good question, but that's not one that I can answer.
Okay. Okay, so this person will have to wait until this is announced by whoever is going to license that from you guys. The other question is, how can you, I mean, there was mentioned sometimes, it's a question that came here, it was mentioned during the laser times of basically increasing the dielectric constant.
Yeah.
How can you do that and at the same time keep that low losses?
So that's something we've been talking about a lot. It's actually, I don't think it'd be that difficult because we can add ceramic particles. Now that might disrupt the rheology, but things like BST have a very high dielectric constant. And maybe just adding small amounts of those nanoparticles would increase the dielectric constant pretty easily without disrupting the actual organic matrix we're using.
Okay, and then okay, and basically, how is this material be able to? Can you apply this thing also to ferroelectrics?
I'm not really sure. I don't really have a ton of experience in ferroelectrics. I assume it'd be a similar approach. Would be adding some sort of ceramic particle to the matrix, but that's not something that I've researched at all.
Okay. Another question that has come up here is if the 5V2N material that you described, it can range from a plastic elastomeric up to fully rigid. So basically, you can do flex as well as rigid with that.
Yeah, and that probably has to do a lot with the curing conditions. So that's, yeah.
Okay, so it's possible to do that.
I think so. We need to research that more.
And just, I think this is the last question that's come up. Isn't that the overspray a result of the aerosol process?
It might be. There might be a range of conditions that we can use with the different sheath gas or mass flow controllers to get rid of that. But again, that just requires more research. But it could easily be just an effect of the way we're operating the printer.
And then just another question, what's the viscosity of this material?
Well, it's tunable with this approach. That's what we like so much about it. So the stuff that you saw was around 5 centipoise, but we can grow that polynorbanine chain as long as we want and then stop it. So we could also do syringe dispensing with higher viscosities.
What about lower viscosity?
Well, so the monomers we're using, the 5-vinyl-2-norbanine is incredibly low viscosity. It's like water. So there really isn't much of a barrier when it comes to making it low viscosity. Now, adding dicyclopentadiene, that is a solid, but it's very, very soluble in 5-vinyl-2-norbanine and other norbanine liquid-based monomers. But that probably has a viscosity around 5 centipoise in if you had about 95% dicyclopentadiene and 5% 5-vinyl-2-norbanine.
So basically, you can make this also not only for single dispensers, single nozzle dispenser, but for inkjet as well.
That's the dream, but I don't know. Our Dymatics is out of commission right now, but I'd love to test it. I haven't tested that though.
Okay. Okay. I don't see any more questions coming online. So Yuri, thank you again. This was pretty good. Very well taken. Also good feedback on the audience here. Many high rises. Thumbs up, basically. Okay, so thank you, Yuri. With this, let's move forward to our next presenter. And that will be Dr. Daniel Hines from the Laboratory for Physical Sciences at the University of Maryland, who is going to talk to us about the production level fabrication of additively manufactured printed hybrid electronic circuits. Daniel?
Hi, hello, I hope you can hear me. I'm trying to share my screen here. Okay, hopefully you can see that.
Yes, we can.
Okay, good. Thank you for that introduction and thank you for the opportunity to talk today. I want to talk with you about what I call printed hybrid electronics. This is very similar to the AME concept, where how do you take additive manufacturing methods and apply them to the fabrication of electronic circuits? And so we're using primarily for these examples here, aerosol jet printing. And the idea of this PHE is, you know, as we've talked about, you know, a lot today, how do we get away from standard, you know, passive and active components, as you see here for resistors, capacitors, and inductors, and how do you replace them with ones that have been additively fabricated? Now, for a integrated circuit, we're probably not going to be able to print the bare die part of it, but what we can do is get rid of this package, get rid of the lead frame, get rid of the solder, and replace the wire bonds with printed interconnects. And you can see the difference here between the size of what's inside this package and the package. So you can, you know, really get a nice gain in both size, weight, and power for this. Now, there are some, you know, minimum printing requirements. You've got an ink stream that has a certain, the printed trace has a certain width to it. And you want to be able to put down enough material so that you can, you know, fabricate any given layer in a reasonable amount of time. And so that gives you a, you know, a deposition rate at which you want to be above for that. And, you know, when you design something that relates to the final product, final part that you've made, not necessarily what you're printing, because while you're printing, you've got solvents and such things that you have to drive off afterwards. So I think about this, what I call a post-process deposition rate and an ink stream deposition rate, which is what you have access to while you're printing. And we look at a scale factor between those two. You also want stable printing over at least, say, 3 hours. Printed trace widths between, say, 20 microns and 300 microns with good surface roughness, low surface roughness. We've set a maximum temperature for both in situ and post-processing of 150 degrees C. That way, if you have components that are temperature sensitive or polymers or substrates that are temperature sensitive, you're not exceeding the temperatures of those sorts of materials and components. You want to be able to print high quality conductive features, interconnects and circuits. And so we've set a resistivity of no greater than 6 times 10 to the minus 8 ohm meters. This is basically 4x bulk silver. And you have to have good adhesion onto the substrates, at least to be able to pass the Scotch tape test, for example. And so we wanted to come up with a circuit level demonstrator. And so, there's this Arduino Mini, of which NextFlex has taken that concept and fabricated this, what they call flex Arduino type circuit that you can see here. So this is their flex circuit. And so we approached NextFlex and said, hey, could we get your designs and bill of materials and help us to take what you've turned into this flex circuit and help us turn it into something that can be a PHE version of this. And so we worked with them and brought in their designs and their chipset and morphed it into something that can be designed and fabricated using aerosol jet printing. And so you can see here this the design laid out in AutoCAD. You've got 2 circuitization layers, the red and the green. You've got a printed interconnect layer, the purple here. The blue is all the components. You've got a bare die right here with printed interconnects. And we couldn't get bare die version of an accelerometer and a voltage regulator. So we have those at leadless chip packages with pads up mounted in cavities. And those cavities can either be, if you've got a 3D printed substrate, which is what this cartoon shows here, you can just build that right into the printing of the substrate for those cavities. You can mount the components in the cavities, and then you can print the various levers. Now we've got a base dielectric that goes down first. It's not shown in the design just for clarity. And then you've got the interconnects, circuitization traces, and dielectric separating all the crossovers between the 2 circuitization layers. And so you can see here, this is a fully fabricated, fully working circuit, this circuit level demonstrator, PHE Arduino type circuit. And what we want to be able to do is go and take this into, we've demonstrated in the research lab fabricating these demo parts. Now we've been working over the last couple of years with funds from OUSD to tech transfer that into our production space and do true production level fabrication of these sorts of circuits. And we want to then also put that through full reliability testing. And so, the circuit is not really, laid out to do a, full quantitative reliability testing, thermal cycling, temperature humidity bias, because, we've got 5 volts input here, and we've got these LEDs that light up whether you're, turning it based on the values from the accelerometer, for example. So what is it that you're measuring and quantifying for reliability? So what we've done is we've looked at the geometry, the local geometry around in the circuit and said, all right, let's pull these out. You've got this bare die with these printed interconnects, and you've got passive and active components mounted in cavities with moat fills and circuitization or interconnects printed across that. And then you've got areas of multi-layer circuitization where you've got metal traces printed on top of dielectric traces. And so we've pulled those out into these component level test coupons so we can now do full reliability testing. We can monitor the resistance of the traces here in all these cases and come up with, in situ measurements of these resistance values as we go through full reliability testing at the component level test coupons. And because these component level test coupons come out of the circuit itself, then when we put it all together, we should have the same reliability of the circuit level demonstrator as we do for the component level. And then we also are doing materials level testing. We're printing resistor dog bones for 4-point probe measurements on the thermal cycling. I'll show you a picture of those in a minute. And we've also got interdigitated electrodes for temperature humidity bias testing. And these materials test coupons will also be good samples for testing the geometry at that we have here at this multi-level circuitization. All right, so let's look real quickly at what the geometry looks like for each of these component levels. So this is a bare die, pick and placed onto a surface, and then we print. We want a smooth transition onto the top surface, onto and off of the top surface of this die for these printed interconnects. So you can see we've got these printed, what I call fillets, where needed around the edges, so we get a smooth transition. And you can see the printed interconnects there. Multi-level, multi-layer circuitization, printing here. You can see you can't really see the base dielectric so well, but you can certainly see the dielectric here where it separates these two circuitization layers. For passive components and active components, you can see that we've got these mounted in cavities, and we've done this moat fill, and we're printing the circuitization or the interconnects across that moat. All right, so for the materials level test coupons, you can see the test coupon here for the thermal cycling. You can see we've got two different versions, one that has a single trace printed or about 50 micron wide line traces, and the other is a several hundred micron wide trace. So it has a border and a serpentine fill to fabricate that feature. And you can see the nicely formed base dielectric layer that's first printed before you're printing the circuitization, the metal features. And so, we've worked very hard on understanding how to take this into true production level efforts. And part of that is to, if you've got a design in something like AutoCAD, and then it's important to know, you're going to want to set a specific deposition rate. And so the total volume of what you want to have printed with the divided by the deposition rate is going to give you a total time that you need to print for. And if you look at the total length that you're going to print for this tool path, the border and all the serpentine fill, that gives you a total length that you're going to print. And so you take that total time divided by that total length, and that gives you the print speed that you need to use to print this. So all that information is here provided in a print table. So this print table goes along with the design file and the tool paths that come out of that design file. And this is all the information that a tool operator would need in order to take these files and know exactly how to print them for the material that's being called out for printing these layers. For the temperature humidity bias, you can see here, same kind of information being shown here. You can see the two interdigitated electrodes for that. And then we also have these circuit level demonstrator coupons. This is the one on the left for, we call it life preserver, for the that's testing the interconnects over fillets. We've got this serpentine trace going across multiple times across the fillet, and we'll be able to monitor the resistance. And you can see we've got, this is the sample level, and we've got 4 samples we've got a quad of 4 samples per bare die, and we've got a 3x3 array of that. This is all on a single substrate then, so that gives us 36 samples that we can measure off of one substrate. For the passives mounted in a cavity, with the moat fill around the cavity and the circuitization printed across onto those electrodes. You can see here, we've got another quad sample, and we've got this. We've got two different types of capacitors in this PHE Arduino type circuit. We've got a LED diode, and we've got one type of resistor. So we've got a test structure for each of those components, and these will go into full reliability testing. You know, it takes about, so to do a lot size of 4 of these, takes about 45 hours with 5 overnight post-processing. This is very conservative estimates, where we're being very careful not to create, to do the thermal sintering slowly, so we're not building excess strain into some of these devices. So I think, you know, and we're doing very slow print speeds, so we can kind of watch this as we're going along. So I think these numbers can be dramatically reduced over time as we perfect the fabrication capabilities. All right, so, you know, like I said, there's a lot of work that's gone into, you know, just going from, you know, like, a circuit design, standard circuit design that we send off to a board shop. If you start with that, how do you do this additive design to tool path? And so we've got about a 20-page document which says how we have done this. It's a little bit of a manual process right now, but we have been working to improve and make that a little bit less manual effort. Reliability test plan document. We've got a full reliability test plan. I'll show you a table from that, but you know, again, this is about a 20-page document saying how we're going to do this full testing. And then we've developed another almost 50 documents for how do you, you know, what are all the specifications for the materials that we're using? What's the step-by-step procedure for taking this material, mounting it up on a tool, getting a good stable ink stream, and then printing these various different kinds of additively fabricated features with that. Custom tool configurations that we've had to do. I won't get into those, but there are a couple of custom configurations that we've done to these tools. And so we've fully documented how to do that. And then, you know, how you're going to fabricate, step-by-step fabricate all of these different features. And then all the details in the doing the fabrication for these different materials level and component level test coupons, and also for the circuit level demonstrator itself. So we've got these. They are all you know, available. We have these. If you're an XFlex member, we've got these all on the XFlex members portal. We hope to add, you know, all the reliability and physics of failure testing that we are doing on these. So at the materials level, test coupons, we're doing full physics of failure. We want to stress them to the point where they fail. On the component level test coupons, we're doing a set number of thermal cycles or hours in temperature humidity bias, and I'll show you that in a minute. But you know, we've worked very hard to, you know, there are a lot of issues that have come up. We've kind of, you know, given a name to about 21 of these issues, and you know, how are we going to given that we've gotten the issue, how are we going to come up with a solution to fix the problem? Some of the solutions have been simple. Okay, this is the problem, this we think will fix it, and indeed it does. So that's kind of a linear solution approach. But there have been others that have been a little bit more challenging, where we've got the problem, we come up with a solution, it improves it, but doesn't really fix it. So we have to do a feedback and continually, you know, try to come up with a good solution. And so we have both linear solutions and, you know, feedback solutions. And I've kind of, you know, put a list of some of them here graphically. You can see, you know, we were having, as we transition this to the production team and the production tools, we were having some issues where we were continually getting these mud flat cracks when we were, even after drying on the hot plate, on the build plate, heated build plate, even before we went into thermal sintering, where this is the kind of result we want after fully post-processing. And so it took a little bit of time to figure out how come, you know, how did we end up in left field here, just switching to another tool with a different team. And so, you know, we put some effort into that, and we were able to, you know, come up with the solutions and dial back in the exact fabrication and, you know, and good fabrication methods that we were looking for. We had an issue where, you know, if we when we do the pick and place of the bare die, if we don't have that adhesive layer underneath that die perfectly, wetting to the edges, and you end up with some air gap under there, then when you print this fillet, you kind of seal in that air, and as soon as you start to thermal cycle it, it cracks, and you have some problems. So it took a little bit of effort to fix that and have a pick and place method that really was robust and well done and didn't have any of this cracking. We also saw that as we transition across a moat and cross the edge of a component, or we also have, as you'll see in the materials level test coupons, we keep some copper pads so we can solder to one side of the copper pads and print to the other side of the copper pads, just an easy way to connect up to the test equipment. At that copper edge, if we don't have that dielectric form just right, we'll see some cracking at that edge. And so we took some time to do finite element analysis of these geometries where we're seeing this cracking coming in. And I'll show you a more detailed slide of this in a minute, but we were able to decrease the peak strain by about a factor of 5 and spread it out over a larger area. And this wasn't a catastrophic problem. It didn't show up until after about 2,000 thermal cycles, but yet it was a failure mode that we saw that we wanted to improve on. And so this is the modeling for that we did. So you can see this base dielectric, and we're modeling it as it comes over that copper edge and onto that structure. And so we modeled both the how far out that transition extended and what was the height of that transition above the edge. And you can see the strain map here for an optimized geometry coming out of the finite element analysis. And it turns out we did this for different substrate, different material sets and different geometries, and we found that at around 15 to 25 to 35 micron step height, this B height gave us an optimum improvement in the stress map. And so that was and that was for the thermal cycling. For the temperature humidity bias, you can see some of the results here. You get this dendritic growth across the electrodes, exactly what you expect. And you expect the silver to have a higher migration than the copper. So we really want to understand how this new material behaves in terms of temperature humidity bias for these printing methods. And you can see that for a couple different humidity levels, temperature and humidity levels here for the printed silver. And you can see it as compared to a plated copper. You can see it's got a bit of a different manifestation as a function of electric field. And so it turns out that in the copper, as I understand it, you get a nucleation, and that precipitates a dendritic growth right there. And you don't really get a separation between the two. Where here with the printed silver, what we're seeing is that as you're increasing the bias voltage, you're creating more and more nucleation sites. So it then spreads that out, and then you get a separate mechanism for the growth of that dendrite across the gap. And so it can actually improve for you compared to what in terms of mean time to failure. And so this is kind of a new mechanism, different mechanism that we're seeing in the copper. And so we're working to better understand that and modeling it from the failure analysis side. All right, so here is an optical image of one of these passive components in a moat, in a cavity with the moat fill. And you can see if we don't have this moat printed properly, you can see this one doesn't have that 15 micron transition thickness onto the resistor, and you can see this cracking that's coming in. And so this is how we kind of set this up in the finite element analysis model, and you can see the results coming out here. And as I said, it's not a catastrophic problem, but it is one that we wanted to be able to improve on. All right, and so we've taken all these test coupons into full reliability testing. in order to have a 90% reliability level at a 90% confidence, we want to be able to take lots of 22 of these test samples per test and put them through for thermal cycling. We want to do -40 to 85. For the materials testing, we did -40 to 125. But here we're going to go a little lower because of the restrictions on some of the components. This will be 5 volts because that's the operating voltage for the PHE Arduino type circuit, and we can do 1,000 hours. And for temperature humidity bias, 85, 85. Again, the voltage bias will be 5 volts, and we want to do 1,000 hours. And so the goal here is to run these 2 tests fully through with lots of 22 per coupon sample and have no failures. If we have no failures at this test, then we've tested out, again, like I said, at the 90% reliability level with 90% confidence. And so we have, I haven't been able to, didn't have enough time to get all of the data analyzed and into the slide set for today, but this is the first set of data that came off out of that testing. And so this is for the interconnect over fillets sample. And this is the thermal cycling for that. And so you're scanning, you're cycling from -40 through room temperature up to 85 degrees. You've got to hold at the top and bottom temperature, and then you continue to do that cycling. So what we've done is, so we've got a huge data set here. And so we've pulled out the values for each cycle as a function of a cycle number. We've pulled out the resistance value at the high temperature, at the low temperature, and as we pass through room temperature. There's 27 samples set here. So it's a little bit bigger than the 22 samples. And you can see they all line over. We have normalized the resistance. And so coming out of fabrication, we have a acceptance value of ±20% of the design value. But going into reliability, given that we have a trace that's been printed that has a specific resistance, that resistance has to be within 20% of the design, but now it has a specific resistance. We don't want that resistance to change by more than 5% throughout this whole test. And you can see these black lines as the ±5%, and you can see we're well within that 5% for, at all 3 of these temperature values. And the initial analysis that we've done of all the rest of the reliability testing for all the other types of samples, they're coming out to look basically, as good as this particular data set. So my computer seems to have frozen here. Is the slide set advancing? Can you still hear me?
We can hear you, but it's not advancing.
All right. I don't know. Let me.
I'm going to stop sharing for a moment.
Yeah, I only have a couple slides left, but something. All right. All right, now I'm back. Let's see if I can share again. All right. Is it working? Microsoft PowerPoint is not responding.
Okay, so you want me to bring your backups?
So what I can do is, there are only a couple slides left. So we've done, so I can just talk through the rest of it. I apologize for my PowerPoint freezing up here. But so not only have we done this for this, flat, 1 inch by 1 inch square type circuit, we've also done it for a 4-inch hemisphere. And we're working, we're partnering with, oh, you've got it up here?
Let me just,
all right, great.
Let me just bring it up. Okay.
Yeah, so the next slide will show, we're also partnering with NASA, both Goddard and Marshall Space Flight Center, to do this on a.
Here you go.
Okay. I can't see it, but okay, yeah. So here you can see this is on a inside surface of a sounding rocket door panel. So we're fabricating one of these circuits right onto the door itself. And we have two other circuits there just for risk mitigation that can actually be swapped out. And so, if we have a problem with, shipping or handling of this just before the launch, we can swap out the, we've got ones that are both thermally connected to the door panel and thermally insulated from it. If you go to the next slide, we've also done a 4-inch hemisphere version of this. This is a 3D printed 4-inch hemisphere, and using a 5-axis aerosol jet printer, we've been able to fabricate this right onto the surface of this hemisphere. Next slide. And so, people have asked me, I'll just finish up in the last couple of minutes here. People have asked me, what are some of the hard topics in this area of trying to get, trying to use additive manufacturing to fabricate electronic circuits. And one of them is you've got these, direct write printing tools, but they don't really have any way to actively monitor the quality of ink stream while you're printing. And so having in situ monitoring on these tools with active feedback in order to keep the ink streams within specification the whole time during printing would be a huge improvement. Advanced formulations of ink, you heard from Yuri, the work that they're doing there in order to try to come up with better dielectric inks for RF applications. It's fantastic. Really, we only have a couple of inks in our tool set right now in our ink library. And so having more inks with better functionalities, lower processing temperatures, things like that would be a great improvement. Design to tool path, if you look at those that PHE design, it can take quite a while to go from something that looks like it was done in a circuit design application, bringing that into a space that you can use, work on it to fabricate, to morph it into something that can be aerosol jet printed or inkjet printed. It can take a lot of effort right now. And there's some subtleties in local geometries. You don't want different local geometries in different places. You want the same local geometry everywhere. And so it's a bit of a challenge for the existing tools. I really liked the Altium presentation earlier today and the work that they're doing that would fit into that space. And physics of failure and reliability. I think we've got some great results for that here that I've shown you today. But how long has it taken to do reliability of printed circuits and just solder over the decades? And so it's a very mature area, but it has not been done with these new materials, with these new printing methods. And so it's just going to take time of a lot of groups doing a lot of work to build up that understanding and that body of knowledge for true reliability. And that's it. Thank you very much.
Okay, great.
I'll take questions.
Daniel, thank you for this great presentation. Enlightening, actually, there are several questions online here. One of them basically, actually starting with a fascinating update. He's asking basically if you have tested the reliability-wise, the variability from ink lot to ink lot, basically lot to lot variability as well.
Yeah, I mean, that's something that is very important. Do we have reliable ink manufacturers that are going to give us consistency from lot to lot? We haven't really looked at that. I wouldn't say as we run out of ink from a jar, we add more ink in, we buy more ink. We haven't really looked super carefully from the production side of things for that issue, but it could be one that's very important.
Okay, then the other question is saying with respect to the whiskers growth that you described there, the silver traces or the copper that you had there, those were just exposed to air, right? They were just printed on top of a substrate, as opposed to being encapsulated by another dielectric.
So we wanted to start off, at a base layer where we did not have an encapsulation there. So these did not have a barrier layer printed over it. At some point, we would probably want to do that and mature the testing to incorporate what kind of advantages we can get with different encapsulation methods. But the testing I showed you does not have any encapsulation over it.
Okay, so another question comes that says if you have done this testing with a multi-level type of interconnects by additive manufacturing, and my understanding is from what you explained that it's just a single layer.
Sorry, is that the questions for the interconnects?
Yeah.
So right, so what I've shown is only for single layer interconnects. We have done work where we can print a dielectric. We can print one layer of interconnects, print a dielectric over, and then print another layer of interconnects. That's certainly possible. We haven't done much. We haven't done any real testing on that, but that is certainly something that would be just about as easy to print as what we've shown.
Okay, and the last question that came up is, let me just read here. Yeah, you basically explained that basically as you have the effect of dielectric curvature on the, I think it's just the curvature on the reliability testing or the cracks mode on the traces, is just the dielectric curvature or is other factors of the dielectric properties that affect that reliability?
So it seems that, of course, it's going to be affected by CTE mismatches. So material sets can be important. We did look at different dielectrics for the moat fills, and so we did choose a particular moat fill material based on that, and then but we also saw a large effect from the geometry of that transition across that edge. That turned out to be an important aspect of it.
Okay, Daniel. So thank you very much again. I don't see any more questions right now. And appreciate for this great presentation, enlightening for everybody. I think that's something that many in the industry need to adopt as they start testing and evolving more with the additive manufacturing electronics technology. So with this, let's move to our next presentation, a bit of a change in the structures and these things, but we're going to now hear from Professor Cortus from Purdue University on 3D printing of soft materials for robotics. Basically, that will be another important thing to listen to, as robotics are becoming more and more important in our life-to-life for in many aspects, not just to help people around, but also to manufacture and do other things that we need to do. As well as was presented earlier today, also to help with prosthetics. So Professor Cortus, please.
Sorry, I just needed to unmute myself. Okay, so thanks for the introduction. I'll be talking today about 3D printing of soft electronics. And since other people were mostly talking more about rigid or flexible electronics, I'll first try to justify why we want to look towards fully soft systems in the first place. So if we look at the 10 biggest industries by revenue, and we kind of get rid of the ones that are just numbers on a computer, like insurance, And then we also get rid of things that, are service industries. We can see the industries that are left are, industries that focus on making real physical products. And out of those industries, we can see hospitals and food are really important. So food and medical are two of the largest physical industries in America and also two of the oldest. And technologies and robotics in these industries benefit from being soft. And since my talk is a little bit different than most of the other ones, I'll orient my talks at somewhat of a higher level to give a high-level overview of the field of 3D printed soft electronics. The detailed technical content in the work is focused on my own work, but I'll also emphasize a little bit about the work of other labs to provide more context about the broader field in general. So to give more detail about soft electronics in medical and food, one of the large commercial electronics firms originally planned to include pulse measurements and monitoring functionality in their first smartwatch, but ended up removing the feature just before launch because of the poor reliability of the measurement. So that's just because, when you take a normal rigid electronic and just strap it onto your body, it kind of slides around and there's all kinds of motion artifacts when you're trying to measure things. So if you look towards fully soft systems, they've been demonstrated to allow conformal contact with the skin, which can eliminate these types of measurement artifacts in medical devices. In the food space, robotics are being used to automate things like food handling, many foods of which are often soft. And we have a couple of examples here from a startup company called Soft Robotics Incorporated, where they're using soft grippers in order to pick up foods or fragile foods like cupcakes. During my work during my PhD, we additionally designed things like electronic skins that could be put onto the end of robotic end effectors in order to improve handling of very fragile objects like raspberries. And if we look at some of the things that are happening around the world, for example, in the UK, they had problems with getting enough laborers to harvest things like food. So there was just food kind of rotting in the fields. This might be a solution to some of those types of problems. So there are several ways to make things soft. Traditional electronics are hard, whereas rubber is very soft, but it doesn't have any electronic properties. So we can either take traditional electronics and put them onto rubber in a way that makes them stretchable, basically pattern them into spring-like structures that makes this whole system overall deformable. The other strategy is to take rubber-like materials and give them electronic properties by adding or doping electronic functionality into them. And this is the approach that I've used throughout my research because it is kind of more compatible with low-cost additive manufacturing approaches, and the resulting devices that we fabricate tend to be a little bit more mechanically durable. So we can also look towards why we want to adopt additive manufacturing within the field of soft electronics. The first methods used to make soft robotics were things like molding and injection. And the first methods used to make soft electronics were traditional patterning methods like lithography and etching. But there are a lot of application-driven reasons why we want to start printing these devices. The first major commercial applications for polymer 3D printing was in patient-specific devices in fields like dental. And we can see this concept of patient-specific design in a recent publication from the McAlpine group, in which they embed electronic sensors in a patient-specific replacement aortic valve. Especially in fields of surgery, there are situations where we might want to create a device on demand in a few minutes to complete a surgical procedure. These real-time fabrication applications can only be done using on-site additive prototyping approaches. In the field of tissue engineering, direct ink write 3D printing is emerging as kind of the top fabrication technique and the most popular way of making these types of new tissue tissue mimics. In this example from a lab in Israel, multi-material printing is used to deposit printed muscle cells that are integrated with electronic sensors and electronic stimulators actually at the cellular level. And this is envisioned to dramatically improve the quality of those new printed tissue devices. Lastly, if we want to make something like a wearable virtual reality suit that's the size of a person, we can't really do that using lithography. So if we want to start making things like human scale electronics, they need to be produced using scalable fabrication approaches like printing. And this is an example from our work where we were doing things like printing arrays of actuators that are, approximately the size of the palm of your hand in only about 5 minutes. So in addition to the application-driven motivations, there's kind of a more nuanced reason for using additive processing that's specifically related to the nature of soft materials. If we look at kind of the counterexample of lithography, so subtractive lithography patterns a film using subtractive processes like oxygen plasma. However, in stretchable systems composed of polymers, we typically don't have etch stops. So if we use something like oxygen plasma, it will typically just etch through all of the layers. When using things like lift-off lithography, the dissolution of sacrificial resistant solvents can damage organic or polymer-based films, which are typically swellable in those solvents and modifying the properties of the composites. Consequently, additive processing methods that avoid solvents are particularly advantageous specifically for these soft systems that aren't really sintered. So for these reasons, soft systems are almost kind of or additive is almost a necessary next step in the development of soft electronics. So compared to other talks in this event, intrinsically soft electronics are usually used for a range of applications that require less complicated device structures. So even something very simple like a strain sensor that consists of a single printed material can be useful in things like biomonitoring applications. On the other hand, the most complex devices that we envision making include things like sensors with in-sensing computing. And an example of this structure is shown on the right, where we use traditional fabrication methods to make an electronic skin that consists of sensors, oscillating circuits, and organic memory elements. So in this talk, I'll start with a general description of some of the materials considerations, and then I'll move on towards new nozzles and some examples of devices that we've been able to make using these technologies. Soft materials are really versatile, and they can be adapted to pretty much any type of extrusion technique. We typically need the ink to be in a liquid-like state when it's moving through the nozzle and return to a solid-like state after exiting the nozzle. This can be done using a few mechanisms like thermal cooling, solvent evaporation, catalyzed cross-linking, or UV-induced cross-linking. In this talk, I'll mostly focus on the design of direct ink write inks that have rheology that's suitable for this, liquid to solid transition through designing the rheology of the ink appropriately to have shear thinning behavior. And this, because this technique is more appropriate to things like tissue engineering that I was talking about earlier. So a typical shear thinning ink consists of particles that form a mechanically percolating pathway in the absence of shear stress. And then when we apply a large shear stress, these mechanically percolating pathways kind of break down and allow the ink to flow. In this example ink, we use carbon black dispersed in polymer oligomers. And the nature of those polymer oligomers is really important for enabling good print fidelity within the system. So we can see here that when we have a composition that has very low molecular weights for the polymer, we get this very nicely, strongly shear thinning ink that changes its viscosity by several orders of magnitude. Whereas if we have these higher molecular weights, that gives us a higher viscosity continuous phase that gives us a much higher dynamic viscosity even after shear yielding. And this has really important implications for the print process. We can see here when we're using a high viscosity ink, when we're changing directions, we can kind of pull the existing printed structures out of place, which can effectively cause defects in the printed structures. And in this case, we're even just printing back and forth on top of itself, but you can imagine that if we were printing things like a 90-degree angle, we would show even more dramatic defects within the printing process. And this gives an example of when we're using these low viscosity, highly shear thinning inks, we get almost perfect line widths and perfect print fidelity, whereas when we move towards these higher dynamic viscosities, we end up with defects like these end beads that can impair the device functionality. Now, there's a little bit more nuanced reasons to pay attention to the dynamic viscosity. When pressure is applied in a syringe, the pressure would ideally be fully accommodated across the nozzle and be used to extrude material out of the nozzle. However, there's parasitic sources of mechanical compliance in the syringe that include the compressibility of the ink itself, as well as the compliance of the syringe, and which is typically made of plastic. So if the dynamic viscosity is high, we need to print at higher pressures, which increases the time it takes for the extrusion rate to meet a steady state. So that means that when we turn on and off the pressure in order to switch on and off the flow of ink, there's this kind of lag time that goes away or disappears when we move towards these highly shear thinning inks with low dynamic viscosity. And I can tell you from experience that printing complex circuits like this is really tricky, especially when using the traditional inks that usually have quite a high dynamic viscosity. So from the previous few slides, hopefully I've convinced you that the rheological properties of these inks are really important, or especially these soft inks. And we can tune the rheological properties by changing the viscosity of the continuous phase. However, for these stretchable systems, we also have an additional consideration in that in the cured state, once we cure the polymer, the elastic modulus is related to 1 over the molecular weight between cross-linking. So we have this kind of apparent trade-off here where we want a low molecular weight in order to get good rheological properties, but we want high molecular weight between cross-linking in order to get the mechanical properties that we want in soft systems. So in this case, we developed an ink that uses a strategy of simultaneous chain extension and cross-linking that can decouple these mechanical and rheological behaviors. And we have an example here where we show the mechanical properties of one of these inks as we change the ratio of chain extender to crosslinker. You can see that the mechanical properties change pretty drastically over this range, but the rheological properties are exactly constant for these different compositions. So another consideration here is that while the short-term extrusion response is determined by the compliances, the long-term response of the extrusion rate is usually determined by the rheological properties of the ink, which can be very complex. So we empirically see all kinds of behavior in inks, which can include increasing or decreasing viscosity over time as we print. For the ink that I've been describing, we happen to observe almost constant viscosity over time. And this is actually the really big reason why I ended up using this particular ink. When we need to do things like printing hundreds of devices to test the effect of these different device parameters, we need to be able to basically turn on the printer and let it print for 12 hours and have constant line widths and constant print extrusion rates during those entire, several hour print sessions. So we have some theories about why this particular ink is very stable, but we haven't experimentally verified them or published that yet, so I won't talk about them here. So in this example, we used ink design to improve print stability, but more recently, we've been working on kind of a patent pending hardware-based solution that corrects for these variations in ink viscosity over time. So in the last few slides, I've discussed the impact of polymer phase on the ink design. in the next few slides, I'll talk a little bit about the impact of the selection of different types of particles. So when it comes to the electrical properties, the filler aspect ratio has a really important effect. So the percolation threshold kind of describes how much volume fraction of particles you need in order to get electrical conduction through the system. And this percolation threshold decreases a lot as we increase the aspect ratio of the polymers, as you can see from this, seminal work looking at the effect of aspect ratio on the critical volume fraction. Now, the reason this is important is because if we want to make a stretchable system, essentially we're taking this composite material and we're stretching it, which reduces the number of percolating patchways. And so the stretchability typically improves as the particle concentration increases above the percolation threshold. What this means is that these high aspect ratio structures typically give us much better stretchability within these stretchable composites in terms of the electrical stretchability. However, we have this trade-off with the ink design. So increasing the aspect ratio improves the cured mechanical and electrical properties, but increasing the aspect ratio compromises the shear thinning behavior and gives us this kind of a high dynamic viscosity. And the origin of that is kind of just very similar to the same as the origin as having high molecular weights for the polymers, which gives us kind of this high viscosity even after shear yielding. So when we look at filler size, the resistance within the bulk of a composite material in the cured state is determined by the bulk conductivity as well as the contact resistance. So in flexible or rigid systems, you can kind of just sinter these composites in order to completely remove this contact resistance. But in stretchable systems, if we fully sinter it, then it becomes rigid and it's not intrinsically stretchable anymore. And so we kind of just have to deal with these contact resistances. So when we do calculations in order to figure out the optimal size of these particles in stretchable composites, we find that the optimal size for conductivity is in the range of several microns. However, in order to print through a extrusion nozzle, the fillers must be approximately at least 10 times smaller than the size of the nozzle. And this gives us a trade-off between this filler size and the composite conductivity, in that we need to reduce the size of these fillers in order to print through smaller nozzles, but then that will also give us significantly lower conductivity. One method that we can look towards to eliminate this trade-off is to use conductors that are molecularly deformable and therefore don't rely on finite particle sizes. In this example, we use an ionic ink that's composed of a deputectic solvent, which is an ionic conductor that's bio-derived and biodegradable. In fact, most of these deputectic solvents are actually made or based on fertilizer, which means that they're biocompatible and pretty cheap as well. So we designed these inks to be used with polymer-based rheological modifiers, which eliminates the problems with nozzle clogging. In this work, we were able to design a combination of UV curable elastomer and UV curable ionic conductor that have equal and tunable mechanical properties. They also exhibit intrinsic bonding at the interface, which allows us to UV cure them together and then stretch them while still having perfect interfacial adhesion at that interface. So obviously the drawback of these ionic conductors is the low conductivity, meaning that they're primarily used as deformable sensors. In our case, we were actually using them as electrodes for electrostatic actuators, which don't require high conductivity. So a quick note is that there are other emerging design inks or other emerging ink materials for these types of intrinsically stretchable systems. Some of the more popular ones are these liquid metals, that have good mechanical stability, metal level initial conductivity, and have very little change in their resistance as a function of strain. And you can see from recent resistance or recent publications, this is probably one of the hottest topics in the field of material science right now, is how to design these types of liquid metal inks for 3D printing. So you can see from a recent review article that we published in my lab that polymer-based inks are also becoming quite popular. Fully polymer-based inks that have polymer-based conductors also allow extrusion through very small nozzles, since the ink is entirely based on polymers and doesn't have these rigid conductors. So if we look at a recent review article, the reason I call these emerging materials is because if we look at a recent review article, this review article specifically focuses on devices that were published recently that actually have some functionality when integrated with a person. So they can be put on a person and measure some useful property, whether it's deformation or chemical properties. And based on this review of these papers, 27 of them use traditional composite materials, 4 of them are using ionic conductors, 2 are using conductive polymers, and 1 is using liquid metals. However, if we look at more recent papers, like papers that are only looking at the design of new materials for 3D printing inks, we would see a much larger proportion of these that are using things like liquid metals and ionic conductors. So they haven't quite reached the point yet where they're being widely used for real human interfacing applications, but they're kind of on their way there. So a really important part of designing multi-component systems is the adhesion. So in stretchable systems, we often need to deform the devices during their normal operation, which means that the adhesion between materials and multi-component systems is critical. So this is particularly problematic in hybrid printed systems that include rigid chips. So you can see in this work, we were essentially connecting a LED using these intrinsically stretchable printed components and then stretching it. If we don't have the right adhesive components, it can only stretch to less than about 20% strain before adhesive failure, whereas optimizing the adhesive is really kind of the key way in order to improve the mechanical properties of the system. In fully soft systems, we often end up having heterogeneous mechanical systems. In this case, we have an example where I was printing a device and we were kind of applying pressure on it in this direction, which could cause delamination if there wasn't good adhesion between the 2 different materials in the system. And so this work really allowed us to explore the range of different compatibility between ink chemistries. There's a lot of different ways that you can cross-link things like elastomers. You can use hydrosilanes, thiolines, monoacrylates, polyacrylates, epoxies, and urethanes. Here's kind of a quick summary of the experience that we generated, in that some systems are obviously compatible with each other. Some have incompatible curing, in that they don't cure when they're in contact with each other due to things like poisoning of the catalysts. And some systems don't have good adhesion to each other. So my work has mostly focused on these thiolines for exactly the reason that they have really great adhesion to almost every other type of 3D printable material. So when it comes to nozzle innovations, we can look at a few things like active mixing, as well as active rotating devices and multi-material printing. And I'll focus on this multi-material printing because that's what we ended up using to develop our champion 3D printed devices. So in this case, we have a nozzle that consists of 3 materials that can control the pressure to each of these inlets independently. That allows us to extrude materials through this nozzle, and we can print a a filament that has a composition that's kind of graded along its length. So this enables a few things. One is that it enables us to print feature sizes that are actually smaller than the nozzle dimensions by changing the ratio of the pressures within the nozzle. So this is really important when it comes to increasing the scalability while simultaneously reducing the feature dimensions. So this intra-nozzle patterning allows us to accomplish kind of complex device structures. In this example, we can see that we're printing electrodes only on the left side, but not on the right side, which allows us to accomplish kind of unusual device structures. I'm taking longer than I expected, so I'll skip through a couple of the slides. This scalability that is enabled by 3D printing allows us to do things like bundling these actuating fibers together in order to create things that mimic muscle fibers that are consisting of many small actuators. It allows us to also make things like dynamic reconfiguring of devices, where we can operate these devices at their resonance frequency, at their mechanical resonance frequency, in order to accomplish sophisticated device movements. And lastly, we can make very sophisticated 3D structures out of these actuators that allows us to make things like lattice type structures that could be compatible with things like cell culture applications. And I'll skip this last slide again for the interest of time and ask if anyone has questions.
Okay, Alex, thank you very much for this enlightening presentation and opening the eyes to other things that can be done with basically additive manufacturing electronics now for basically flexible materials in the point of view of application to robotics and medicine and so on. Actually, there was one question that came in the middle of your presentation, but you answered it, which was related to the use of liquid metals. So you answered that already, which was kind of timely. It was like a minute after the question was posted, you answered it. Then the other question that just came up is, have you done any kind of reliability testing of this by flexing it, flexing cycles and so on?
Yeah, we've certainly done those types of reliability testing. I don't have that in these slides. That is kind of a major limitation of a lot of these composite-based materials. If we stretch it to more than maybe 50% strain, there will be some degradation over thousands of stretching cycles. But that is definitely a big area for future development. And to be honest, the field is so new that not that many people have kind of just gotten around to that yet.
Okay, Alex, thank you very much. We don't have any more questions right now, so I really appreciate it. This was a nice complement to the rest of the things that we have discussed today. And with this, I would like to now introduce our last speaker of this session of the AME Academy, Mr. Michael Grady, is a research engineer at the Georgia Tech Research Institute, who is going to talk to us about improved bandwidth using a 3D printed quasi-ideal grounded container waveguide transmission line. Michael, the stage is yours. Michael, you just need to unmute yourself.
Yes, can you hear me?
Yes, we can hear you.
No problem.
Just use the screen share.
Not a problem. All right. Are you guys seeing the proper screen?
Yes, we are seeing it. Great. Thank you.
No problem. So I'd like to introduce myself. I am Michael Grady. I am a research engineer at the Georgia Tech Research Institute, and I am housed in the Advanced Concepts Laboratory. The title of the talk today is called Improved Bandwidth Using a 3D Printed Quasi-Ideal Grounded Coplanar Waveguide Transmission. This work is adapted from a previous conference paper originally presented at the WAMICON conference. This is, again, is the title of the paper. And I just wanted to give an acknowledgement to my co-authors, which are Dr. Josh Kovitz and Avaram and Jackie from Nano Dimension. The link of the paper can be seen below. So what is the overall takeaway of my talk today? 3D printing a continuous metal wall within the substrate of a printed circuit board allows you to replace grounding vias and thus increase the usable bandwidth of a transmission line structure. If we take a look at the figure to the top left, we have an edge view of a printed circuit board that has grounding vias. We can see those grounding vias going into the board. We can see those grounding vias going into the board. And so if we look at the figure to the bottom left, we can see an X-ray of that same board where we see the conductors, which is the light gray, and then the dark circles, which are those vias. Taking a look at the figure to the right, we have a printed circuit board with a metal wall that is going throughout the board. And again, we have that same metal wall with the X-ray view. So this is the outline of the remainder of the talk that I will give. So you guys have seen a number of amazing presentations today, but this is the approach that I'm looking at. So traditional PCB fabrication processes can be very limiting at times. They limit the number of layers that you can use within a board. They limit the minimum feature size and the transmission line spacing. And we are limited to 2.5D structures, which mean that we can only have a structure in the XY plane or the Z plane. Lucky for us, we have 3D printing that gives us a unique opportunity to have any number of board count, and it also allows for unique RF structures. Today, I'll show you a very simple structure that we use to, and a very simple RF structure that's also a unique structure in itself. That structure is a grounded coplanar waveguide transmission line. If we take a look at the figure to the left, we can see the diagram of the grounded coplanar waveguide transmission line. And that consists of a center conductor, which is housed by two side ground plane conductors. You have a substrate, which is a thickness of H, and then at the bottom and beneath that, we have a copper backing or a metal backing. If we look at the figure to the right, we see the traditional implementation of the grounded coplanar waveguide structure, which is typically implemented by vias to ground. Again, we have those that center conductor, those side ground planes, and then the vias to ground connect us to that bottom ground plane. And so the grounded coplanar waveguide is a good candidate to show us the advantages that 3D printing can offer for microwave devices. The impedance of this structure is calculated by a ratio of that center conductor to the gap width to that substrate height. If we look at that box, the table to the right, we can see that if we have a conductor width of about 50 mils, a gap of about 7 mils, and a substrate height of about 30 mils, we can get an impedance somewhere around 50 ohms. And so the grounded coplanar waveguides offers some advantages over microstrips, which a microstrip is take away those top side ground planes, and then you have a microstrip. And it offers advantages in that it gives you lower loss, it gives you improved isolation to other conductors, center conductors, and then it gives you a wider bandwidth because the impedance profile is maintained over wider frequency ranges. So how is the grounded coplanar waveguide constrained? We're constrained by the cutoff frequency. And so if you take the grounded coplanar waveguide, there's something called the effective waveguide cutoff, and that effective waveguide cutoff has a spacing that must be a wavelength, must be less than a wavelength over 2 to avoid higher order modes. If you take that relationship, this means that the cutoff frequency is equal to the speed of light divided by 2 times the edge-to-edge distance between the vias multiplied by the effective permittivity. The resonance frequency can be related to this cutoff frequency by 0.65 times that cutoff frequency. So given that equation, if we want to increase that cutoff frequency, thus increasing the usable bandwidth of our structure, we have to minimize the via distance. So there are a number of rules of thumb that are out for a designer to design a grounded coplanar waveguide. Again, we have that waveguide cutoff that says a wavelength over 2. We have the quarter wave resonator rule, which says that if you have a monopole, then somewhere around a quarter wavelength, you can see radiation. And then there's an RF industry practice that says that if you have grounding vias, you should space them a wavelength over 20. So given all these rules, which one should we follow? So at the end of this presentation, we'll give a recommendation on which one should follow, especially if they have the resources. So now we'll go into grounded coplanar waveguide comparison using both circuit and finite element simulators. So for this study, we used Keysight's ADS circuit simulator, and we compared it to ANSYS's HFSS finite element simulator. If you look at the figure to the left, this is a diagram of the Keysight circuit simulator. So the circuit simulator assumes that there's a perfect current path along the entire length of the transmission line. So if you take that top ground plane and you go right to the edge of that top ground plane, it assumes that there's a perfect current path from the edge of that top ground plane to the bottom of that ground plane. So what we had to do in HFSS was create that exact setup. So in HFSS, you can see the figure to the right. There's a grounded coplanar waveguide, and you have 2 ports, one at the top of that structure and one toward the bottom of that structure. If you look at the top right of that figure, you can see that there's a perfect electric conductor sheet that extends along the edge where the port is and along the edge where the center conductor is. And so that makes it equivalent to the ADS circuit simulator, where there are PEC sheets extending from the upper to lower ground plane. So what happens when we compare these two simulators and look at the performance? In the figure to the left, we can see that the ADS simulation of a transmission line for a transmission line that gives us a has wavelength of about 10 gigahertz. And if you look at the black curve in that figure, we can see where there's a resonant at 10 gigahertz, 20 gigahertz, 30 gigahertz, 40 gigahertz, 50, 60, and so on. So the same comparison with the HFSS model is that we can see that it follows very closely to that ADS model, but after 30 gigahertz, we see some deviations. And so this is due to the way that the 3D modeler EM simulator takes into account the fringing effects. So it's a more accurate representation of those fringing effects. And so at higher frequencies, you see those fringing effects, and it affects you at those higher frequencies more. We also looked at different iterations of this structure as well. A, again, is the ADS equivalent model. B, at the top, is a solid ground plane block. C is a finite thickness wall along the direction of propagation. D is a finite thickness wall along the direction of propagation, and the port. So looking at the figure to the left, we can see that the ADS equivalent is the red curve. This is the curve that we just saw. Looking at the curve for the solid block, we can see that that is the green curve. And so it pretty much agrees with some slight shifts again above 30 gigahertz. If we look at the finite thickness along the direction of propagation, we can see that that is the blue curve, and it agrees with some slight degradation due to the increased inductance. So if you take that PEC sheet, which is, an infinitely thin sheet, and then you add some thickness to it, you have inductance. And so that inductance can give you some degradation there due to the currents traveling across that. We also can take a look at the finite thickness wall along the direction of propagation and the port, which is the purple curve. And so again, the peaks follow very closely with some reflection loss again. We also took a look at some comparisons to the ADS equivalent to adding more vias. Figure E is a case where you have 2 ground vias. Figure F is a case where you have 3 ground vias. Figure G is a case where you have 5 ground vias, and figure H is a case where you have 9 ground vias. All we pretty much did was we just took the distance and halved it and just made the ground vias more. So if you look at the curve to the left, again, we see the ADS equivalent curve, which is the red curve. It's the curve that we've already seen. For the 2 ground via case, we see a lighter red curve with the circular marker. And so if you look at the curve to the top, that is insertion loss. And so right about 6.7 gigahertz is where that curve starts to deviate from the ADS equivalent curve. And so this is also the value of the resonance that is calculated from that cutoff equation that we use. And so that happens about 6.7. For the 3 ground via case, the resonance occurs at about 14 gigahertz. And we can see for the blue curve, it starts to deviate from the ADS equivalent somewhere around 14 gigahertz. You can see it better for this case, which is the 5 ground via case. And we can see that the resonance starts to occur at about 31 gigahertz. And you can see that pretty well that for the gold looking case, it starts to deviate somewhere around 30 gigahertz. And then the 9 ground via case, it occurs around 81 gigahertz, which is slightly above the frequency range that we're using. So from this point on, I will now refer to the finite thickness wall along the direction of propagation as the quasi-ideal grounded coplanar waveguide transmission line. So whenever I refer to that will be the quasi-ideal grounded coplanar waveguide transmission line. So what is the quasi-ideal grounded coplanar waveguide transmission line? It is the circuit board comprised of a metal wall contained within the substrate at the ground plane edge running continuously along the direction of propagation. If we look at the figure to the top left, we can see a image of a printed circuit board. It is actually a 3D printed circuit board, and we can see our center conductor in the middle, and that is sandwiched on the top by the 2 side ground planes. We can see the bottom ground plane beneath that, and then in that middle, sandwiching that center conductor, we can see those metal walls that are sandwiching, connecting the top ground plane to the bottom ground plane. Looking at the figure below that, we can see that same circuit board with the connector, and those figures on the right are X-ray images of this same board. And we can see that the light gray is those top conductors, and then that black strip is the metal wall, and the other one is an isometric view of the X-ray. So we use a 1-inch 3D printed grounded coplanar waveguide for our test sample configuration on a 30 mil substrate. We also use some Southwest microwave connectors, and we did 2 things. We simulated the predicted performance in ANSYS HFSS, and we also measured the performance with a Keysight PNA system. The figure to the left is a simulated mock-up of a printed circuit board with the model connectors and the model board. And the figure to the right is a picture of the actual measured board with the connectors and the 3D printed board. And these were the dielectric constant that we use. So we use 6 grounded coplanar waveguide configurations, and we simulated both of those. We simulated and measured those to compare. The configuration A is 4 ground vias separated by 300 mils. Simulate B is 7 ground vias separated by 140 mils. C, 13 ground vias separated by 60. D, 25 ground vias separated by 20. And so again, all we did was just took that distance and cut it in half, and we added more vias. F is an indented continuous wall. So if you take a look at those vias, they are constrained by the via pad. And so the via pad restricts you to where you can only get it so close to the edge. And so what we did was we kept the continuous wall indented at the same plane as those vias. And then we also made that same wall flush in configuration F. And again, that's what we call the quasi-ideal grounded coplanar waveguide. So here are some pictorial views of those configurations that I just mentioned. Again, those vias running down the edge, we can see the edge view in that figure to the left. and then we can see the corresponding X-ray view with the light gray being the top conductor and those dark circles being the vias to ground. We can see E in the middle with the indented continuous wall, and we can see the corresponding X-ray view. And we can see the quasi-ideal, which is the flush continuous wall on the figure to the right, and we can see the corresponding X-ray view as well on that bottom figure to the right. So looking at HFSS simulations, we have the design A, which is the via spaced at 300 mils. So the theoretical resonance that we calculated, which is defined by the equation at the bottom left of the screen, is 0.65 times the cutoff frequency. Again, the cutoff frequency is equal to the speed of light divided by 2 times the edge-to-edge distance times the permittivity. And so the calculated resonance occurs at about 8.82. The calculated theoretical resonance occurs at 8.82 gigahertz. So if you take a look at that figure A, the simulated HFSS resonance occurs at about 8.6, which shows that there's pretty good agreement. Looking at the next case, we have the via spacing of 140. The theoretical resonance occurs at about 18.9 gigahertz, and then that simulated resonance occurs at about 18.8 gigahertz. So again, good agreement. Next one is 60 mil spacing. We see the theoretical occurs at 44 gigahertz, and then the simulated resonance occurs at about 38.9 gigahertz. And so this is due to the way that the equation was defined. So there can count more fidelity in the equation. But we also have the 20 mil case, and it says that a theoretical resonance occurs at about 132 gigahertz, but the simulated resonance occurs at about 47. So now we're starting to get some deviation here. When we have the continuous indented wall, the fact that this equation takes into account the distance between vias, there is no theoretical resonance because it would be infinity, but the simulated resonance occurs at about 53 gigahertz. We can also see that continuous flush wall, where the simulated resonance is outside of our bandwidth, which is above 67 gigahertz. So now looking at these same ones, but measure the actual measure, again, for the 300 mil case, we can see that the measured resonance occurs at about 12 gigahertz and the theoretical says about 8.82. We can see for the 140 case that the measured resonance occurs at about 24 gigahertz. We can see that for the 60 mil case, the measured resonance occurs at about 36 gigahertz. We can see that for the 20 mil case, that it occurs at about 41 gigahertz. And the continuous indented occurs somewhere about 58. And then the flush indented occurs somewhere about 65. But the thing about that graph is that we calibrated it at 67 gigahertz. So this could also be a measurement artifact that is causing that dip at 67 or so. So one thing that you'll notice is that both the simulated and measured data shows that the quasi-ideal ground coplanar waveguide extends the usable frequency range of the transmission line. And so as you get those vias closer, you're pushing those higher order modes up in frequency, which means that you can use it at a higher frequency. And so we observed that resonances with those via spacings are as tight as a lambda over 10. And so if you take a look at case D, the measured resonance, we can see that that corresponding wavelength of where that resonance occurs is about 0.1 of a wavelength. So this observation pretty much reinforces using the lambda over 20 rule of thumb. If you can afford it, just make your vias lambda over 20 and you can push those higher order modes up as high as possible. So in conclusion, again, what we showed you was that 3D printing a continuous metal wall within the volume of a printed circuit board substrate can replace grounding vias and increase your grounded coplanar waveguide transmission line bandwidth. We showed that with 25 vias, we saw that the higher order modes occurred somewhere around 41 or so gigahertz. We showed that with the indented continuous wall, the middle figure, it occurred at about 51 gigahertz. And then we showed that the flush wall, that it pushed those higher order modes outside of our measurement band, which was 67 gigahertz. Use a continuous wall and you can afford yourself better performance without having to increase the material parameters. So I'd like to give, again, thanks to my original contributors to the original work. Again, thank you to Josh and Kevin. Kevin actually took those X-ray images for us. Josh and Kevin of Georgia Tech. and Everam and Jackie of Nano Dimension, and the paper can be found there. Thank you for watching. Are there any questions?
Michael, thank you for this wonderful presentation. I don't have, the audience doesn't have any questions. You made such a clear presentation and with very logical approach that it was well absorbed right away, okay? So thank you, it was very obvious conclusion from the way you approached the whole thing as well. So I would like to thank you, and with this, basically, I would like to we're going to close the session for this AME Academy. And I would like to basically thank all the staff from the AME Academy, as well as, of course, the audience. But in summary, basically, what we saw today is several applications and directions of the industry in packaging, system in package, biomedical applications, sensors, robotics, 3D electronics, and all electronics in general, and of course the RF and millimeter wave. And for the guys who attended this morning, this particular CT corresponded to the work by James regarding that cube that was shown by Gene Weiner as the first speaker in the morning. And this basically is a case where there is no vias, and all the things that you do, these are tubes, which actually are micro coax cables connecting all the high-speed communication components of this PLL circuit. And this was converted from a 40 by 60 millimeters to a 10 millimeters by 10 millimeters by, 20 by 20 millimeters by 10 millimeters high tube. So if anybody wants to get in touch with James, this is the website as displayed there. And we'd like to, again, thank you everybody in the audience, and thanks everybody else for participating and the speakers. Thank you, and look forward to the next announcement for the next session of the AME Academy.